right, hi everybody. I'm just gonna wait a minute or two. See the numbers ticking up slowly. Okay, I guess I'll get started. Hi everyone, thanks for joining us at hour 27 of the Weather and Climate live stream. So we've got 73 hours to go. I'm Nick Seiler. I'm a professor at Oregon State University, and I'll be your host for this segment. Before we get started, I just want to remind everyone first that all of our speakers are appearing in their personal capacities and expressing their own views. So they're not representing the institutions they work for, and their views may also differ from those of other participants in the live stream. That said, we're all here with a purpose, and that's to remind the public and ultimately our representatives in Congress why weather and climate science is important and why it's important to keep funding it at the federal level. And the main reason it's important is that good weather and climate forecasts really benefit everybody. And US scientists have really always been world leaders in the science that underlies these forecasts. So some examples, the US developed the first computerized weather forecasts. We also developed the first computer models that simulate the impacts of carbon dioxide and other human emissions on the climate. We've developed a huge network of observations, weather stations to satellites, planes, balloons, etc. And this excellence is really because of investment by US taxpayers through acts of Congress. This has long had bipartisan support for the obvious reason that it has huge economic benefits. So the Federal Reserve estimates that government-supported research from the NSF and other agencies has had a return on investment of something like 150% to 300%. So that means for every dollar US taxpayers have invested, we've gotten back between $1.50 and $3, according to the Federal Reserve. And this number is probably even higher for weather and climate research. But now funding cuts are threatening to really kneecap weather and climate science in the US. Some of these cuts have happened through executive order, and that includes staff reductions at the National Weather Service that have left these weather stations short-staffed. But ultimately, it's Congress who controls the power of the purse, and Congress hasn't yet weighed in on the president's budget request. So this is where you all come in. There's a banner at the bottom of the screen, wclivestream.com/act. So that will take you to a website where you can put in your zip code and find resources for contacting your senators and your congressional representative. So I encourage you all to do that. With that, we'll move on to our next speaker, Andrew Winters, who will be discussing how the upper level jet stream influences high impact weather events. So go ahead, Andrew.
Hey, Nick, thanks for having me, and big thanks to all the organizers. It's been a lot of fun to see what everyone's been up to and also to support this very important cause here. My talk today is going to be really focused on the upper level jet stream. So trying to understand how this rapidly moving river of air in the atmosphere impacts the production of high impact weather. And one of the ways I like to think about the jet stream is very similar to these two confluent rivers you see on my title slide here, where basically just like two rivers are rapidly moving sort of ribbons of water near the ground level, the jet stream is a rapidly moving river of air that can meander. It can merge with other tributaries in the atmosphere to create even more rapid areas of atmospheric flow. And so today I'm going to talk a little bit about how that impacts sort of the high impact weather type development and how we can think about our jet stream as sort of this atmospheric intercontinental highway, just like an interstate highway, for example. So when it comes to my past, though, before I get into some of this detail on the jet stream, I want to cover a little bit about how I got here. I grew up in southern Wisconsin, went to the University of Wisconsin-Madison, and did my undergraduate and PhD research there through NSF-funded projects. But what really got me into research as a career was trying an REU experience, which is an NSF-funded research experience across portions of the country, and it's held at many different universities. I got to do one at the University of Oklahoma. That's me in the top left there, working on a project focused on severe thunderstorm wind gusts. And before this moment, I really had no desire to do any research, as a career. I wanted to go on, get a degree, become a forecaster in the Weather Service, but I really fell in love with the idea of being at the forefront of knowledge generation and trying to understand really how our atmosphere works. And that's really what sent me on a path there. And so I came back to the University of Wisconsin to get my PhD before moving on to the University at Albany in New York. There I worked on both an NSF-funded project and a NOAA-funded project looking at predictions of extreme weather events and also jet stream connections there, before finally arriving to my current position here at the University of Colorado. And here I lead sort of our synoptic meteorology group. We look at day-to-day weather conditions, how it impacts extreme weather events, and lead a large number of graduate students who are really doing great work in that area as part of our program. So getting more into how we discovered the jet stream, I want to go all the way back. And this feature has, it's always been around. It's always existed in our atmosphere, but we really didn't know about it until, let's say, the last 100 to 150 years, when our observations identified this feature in the upper atmosphere. And before this time, we really didn't have much of a reason to know it was even there in the first place. One of the first ways we got observations that there might be some of the structures in the atmosphere that support a jet stream is through some analysis that was done by Coxwell and Gleicher back in the late 19th century. In this particular scenario, these two individuals took a hot air balloon well up into the atmosphere and noticed that over time, conditions were getting colder and the air was getting thinner. But before this time, we had no idea that this was actually happening. And it turns out, as they rose 4 or 5 miles up above the Earth's surface, eventually one of the individuals became incapacitated due to the lack of oxygen that was available at those high altitudes, and they both began developing frostbite. Luckily, Coxwell was still with it enough to be able to release enough of the release one of the enough of the gas to be able to allow the balloon to slowly descend, where both came to and were able to share some of their observations regarding this common structure we know from any weather balloon launch that we emit into the atmosphere, that temperature generally decreases with height overall. But in the start of the 20th century, de Bort was the first to discover that once you reach a certain level in the atmosphere, the temperature stops decreasing. And the temperature either stays constant or it actually starts to increase with height. And it's going to be this interface between where the temperature stops decreasing with height and starts to increase, where the jet stream sits within the atmosphere. And so discovering the stratosphere, this layer where the temperature increases with height, basically was our lens through identifying this key feature that drives a lot of weather we see here near the surface. And this interface resides about 10 to 12 kilometers above the Earth's surface. You could think of it as about 6 or 7 miles above the surface. Now, in the middle, getting closer to the middle of the 20th century, this is when we began to see more of the horizontal spatial structure of the jet stream. So we got a sense from some of the launches from de Bort that there was sort of this localized maximum in wind speeds aloft, but we didn't have a sense of the spatial distribution of those wind speeds. And to determine that was really through the coordinated weather balloon launches that we take for granted these days, the types of balloon launches that occur all across the world twice per day. But imagine doing this back in the early 20th century when you didn't necessarily have the computers that linked all this observations together. You didn't have the equipment on the radiosondes that they launch up with the balloons to communicate back towards the surface. You actually had to rely on finding the individual observations once the balloons fell back down towards the ground. And this study from Bjerknes and Palmin in 1937 was one of the first efforts to coordinate balloon launches in the published literature. And they called these swarm ascents, where basically these balloons were launched in a swarm vertically at coordinated times. And based off this, they were able to construct distributions of temperature and wind speed throughout the atmosphere that started to give us a sense of these localized wind speed maxima that resided high above the surface. Another sort of key aspect of our historical evolution that allowed for the discovery of the jet stream was the influence of the Second World War. So between World War I and World War II, aircraft became way more important in terms of how the war was fought for World War II. And so as a result, forecasts had to be more reliable for aviation operations within the atmosphere. And so that required observations we didn't necessarily need before for a lot of these types of military operations. And independently, a lot of the different actors in World War II were making their own observations of the jet stream. For the US, it's a couple of weather officers that were flying across portions of the Western North Pacific, where the strongest jet stream winds are observed anywhere on the planet. And they noticed as the pilots were flying west towards the East Asian continent, that their sort of ground motion speeds were substantially slower than what they were expecting because of the strong headwinds they were facing towards the Asian continent, which didn't necessarily allow them to reach their bombing targets. And based off of those observations and their knowledge of how the jet stream, acts dynamically, they were able to place this feature within the atmosphere. Independently, there's text all across the scientific literature that highlights the identification of a similar feature from the German forecasters during World War II. They had a phrase in German. I'm not going to try to say it because I know I would absolutely butcher this, but it translates to jet flow, very similar to our knowledge of the jet stream. In Japan, Wasaburo Oishi also documented these large climatological wind speeds prior to World War II through balloon launches over in that location. But it wasn't until after World War II where Rossby, one of the primary actors in our field, was the first to refer to this phenomena as the jet stream and link it as one of these hemispheric features that's just endemic to our knowledge of atmospheric science these days. What I do want to highlight is, what's unique to atmospheric sciences, maybe compared to other fields you might say, is our field is rather young. We didn't know about the hemispheric nature of the jet stream that we take for granted until 75 years ago, effectively. And it's really exciting to be sort of in a field where a lot of this stuff is relatively new knowledge that we're trying to put together. All right. So what does the jet stream look like on a weather map at any particular time? So this is a view looking down towards the North Pole. You can imagine a camera looking down directly on the North Pole. The outer edges of this diagram correspond approximately to the equator, and the North Pole is right at the center where I have NP labeled. And then the red dot basically just represents where Colorado is, so you can help orient yourself. So right down, if you can see my cursor on the bottom part of this diagram, this is where North America is located. Here's the Pacific Ocean. Here's the North Atlantic. And what I want you to take note is if you look at the colors on this diagram, that's corresponding to the strength of the wind speed. So where you see the yellows and reds, that's where you have really fast wind speeds within the atmosphere. And I want you to notice that the jet stream doesn't necessarily make a perfect circle. It meanders just like the rivers from my title slide. And there's localized pockets where the winds speed up and slow down. It's not this continuously rapidly moving feature within the atmosphere that's, the same anywhere on the globe if you're, at a certain latitude. What allows the jet stream to impact the weather at the surface are these areas of asymmetry within the flow. So wherever the jet stream features some degree of curvature to it, that's where the flow is feeling an acceleration. So just anytime you go on a car ride and you make a really sharp turn, or you're driving in a mountain canyon and you feel that sort of acceleration or force that tries to push you to the outside of your car, The atmospheric flow feels an acceleration similarly when it goes around these areas of curvature. Similarly, where the flow is speeding up or slowing down into one of these areas, it's also feeling an acceleration. And as I'll talk about in a second, it's these areas of acceleration where interesting weather can happen. So where the flow curves, where the flow speeds up and slows down. One of the other key aspects of the jet stream is that it's related, or sort of here, this is just a sense to highlight sort of these different pockets of faster moving wind speeds. Now, directly beneath these sort of localized wind speed maxima, what we're going to look at now is the same map, same projection, but we're looking at temperature within the lowest kilometer of the atmosphere. Notice that roughly every one of these white lines, which corresponds to where the jet stream winds are maximized, is in a spot where the temperature changes very dramatically over a short distance as you move from the outside to the inside of the diagram. And that's one of the key sort of observations that we know about the jet stream, is that if you have, let's say, a strong temperature contrast in the atmosphere, say an atmospheric front, like a cold front or a warm front, there has to be a jet streak that overlays the position of that particular feature. And so oftentimes these jet streams are areas where atmospheric fronts are located. So in order to understand how sort of the sort of accelerations in the jet impact the development of sensible weather, I want you to think about an analogy of one of these moving walkways at an airport. You can think about these moving walkways as areas where you have an entrance region where you try to step onto the moving walkway, and an area where the flow slows down, or where you're stepping into the exit of this moving walkway type region. So you can think of the entrance as where the flow is accelerating, and the exit is where the flow is decelerating, or where you on this walkway are speeding up or slowing down compared to where you were previously. Now, when you think about these entrance and exit regions, these are areas when you're in an airport where there potential to generate clumsiness. So you think extra carefully about how you step onto these moving walkways so that you don't just, completely fall over your carry-on luggage and make a fool of yourself in the middle of the airport. And similarly in the atmosphere, it's going to be these same locations where the flow is speeding up or slowing down, where there's an important area for there to be the generation of weather. So on this particular diagram, these concentric ovals just represent wind speeds. So you can think of the air moving in from left to right. As it moves from the white shading to the darker purple, it speeds up. And where it moves from the sort of dark purple back to the white in the exit region, it slows down. And so these yellow arrows here just help to indicate the strength and the direction of the wind and capture that speeding up and slowing down. It's these entrance and exit regions that matter to the generation of weather. So I won't go into the details because it's a little bit more complicated than we have time for here. But generally within these areas of acceleration in the atmosphere, we see that on the south side of the jet in the northern hemisphere, the air tends to rise, as well as on the north side of the jet in its exit region. And it's going to be these areas of rising air where there's the potential for cloud development, for precipitation, and the development of weather at the surface. So oftentimes we look for these connections between where these areas in the flow are speeding up and slowing down, and tie those into the potential for developing weather conditions at the surface. So how do jet streams impact the weather? We often see this linked to big East Coast snowstorms or nor'easters, as you might hear. They might be associated with bomb cyclones as well in certain cases, depending on the strength of the jet. And what I'm showing you here is a sort of a map here that shows the low pressure center off the East Coast for a winter storm in 2016. The black contours are sea level pressure. So the low represents a minimum in pressure associated with that system. And then the shading represents these jet streaks that we were talking about before. So the flow is speeding up into this jet streak off the coast of Florida, and then it slows down. Notice how the low is in the exit region on the north side of this jet, favorable for upward motion and precipitation. And it's in the entrance region of this jet as it moves off the coast of the US towards the North Atlantic Ocean. And so ultimately, this low is in a spot where the rising motion from the jet stream to the north overlaps with the rising motion of the jet stream to the south to create a favorable environment for clouds and precipitation that you often associate with low pressure systems at the surface. We also look for the jet stream when we're trying to diagnose severe weather outbreaks. The key reason, very simplistic, it's way more complicated than this if you watched Paul Markowski's talk yesterday. But at a very most basic sense, we need some change in wind speed with altitude. We need the wind to speed up and change its direction with altitude, often to support severe weather. And so the imposition of a jet streak aloft is one way to produce this increase in wind speeds as you move higher up in the atmosphere. And that wind shear is important because it tilts the updrafts within thunderstorms so that the downdraft, where you're precipitating within a thunderstorm, is not choking off the inflow of warm and moist air into the thunderstorm, promoting longer longevity when it comes to these thunderstorms and the promotion of potentially bad severe weather. And then finally, jet streams are really important for aviation turbulence. We try to understand how these jet streaks are located so that we can avoid them within airplanes. The strong changes in wind speed over short distances can create the clear air turbulence you sometimes experience on an airplane. So knowing the position of the jet stream ahead of a flight can usually give you a good sense of whether or not you might be experiencing turbulence at certain times during the flight itself. And also, it's really important for aviation commercial airliners to be able to fly their airplanes either to take advantage of tailwinds going from west to east, or to avoid those headwinds as you're coming from sort of east to west. It's the reason why if you're flying back from Europe towards the US, for example, you take a really circuitous route sometimes that goes all the way over Greenland and back in towards the US, and not necessarily as direct of a straight line distance as you might on the flight out to Europe from the US. So the last things I'll mention is when it comes to the research our group is doing, we're trying to understand what happens when two separate branches of the jet stream merge. Shown here are a couple of sort of sequential images as you go from A to B to C of two branches of the jet stream, as indicated by the dashed lines here, merging and then subsequently producing a low pressure system off the East Coast here. What we find is that when these jet stream branches merge, the wind speeds tend to accelerate, which then produce a much more robust environment for high impact weather to occur than if you didn't necessarily have those jet streams merged. And what we find, and this is some work from one of my grad students in our group here at CU, is that when you do have that merger, wherever you see the green shading here is an increased likelihood for extreme wind events. So winds that rank in the top few percentiles relative to a long-term climatology. So think of this as, an event you might see 5 out of every, 100 times you get a surface low pressure system to develop. Do you expect either extreme precipitation or extreme winds? And we're trying to understand, how this changes potentially when we look at future climate projections. There's reason to expect that with a warmer, moisture environment in the future, that there may be more robust responses of these jet streak dynamics than we currently see in the present day. So I'll stop there and use whatever time is left to take any questions.
Thanks, Andrew. Really basic question from Rick. Just can you define an atmospheric front?
Yeah, so anytime we're defining an atmospheric front, and that's a great question, you can think of that as an area in the atmosphere where the temperature changes very quickly over a very short distance. So think of a scenario when you've been outside, temperatures are really warm and humid, and then a front moves through and the temperature drops off rather quickly. And usually those fronts are accompanied by precipitation in those types of scenarios.
Great, thanks. And we have another question from Anna. that's really about the Southern Hemisphere, and so how the Southern and Northern Hemisphere compare.
Yeah, great question, Anna. So the jet streams in the Southern Hemisphere tend to have a little bit less waviness to them compared to what we see in the Northern Hemisphere. And part of the reason for that is there's less land to interrupt the flow in the Southern Hemisphere compared to the Northern Hemisphere. But we still can see these same types of dynamics operate. But one of the key things is that everything in the Southern Hemisphere reverses a little bit. So before I showed this sort of diagram of where the upward and downward motion lies with respect to these sort of jet streaks in the atmosphere, the areas of rising and sinking air are actually reversed in the Southern Hemisphere compared to where they are in this diagram. And that basically just has to do with the dynamics that apply that are different between the Northern and the Southern Hemisphere. But otherwise, all the other interpretations are exactly applicable and can occur down there too.
Great. Thanks, Andrew. Well, I'm showing we still have 1 minute. So if I can ask a question.
Yeah.
There's been a lot of talk about sort of the jet getting wavier as a result of, the decreased temperature gradient between the poles and the equator. I wonder if, this seems like an area where there's really not a lot of consensus in the climate science community about whether that's happening or what the impacts of that are. I wonder if you could sort of speak to that debate maybe in its relationship to your research.
Yeah. So it's a really great question and one that's still highly open in terms of how the jet responds. I think some of the perspective there in terms of sort of how the jet may be, wavier or lack thereof. I think what's really important is that if we go back to that diagram I showed you from that North Pole down looking view, there's a lot of wavy character to the jet. It's not this uniform sort of circle that goes around the globe. And so there's going to be a lot of regional differences, I think, in terms of areas that might be more susceptible to a wavier jet, areas that might not be as susceptible. I think some of the evidence that we've seen is that if you treat sort of different branches of the jet separately, there is an argument for those independent branches of the jet to become wavier. And if so, in the context of these merging jets, we think it may make that occurrence more likely in a future climate and might provide a pathway for more common jet mergers in the future compared to what we're seeing in the current day because of that propensity for those jets to be a little bit wavier than their current perspective. But I think there are some legs to that argument of wavier jets when you consider sort of the branches as their own independent entities.
Great. Thanks, Andrew.
Yeah. Thanks so much, Nick.
Okay. We're going to move on. For those who are just joining us, we're at hour 27 of the Weather and Climate live stream. So we've got, I guess now 72 and a half hours to go. I'm Nick Seiler. I'm a professor at Oregon State University. I'll be your host for this segment and for the next hour and a half. Before we get started, I just want to remind everyone that our speakers are appearing in their own personal capacities, expressing their own views, so they're not representing the institutions they work for. That said, we're all here with a purpose, and that's to remind the public and ultimately our representatives in Congress why weather and climate science is important and why it's important to continue funding at the federal level. And the main reason it's important is that good weather and climate forecasts benefit everyone. And the US has long been at the forefront of the science that underlies these forecasts. We developed the first computerized weather forecast for our country. I wasn't involved in that. We developed first computer models to simulate, impacts of carbon dioxide and other human emissions, developed a huge network of observations that go into our weather forecast models. And this excellence is really because of investment by US taxpayers through acts of Congress. It's long had bipartisan support for the obvious reason that it has huge economic benefits, right? Federal Reserve estimates that government-supported research from the NSF and from other federal agencies has had a return on investment of something like 150 to 300%, which means that for every dollar we've invested as taxpayers, we've gotten back between $1.50 and $3. And that number is probably even higher for weather and climate research. But now funding cuts are threatening to really kneecap weather and climate science in the US. And some of these cuts have already happened through executive order. You've all heard probably about the staff reductions at the National Weather Service that have left some weather stations short-staffed. But ultimately, it's Congress that controls the power of the purse, and Congress hasn't really weighed in yet on the president's budget request. So this is where you can really have an impact and have your voice heard. There's a banner at the bottom of the screen, wclivestream.com/act. That will take you to a website where you can just enter in your zip code and find resources for contacting your senators and your representative in Congress. Okay, so with that, we're going to move on to our next speaker, who is actually the host immediately before me, Richard Rood. Who'll be speaking about scenario planning for climate adaptation. So Richard, take it away.
Thank you. I'm delighted to speak at this event on the importance of weather and climate forecasting. I have worked in both weather science and climate science, especially in modeling and data assimilation. In my most recent years, however, I've worked on how can we better use the knowledge that we have from climate science and planning for global warming and its impacts. How do we become more resilient? How do we adapt? If we look at our history, we can find many examples when societies were challenged by variability in the climate. Sometimes they benefited. We more often document changes in temperature and precipitation that disrupt agriculture, the food supply, and contribute to civil instability. In the book, The Climate of Rebellion in the Early Modern Ottoman Empire, historian Sam White documents periods of drought and failures of grain crops. He discusses civil insurrection and the government's inability to address food supply challenges. A common response was to invade and take more land, a move that increased the number of people to feed. Then crop failure in the new lands would exacerbate the problem. We see similar challenges to the Anasazi civilization in what is now the Southwest U.S. and in the long history of the Roman Empire. Climate variability causes disruptions, which increases stress. This contributes to environmental security, food security, and national security. There are changes in social stability. Empires might collapse. Climate contributes to this instability and potential collapse. Note I said contributed, not caused. In the past, all these people could do was to see what was happening and respond. They did not know the geographical extent. They did not know why. Imagine the benefit people and governments would have had if they had a weather forecast, an El Nino forecast, or knew that the next 30, 60, or 100 years would be warming. What weather and climate science have given us is the clearest vision that we have ever had of an important part of our future. We know it has warmed, and we know why. We know it will continue to warm, and what is required to intervene and manage that warming. We know the warming will be disruptive. The rate of change and the magnitude of change is far greater than that experienced by the Ottomans, the Anasazi, and the Romans. It is the fastest and largest change since the end of the last ice age, a time when climate changed perhaps for the benefit of humans. The disruptions we are experiencing are large, and they will get larger. This is frightening. But we basically know what to expect. It will get warmer. We have a certain degree of smartness. We have knowledge that if we choose to use, we can plan. This is historically unique knowledge, which in fact can be used to make things less frightening. We can take some control. We can empower ourselves as individuals and communities. In this talk, I'm going to provide a human language approach to think about our future climate. This is to complement the model simulations to increase their usability. Though climate science can tell us with near certainty that Earth will warm, when we consider making decisions for ourselves and our communities, the uncertainty we face is complex and difficult to manage. That is likely to always be the case. We cannot wait years and decades for better simulations. The Earth is just simply warming too fast. We must make decisions now. I will present a human language way to think about the future. It starts with the average temperature of the planet will be rising. We will be accumulating heat. Heat will be permeating the Earth, largely through what is stored in the ocean. The physical climate and the biological responses will follow from the temperature increase. To set the stage, this is a figure of temperature change plotted as a difference from a 1951 to 1980 average. This difference is called an anomaly. Spend a moment with the image and understand its shape. I will be presenting other versions of the figure highlighting different points. This figure includes analysis of the observations by 5 independent organizations. It is from 1880 to the end of 2019. This was from a joint presentation by NASA and NOAA at the end of the teens decade, highlighting that it had been the warmest decade. The coming decade, the 20s, will be warmer still. I expect the 30s and the 40s also will be warmer still. I put a large arrow at 1980 to show the time when the upward increase in temperature became large enough that it is easily visible. From the earliest time reported here, 1880, there's been about a 1.5 degrees C increase. This is an important number policy-wise, so place it in your memory bank. To help us organize the storyline, I will start a trail map. What we know is that the Earth is warming. It is directional upwards. That is what we know best. The question is, what next? The answer is, it depends. It is conditional. The two conditions are if water is available to the weather systems that influence a locale, and if it is above or below freezing. The next figure has a lot going on, but it's just a schematic summary of the usual story we hear about climate change. I have imagined the Earth as a machine. We are interested in how that machine responds to warming. I've included the feedbacks. We know the Earth responds to warming by warming some more. And that warming has a whole set of consequences. Ice is melting, sea level is rising, and there is more evaporation from the surface. This leads to more extreme precipitation and more variability. Depending on the availability of water, we get to a situation where we expect more flood and more drought. Storms change as they move around the accumulating heat. Finally, temperature is one of the key factors in biological activity, which leads to changes in carbon dioxide, methane, water, and oxygen, as well as nitrogen and phosphorus cycles. As we move into the future with more warming, all of these things will continue along these trajectories. At this moment, we have experienced about 1.5 degrees C average warming. Heat is permeating the climate, largely through the warmer ocean. I ask you to consider, at 1.5 degrees warming, have the changes we have experienced been important, large, consequential? Have they been dangerous? Have you noticed them? Though this basketful of consequences of global warming might be motivating, it is not, in fact, very usable information. We must unpack this information and bring it to people at a local level to be usable. I now use the same type of temperature figure I used above to look into the future. This plot was made in 2007. This type of plot is regularly remade and updated. This is one of the simpler ones and good for orientation. The basic story of these plots is remarkably consistent over one 5-year time span to the next. There are modeling systems from many countries in this figure, and each modeling system is used to provide, in some cases, hundreds of simulations. The solid line is an average of this ensemble of simulations. There are different scenarios of future emissions. They are represented by different colors and abbreviations. For my purpose, they are low purple, medium green, and high red. Currently, our emissions are far closer to the red scenario than the others. The shading around the solid lines is the spread of model simulations, a measure of model uncertainty. I point out two things. First, in 2100, there are three scenarios that show a 1.8, 2.8, and 3.6 degrees C increase over the late 20th century average used in this plot. In all of these scenarios, 2100 is not the end of the game. The temperatures are still rising. The second thing I point out is that the scenarios mostly overlap in the first 30 years. That is, it takes about 30 years before we see any differences. It takes more than about 50 years to be able to say a scenario is, in fact, working. Excuse me. This gap between a policy action and climate outcome is a major challenge to getting policy to reduce emissions. It's very easy to look at this figure and argue nothing happens for 30 years, so we can wait 30 years to do anything. This argument is flawed and perhaps motivated reasoning. This is the 2021 version of the same graph. It is more complicated and complete. The top left panel is temperature change, the same as before, except that the anomalies are calculated relative to 1995 to 2014. The top right is global precipitation change. You see the far greater uncertainty in the spread of projections. The bottom left is Arctic sea ice area, and the bottom right, global sea level rise. The scenarios our decisions make about decision. The scenarios our decisions about emissions make a difference. However, even in the most aggressive emission reductions, we see vast reductions of sea ice and continuing rise of sea level. This is a cumulative effect. No matter what, our environment will be quite different in the future. We will be forced to adapt to the changes. In the temperature plot, the axis on the right are changes relative to 1850 to 1900. The two lowest scenarios are based on what we have to do to get us to stabilize at 1.5 degrees or 2 degrees C. Either of these scenarios require us effectively to eliminate fossil fuel emissions in the upcoming decades and then to remove some carbon dioxide from the atmosphere. The other scenarios go from about 2.5 to 5.5 degrees C and might be considered more likely scenarios given our current behavior. They're quite consistent with the 2007 version of the figure presented earlier. But I just want to focus on some characteristics of the temperature curve. For a given scenario of change, the curves are quite well behaved. They don't bounce around a lot. Since temperature is one measure of energy, they suggest the accumulation of heat in the environment. What we might consider the more realistic scenarios based on our current behavior all show warming continuing for decades. An important point for thinking about stories of our future for planning is that there are both cumulative effects and what I will call acute or instantaneous effects, weather. Weather is the way we feel the climate. We often spend a lot of our time talking about more severe storms in a warming climate, but storms change in many ways, and most certainly that when there is water, they will be wetter. But storms are only the disaster and the disaster recovery part of climate change. The cumulative effects are changing the environment with physical, biological, and chemical consequences. Next, I focus on the precipitation projections. They are more difficult to characterize because they're more complex. Though there is some general moistening due to increased evaporation, some of the simulations show the potential for less precipitation. Some of the scenarios stop their increase and level off as the climate gets warmer. There's far more spread in what we might expect to realize. We still have cumulus we still have cumulative and instantaneous effects, and the effects of water availability depend not only on precipitation, but evaporation. And evaporation increases as temperature increases. Today, in most places, sometimes it is wet and sometimes it is dry. We expect this behavior to continue into the future. But the additional heat will amplify both the wet and dry times. We need to be on the lookout for changes that lead to evaporation winning over precipitation. I will return to walking our way down the path with the answer to how does the weather change in a warming climate is that it depends. Most importantly, it depends on if water is available. Another important condition is whether we are above, below, or near the freezing point. Here I will focus on is water available? How wet is the surface? Earth's surface is mostly water. In a global sense, there is abundant water available for the atmosphere. On land, in most cases, there's some water at the surface. In all cases, if temperature increases, then evaporation will increase. There is also the potential for water to be a larger percentage of the composition of air. Whether there is more water available in the air depends on how much is available to evaporate. Globally, because of the abundance of water, as the atmosphere warms, we expect and observe an increase of water vapor in the atmosphere. We expect and observe an increase in precipitation. Locally, what happens depends on the availability of water at the surface, or as is often the case, where do the weather features important to a locality get their water? The answer is often the ocean. I now revisit this figure. So far, the climate change we have experienced is in response to 1.5 degrees C warming. We're not even at equilibrium with this increase in temperature. The environment is still changing. I think that these changes are significant. In fact, I argue that we have both underestimated the speed of emergence and their magnitude of warming-related changes. I'll leave it to you to consider the consequences of 2, 2.5, 3.5, or 5.5 degrees warming. Science-informed storylines provide a way to complement science-based knowledge and simulations to make that information more usable to more people. Here are some basic rules that are useful for communication analysis. The rule of complexity. There is no one thing that climate change will do. Variability will increase. New behavior will emerge. The rule of change. We are in a time of change, non-stationarity. What is right for 30 years, which is a very good planning time frame, might not be right for 60 years. The new normal is that things are changing. What I call the rule of continuity. We have a variety of behaviors today, drought and flood, the characteristics of storms. This will continue to be true. There are more rules that require too much time to detail. They include there are cumulative and instantaneous effects of a warming climate, and both are important for planning. You cannot separate the surface, the landscape, from the changing climate. In climate change is always greatest at the edges. For example, the seasons, the edge between land and ocean, the edge between desert and non-desert. In conclusion, if you develop a set of science-informed, plausible scenarios then you can increase the usability of climate science by individuals and communities. These stories are informed by observations, simulations, vulnerabilities, the problem you are trying to address, expert guidance, and synthesis. In this framing, Model simulations provide a fuzzy map of unexplored trails into the future. This is valuable knowledge unique to our times. It would have been amazing if our historical civilizations had known as much as we do. It gives us a fantastic opportunity to take control of a situation and make good decisions. Thank you for listening.
All right, thanks, Ricky. Look in the chat. Okay, I'll ask a question, sort of a big picture question here. You've shown a lot of plots that have these different emission scenarios, or socioeconomic pathways, I guess we call them. You know, but even within those, right, there's sort of envelopes of uncertainty. So obviously, a lot of the differences in temperature and precipitation are driven by differences in what happens in terms of human action and emissions. But could you maybe elaborate a little bit on these kind of clouds of uncertainty, even for a single emission scenario, and maybe more specifically, how kind of policymakers kind of account for that sort of uncertainty when thinking about adaptation in particular?
Yeah, so obviously these things have been named and renamed over the years, and they have various levels of complexity. They are, of course, far more uncertain than things based on physical climate because, they can change fairly instantly depending upon, an invasion or something like that. So for this talk, I'll say there's an important distinction to be made between adaptation and when we think about the mitigation problem. And one of them is that adaptation is something that, one, we need better information for, but it is usually done on 10, 30, or 50-year time spans. And from an emission scenario point of view, if you look at this figure, they don't diverge much on that. So if you're doing adaptation, when a lot of people frequently first ask what's the right scenario to decide, it doesn't really matter that much for the adaptation problem. And so that's, one of the many ways. Within my organization, GLISA, we've actually written a rather large document on the different approaches to emission scenarios and how to think about them in resilience and adaptation planning. But that would be my first thing with regard to adaptation. It doesn't matter that much.
Great, thanks. Okay, we have several questions in the chat here. I guess this question from Isabel about sort of changes, happening between now and 2050, and then sort of beyond that. I wonder if you could speak to that a little bit. I guess this sort of speaks to the question about sort of, uncertainty from emission scenario not really mattering in the near term, but mattering a lot more in the longer term.
That's how, so it matters a whole lot in the long term of whether we maintain an environment that is perhaps adaptable to. And at some level, we're always adaptable, and it's how we respond in society and how we deal with the disruptions that will matter the most. But how will climate change accelerate into 2050? I think one of the things that in the adaptation work we've been doing is that we have been underestimating how rapidly the freezing line is changing, and how rapidly we're seeing basic changes in, say, a Great Lakes area, which I've studied the most, in lake ice. And when that happens, it's a nonlinear response in lake effect precipitation. It's a change in the snow, ice, water, liquid water balance. We just finished a paper documenting trends in freezing rain, which can also be billion-dollar efforts. So that would be one of the biggest issues. But I think in general, we have underestimated these sort of critical points, these transition points, partly because our models treat them a bit incrementally.
Thanks. That speaks to another question from you, talking about sort of the reversibility of permafrost. But I think there are a number of components of the climate system, right, that might experience irreversibility or hysteresis.
Oh, absolutely.
I wonder if you could speak a bit to that. The question from you. Yeah, there we go. Thanks.
I thought when you said you that I was asking the question. It's okay. So, I think one of the tipping points, and I would say that we need far more study of tipping points, and we need models especially designed to study tipping points in geoengineering at this point. I don't think we can rely on CMEP type models for all of our knowledge here. So this is one of the places where I see that the accumulation of heat rather than what's the temperature is an important point, because this heat, you can look in the areas of permafrost and you can see it propagating down into the ground. And even if we immediately started cooling, that heat is still there. It's still propagating. In West Antarctica, you're seeing it in the ocean. In Greenland, you're seeing the ocean eroding the ice sheets from below. So there's a lot of complex fluid dynamics in a system that has a lot of potential critical points or tipping points. And I would say, is there a way to reverse it if the permafrost starts to melt? You're getting into geoengineering and intervention, which I think is alarmingly risky. Okay.
Thanks, Ricky. I think that's all the time we have for your segment. Appreciate it. Okay, for those who are just joining us, we're at hour 28 of the Weather and Climate live stream. We've got 72 hours to go. I'm Nick Seiler. I'm a professor at Oregon State University. I'll be your host for the next hour. Before we get started, I just want to remind everyone that our speakers are appearing in their personal capacities, expressing their own views. They're not representing the institutions that they work for, and their views may also differ from those of other participants in the live stream. That said, we're all here with a purpose, and that's to remind the public and ultimately our representatives in Congress why weather and climate science is important, and why it's important to keep funding it at the federal level. And the main reason it's important is just that good weather and climate forecasts benefit everybody. U.S. scientists have long been at the forefront of the science underlying these forecasts. U.S. scientists developed the first computerized weather forecast, the first models for simulating the impacts of carbon dioxide and other human emissions on the climate. We've developed a huge network of observations, weather stations, satellites, etc., all of which go into these weather forecasts. And this excellence is really because of investment by us, the U.S. taxpayers, through acts of Congress. And this investment has really always had bipartisan support for the very obvious reason that it has huge economic benefits. The Federal Reserve estimates that government-supported research from the National Science Foundation and other government agencies has had a return on investment of something like 150 to 300%, meaning for every dollar we as taxpayers have invested, we've gotten back between $1.50 and $3. And for weather and climate research, I would argue that number is probably a lot higher. Now, as many of you have likely heard, funding cuts are threatening to really kneecap our field, weather and climate science more broadly within the U.S. And some of these results, or some of these cuts have happened already through executive order. Many of you, I'm sure, have heard about the staff reductions at the National Weather Service, for example. But ultimately, it's Congress who has the power of the purse in the U.S. And Congress really hasn't weighed in yet on the president's budget request. So this is really where you all come in. There's a banner at the bottom of the screen with a website, wclivestream.com/act. If you go to that website, that will take you to another website where you can put in your zip code and then find resources to connect with your representative in Congress and your senators. Okay. With that, I think we're ready to move on to our next speaker, who is, drum roll please, Roger Creel. Thank you. Who'll be speaking to us about sort of understanding modern sea level rise through the lens of Earth's history. So go ahead, Roger.
Awesome. Can you hear me okay?
Yes.
All right. So I have some graphics in my PowerPoint, so I'm going to try sharing my screen. And if this doesn't work, there's a backup.
We're good.
We're good. Allow later. Okay. Oh, share window. This.
I was seeing your title slide correctly, I think.
Okay. Wouldn't be online if we didn't have some issues. Okay, I've enabled permissions. Could we try using the slides that I've uploaded? Is that amazing? Okay. Can everyone see okay? Great. Okay, so I am a scientist. My current affiliation is at the Woodsole Oceanographic Institution, but I'm speaking on not on behalf of my institution, but as a citizen. And the title of my talk is Past is Prologue, Seeing Modern Sea Level Rise Through the Lens of Earth History. So I study sea level change, and it should be no surprise to tell you that global mean sea level is rising. So here we're looking at a figure with time moving from 1950 on the x-axis to the present in black, and then projecting into the future with these rainbow-colored lines. On the y-axis, we have global mean sea level, and the big takeaway is that the lines are pointing upwards. No matter what projection we use for sea level over the next century, projection for global emissions, that's these different SSP scenarios, selective socioeconomic pathway, global mean sea level is projected to rise. And we've had humans observing sea level for the last several hundred years. So we know in the historical period, global mean sea level has been rising. But you might wonder, how does this compare to the past? Because none of us have a crystal ball. And one of the best ways that we have of looking into what the future may look like is to gaze into the geologic past and find times that can give us perspective on the future. So here's your first bit of perspective. Comparing modern rates of global mean sea level rise to the past 2,000 years. This is a paper that came out several years ago. And the big takeaway is over the last 2,000 years, rates in millimeters per year of global mean sea level rise have fluctuated somewhat, but are much lower than rates of global mean sea level rise over the last century plus. But Earth history is a lot longer than 2,000 years. So let's zoom a little bit further even into the past and say, how does today's global mean sea level rise compare to the last 12,000 years? And in conversion to PowerPoint, we lost the uncertainty bars on the future projections, but you can see the main lines here are telling this the same story, which is that over the last 4, 5, 6,000 years, global mean sea level, as represented with a rate of change, has been lower than we've seen. And as you get back further into the past, we start to see rates of change that are similar to what we're projecting sea level rise may look like over the next century. But Earth history is longer than 12,000 years, and over the last 5 million years, we're now looking at a diagram of what an estimate for global mean sea level looks like, and high on this plot is high sea level, low is low sea level, and the exact amount for this presentation is less important than the fact there is significant variability over 100,000 year time periods, over longer time periods. But Earth looked very different from now in during much of the time period represented by this plot. And so looking back into the past to compare to these what we call glacial periods when ice sheets were big is not as helpful as comparing to the warm periods. So 21,000 years ago, this is one representation of what the Northern Hemisphere looked like. We had ice sheets covering Canada, Greenland, parts of Alaska, Scandinavia, parts of Russia. And this was a GIF with the Ice Age squirrel jumping up and down, because I think a lot of people are most familiar with ice sheets covering continents from Pixar movies, which have some resemblance to reality and some fictions. But I think ice ages are in the public imagination, and they're very different from now. So here again, thinking like what would it be like to live in a time period with ice sheets? This is not entirely realistic, but to give you a sense for how different the world looked like, this is how close an ice sheet would have been to Manhattan. And Manhattan wasn't the only place that was either covered by ice or nearly covered by ice. Boston, covered by more than 1,200 meters of ice. Montreal by 3 kilometers. Chicago by almost 1 kilometer. So ice age is maybe not our best tool to think about this current hothouse that we're in and what the future may look like. And instead, it maybe behooves us to think more about the warm periods in Earth history. So these are the redder tops of this jagged curve. And in those warm periods, there are certain key time periods that sea level and climate scientists think of as being some of our most helpful analogs for the future. So no time in Earth's past is completely like the present or like the future, but there are time periods that are similar enough that we maybe can get useful information from these time periods. And the two time periods that we're looking at here are the mid-Holocene and the last interglacial. So both of these we call interglacial periods. So the Holocene is the last 12,000 years. The last interglacial is the previous interglacial before the Holocene, and that's 130 to 115,000 years ago. And in both of these time periods, but particularly the last interglacial, sea level, global mean sea level was higher than present. So as we're looking towards 2100, when sea level projections in most scenarios are not more than about a meter, the last interglacial is higher than that. But as we look towards 300, when high-end projections are pushing higher than 10 meters of sea level, that starts to have us look more like the last interglacial. And so the question is, I'm telling you things about past sea level, but how do we know about past sea level? Humans were arguably around, well, definitely around for the Holocene, and to some extent around for the last interglacial, but we didn't have tide gauges out. So there are, depending on how deep into the past you want to look, there are different tools that we have. So on the left-hand side of the screen, we're looking at biological ecosystems that have, in the modern environment, a defined relationship to local sea level. So salt marshes grow in relation to mean sea level. Some parts of a salt marsh are higher than mean sea level. There are some places where sediment is accumulating that are below mean sea level. So we can go to a salt marsh now and analyze the chemistry of the salt marsh, look at the creatures living in the salt marsh, and understand the relationship between those creatures and that chemistry and sea level, and then go to older salt marshes and say, okay, how relative to present day sea level, how high is this bit of the salt marsh that we're looking at, and use that relationship to figure out where was sea level relative to present. And we can do a similar thing with coral reefs, particularly these itsy bitsy coral reefs called coral microatolls. Those sorts of indicators have several sources of uncertainty. So in a salt marsh environment where you have a tidal range, the tides are going up by a couple meters up and down every day. That increases the uncertainty of your estimates. So for time periods closer to the present, we use, where we have them, tide gauge records, or for the last several decades, we have satellites that are measuring the local sea level. So data gets better as you go closer to present, but there's still information that we can extract from the natural world before humans started looking that can help us get to sea level. But especially for an audience as diverse as this one is, I think it's important to underscore that local sea level, the sea level that somebody standing on the coast experiences, is not the same as global mean sea level. So sea level is not a bathtub. In fact, sea level is very much not a bathtub. For instance, looking at the United States, here arrows are pointing, are showing what the present day rate of local sea level change is. This is from NASA, the sort of product that NASA can put out with sufficient funding. And the thing to take away here is that there are some places where the arrows are pointing up. Parts of the US East Coast, sea levels rising by 3 millimeters a year. That compares to global mean sea level rising by about 3.4 millimeters per year right now. But there are some places, like in Alaska, where local sea level is actually falling. And I will explain why this is happening. I won't explain all of why it's happening because sea level is complicated, but the thing to take away is that there are many processes on Earth that shift local sea level even as global average sea level is rising. So let's talk about some of these processes to give you a mental model for how sea level changes on different timescales. So on fast timescales, earthquakes, you can expect local sea level to change by a meter per minute. A little bit longer timescales, sea level can change by a meter per hour as you get a storm surge. Zoom out a little bit farther, and river discharge leads local sea level near coastlines to increase by as much as a meter per day. If you get a big slug of fresh water coming down a river, it gets trapped against the coast, and that can increase or decrease sea level by about a meter per day. Zooming out a little bit farther, and coastal subsidence. This is coastal subsidence from oil and natural gas extraction, from groundwater withdrawal, from in Arctic landscapes, permafrost subsidence. These are processes that can dramatically change local sea level by dropping the land surface. And this is ballpark a meter per decade in some places. Zoom further out, and we're at ice sheets, and a meter per century of sea level is a thing that can easily happen. And then even farther out, mantle convection can change sea level by a meter per 100,000 years. The process that I spend the most time thinking about, and that is critically important on decade to century timescales, is ice sheets growing and shrinking. So that's what I'm going to give you a little bit more intuition for, because I had a different career before I went to graduate school, and then learned what you're looking at on this slide and thought I need to change my life. So it turns out that just as the Earth has a gravitational field, ice sheets have their own gravitational field, and they're big enough that they actually can attract water towards them as they grow. And this is not a trivial effect. This is actually a pretty substantial effect, tens of meters over a glacial cycle or more of sea level rise because of the gravity of ice sheets as they grow. Ice sheets are also big enough that they sink the Earth. So imagine sitting on the edge of your bed. It's squishy. You sit on it, it sinks. That sinking also displaces material around the edge. So you have a bulge around where you're sitting. And ice sheets behave the same way. So put an ice sheet on Canada, and the continent around that ice sheet lifts up. So New Jersey lifted up because of the ice sheet on Canada. Ice sheets also change Earth's axis of rotation. This is a little bit less intuitive, but grow an ice sheet on a part of Earth that is not exactly on the rotation axis, and the entire Earth axis of rotation shifts to accommodate that change in mass. That also changes sea level. So put these three processes together, and you get what we call glacial isostatic adjustment modeling. That's a lot of words, but what's neat about this is that because ice sheets in different places have different effects on the sea level, we can do what we call sea level fingerprinting. So this is the fingerprint of what happens if enough water melts from the West Antarctic ice sheet to increase global mean sea level by a meter. And the takeaway is, near the ice sheet, the red blob indicates an area where, even though global average sea level increases because you've melted part of an ice sheet, there's less gravity around Antarctica, and Antarctica responds to the deformation of losing this mass. So sea level, if you're standing on Antarctica, actually falls if you melt part of Antarctica, whereas sea level on the US East Coast increases by more than global average sea level because you're far away from the ice sheet. So melt ice from the ice sheet, diminish the gravitational field, and that water has to go somewhere, and where it goes is as far away from the ice sheet as possible. This is a complicated figure, but the thing I want you to take away from it is that processes acting on our planet cause local sea level to change in ways that are different, that cause local sea level to differ from global mean sea level, and these processes are important. So I started off this talk by saying sea level is rising, global mean sea level, but there's a lot that we still need to learn about how and why global mean sea level is rising and how local sea level will differ from global mean sea level. So things that you can do to help, get engaged with your local politics, wherever you are, and whatever your political beliefs are. Talk to your friends and family and network about what you learned today. Ideally, those conversations are friendly because everyone learns more from their friends than their enemies. But we also have a range of conversations, and that's okay. And finally, support funding for sea level research and coastal resiliency. All of us, let's not say 100% of us, but I bet the degrees of freedom between you and somebody you know who lives on the coast is not that far. A lot of us are going to be impacted by what's happening on the coasts, impacted economically, impacted socially, impacted intellectually, and coastal processes matter for everywhere in a nation. So thank you very much. This is a photo from driving home last week. We had a small storm on the US East Coast in Massachusetts, and houses that are built along the coast, even if they're on stilts, started getting flooded. So this is things that people have to deal with right now. So I'll stop talking and thank you very much and open up for questions.
Thanks a lot, Roger. As we're waiting on questions to trickle in, I'll just ask about the last interglacial. That seems, like an interesting point of comparison with the warming that we're projecting, as you've shown. Temperatures were warmer, sea level was higher. I wonder if you could speak a little bit about sort of the reasons we think the Eemian or the last interglacial was warmer than the Holocene. If you could shed some light on that, potentially.
Yeah. Yep. So so much about Earth temperature depends on Earth's relationship to the sun. And that relationship shifts through time. There are three ways that it shifts. There's how much is the North Pole tipped towards the sun. There's how circular or eccentric is the orbit of Earth around the sun. And there's where in Earth's orbit is the North Pole pointing towards the sun. And these three processes have different timescales for cycling, but the elevator pitch for why the last interglacial was warmer is that the northern hemisphere was tipped slightly more towards the sun. Earth was getting more sunlight, more energy from the sun. So even though CO2 levels were nowhere near as high as they are, Earth was warm just because its relationship to the sun was different.
Cool, thanks. One big question of sea level rise, obviously there's a question of kind of how much sea level rise we can expect from a certain amount of warming, but you talked about this sort of uncertainty about the time scale too. And I wonder if, the geologic records, say from the last interglacial or even from, the LGM to the Holocene, if that is, do we have enough information to sort of help us constrain kind of how fast we expect sea level to rise over the next couple of centuries, or is the geologic record just not good enough?
That's an excellent question. We struggle in the deep geologic past to capture exactly how fast rates are, exactly how fast things happened, because the measurements that we have on when things happened have uncertainties. So some of our best ages on sea level come from corals, corals that we date using ratios of uranium and thorium in their skeletons. Those ages have plus or minus hundreds of years. So 100 years is the time scale that a lot of the projections that we're thinking about happen on. So I think it's fair to say that if we take the atmosphere and the world that we have and run it forward in time for 1,000 years, the 1,000 years that that would be within last interglacial kind of time scales, sea level is if nothing changes, sea level is probably going to be at least as high as it was during the last interglacial. I think that's a conservative interpretation of the data. The question is, hitting the Earth with a hammer, how fast does it react?
Right. Exactly.
And we're hitting it with a more energy intensive hammer than the Earth got hit in the last interglacial.
Right. Okay. I'm really tempted to ask one more question, but I think we're at our switching point. But thanks so much, Roger. That was super interesting. Okay, we're gonna move on to the next speaker. But before I get there, I just want to welcome everyone. Again, we're sort of halfway through hour 28 of the Weather and Climate live stream, so 71 and a half hours to go. I'm Nick Seiler. I'm a professor at Oregon State University. I'll be your host for the next half hour. Before we get started, I just want to remind everyone that all of our speakers are appearing in their personal capacities, expressing their own views, so they're not representing the institutions they work for, and their views may differ from those of other participants in the live stream. So that being said, we're all here with a common purpose, and that's to remind the public and ultimately our representatives in Congress why weather and climate science is important and why it's important to keep funding it at the federal level. So the main reason it's important is just that good weather and climate forecasts are beneficial to everyone. And US scientists have long been at the forefront of the science that underlies these forecasts and that continues to improve these forecasts. So, some examples: US developed the first computerized weather forecast. US also developed the first models that simulate the climate impacts of carbon dioxide and other human emissions. In recent decades, we've developed a huge network of observations, weather stations, satellites, planes, balloons, etc. And all of this has been made possible through investments by US taxpayers through acts of Congress. And this investment has long had bipartisan support for the very obvious reason that it just has huge economic benefits. The Federal Reserve estimates that government-supported research from National Science Foundation and other government agencies has had a return on investment of something like 150 to 300%, which means that for every dollar we as taxpayers have invested, we've gotten back between $1.50 and $3. And I would argue for weather and climate research, that number is likely significantly higher. Now, as many of you have likely heard, funding cuts are threatening to really kneecap weather and climate science in the US. Some of these cuts have happened already through executive order. I'm sure you've heard about staff reductions at the National Weather Service, for example, that have left some weather stations short-staffed. But ultimately, in the U.S., it's Congress that has the power of the purse, and Congress really hasn't weighed in yet on the budget request from the administration. And so, this is really where you all come in, and where I think your voices can have a big impact. So there will be soon a banner, I believe, at the bottom of the screen, but even if it doesn't appear, there it is, wclivestream.com/act. If you go to that website, you'll be taken to another link where you can put in your zip code and then find the resources for contacting your senators and your representative in Congress. Okay, so with that, we're going to move on to our next speaker, who is Shawn Wang, and he will be presenting on a very timely topic, megadroughts, and looking specifically at a case study in Southeast Asia. So take it away, Shawn.
Great. Thanks so much, Nick. And thanks to all the organizers of the Weather and Climate Livestream, and to everyone that tuned in. I'm really excited to share my research and just advocate for how important federal funding is for what we do. And so let me real quick, how do I share my, yes. Okay, cool. There are my slides. And so, right, as Nick said, today I'll be talking about megadroughts, or it's the fancy name for extended droughts, with a specific focus on Southeast Asia. And so we can dive right in. A little bit about me first. I am also a scientist at Woods Hole Oceanographic, just like Roger, who just presented and gave a great talk. I recently completed my PhD in climate science, and my research area is focused on studying how the ocean and atmosphere change on these really long time scales of decadal to centennial time scales. And so to provide some initial context for that, the Earth system, the climate system, has variability on all sorts of time scales. It's very rich. Most of us are probably familiar with changes in weather associated with oscillations on hourly to daily to monthly time scales, such as tornadoes, storms, hurricanes. But the climate system also oscillates on these longer time scales. These include the El Nino Southern Oscillation, which is warming in the Pacific on these interannual time scales. We have droughts that can last for decades, such as what's happening right now in the US Southwest. And then most notably, right, what we're experiencing over the last 100 years or so is this climb in global temperatures, this centennial scale change. And so most of what I am interested in is really the right-hand side of this frequency spectrum of looking at these long oscillations. And specifically, like Roger, I'm sort of interested in what happened in the past. And so, like my slide said, my focus for this study is looking at Southeast Asia. And so this map here of the Asian continent helps orient us of where Southeast Asia actually is, which is this black box, and includes countries like Cambodia, Thailand, Indonesia, Philippines, Malaysia. And the color that you have overlaying these countries is how much rainfall they receive every year. So the more blue is the more rainfall. And just for context, I sort of put, I'm currently in Boston, Massachusetts, and that's sort of how much rainfall we receive here in Boston every year, which is around 1,000 millimeters per year. And so anything more blue than that is more rainfall than I see on an annual basis. And you see that Southeast Asia gets a lot of rainfall, sometimes twice as much as what we see here in Massachusetts. And that rainfall is important. It's important not only for the people that live there, but also for agriculture. Southeast Asia, as some of you may know, is a huge producer of rice for not only themselves, but also the globe. They account for like roughly 40% of all the global exports of rice and 26% of all the total production. People have coined Southeast Asia as sort of the global rice bowl. And so if any of you like me enjoy eating jasmine rice, sort of with any meal that you have, then you should care a lot about what's going on in Southeast Asia and the rainfall that it receives. But we have evidence that this rainfall that's really important has actually not been consistent in the past. There seems to be, okay, well, a little formatting issue, but that's all right. Here is a plot, a time series of the last 1,000 years with us in 2025 in the present. And we have overlaying here are various long droughts or mega droughts that have occurred in Southeast Asia, which we know from historical records, from scribes, and also from paleoclimate archives. And let's see, actually, maybe we might be able to switch to the shared screen that I have so there's less of a formatting issue. So yeah, maybe we can do that real quick. Oh. Sorry, okay, yes, we're back. Technical difficulties, but this is great. Yay, no formatting issues. Okay, so like I said, throughout the last 1,000 years or so, Southeast Asia has experienced these long, prolonged droughts that last for sometimes more than a decade that have really affected society. And I've sort of highlighted a few of these with these gray bars over here. And I want to briefly touch on just a few of them. The first are the Angkor droughts that occurred in the 14th and 15th century. And these droughts were so devastating that they actually contributed to the Khmer Empire that was currently living at the time, abandoning their capital city. So this picture in the top left is a picture of Angkor Wat, which is a beautiful set of ruins that are in Siem Reap in present-day Cambodia. And it's a huge, massive sprawl. And it's amazing to believe that the society just abandoned this whole complex and moved somewhere else. But, drought and a lack of rainfall really contributed to that. Another example is the late Ming Dynasty drought that occurred in the 1630s or so. And associated with this drought led to famine widespread famine throughout Asia. And that eventually led to peasant rebellions that also led to the fall of the Ming Dynasty. And so these are two instances of rainfall and climate having a distinct impact on past society and societal unrest. And so it's of interest for me and for many others to try and understand what exactly caused these droughts, these prolonged periods of just a lack of rain. Unfortunately, though, our usual tools of the trade that we have as climate scientists, including satellites, weather balloons, or floats that are used to help sense and observe and take in measurements of the climate system, weren't really present during the 1400s or the 1600s. Most of our data goes back to maybe 1950s or so. Some of them to the early 1900s, but not much beyond that. And so we really have to rely on something else to try and understand how these droughts came to be. And that's where climate models come in. Here is a sort of, I'm going to present a brief overview of climate models and how they work. Very briefly, climate models are just complex computer simulations that try and characterize and simulate all the important processes in the atmosphere and ocean system, including rainfall, snow, winds, heat transfer between different parts of the climate system. And it's sort of solving all these differential equations and sort of making all these computations on individual grid cells that simulate the entire planet. And so they're run on these super large supercomputers that are housed all across the world, many of which are in the US. And they are a valuable tool for climate scientists to understand how Earth is changing now, how it's changing in the future, and how it has changed in the past. And here on the right, I'm providing sort of an example comparison to illustrate how useful a climate model is. So in the top right here, we have the observed average rainfall globally from satellite data that we have. And we see where the more green the values are is the heavier rainfall. So we see across Southeast Asia a heavy band of precipitation, and it extends into the Pacific Ocean. And as we go further toward the poles, we have less rainfall. In the bottom, we have a global rainfall map, not from observations, but from a specific climate model. This is the CESM model, which was developed here in Boulder, Colorado, in the US. And what we see when we look at the two is that, if you squint your eyes, they look pretty much like they're matching each other. They have the heavy rainfall in the equatorial region and less rainfall as you go further to the exotropics. But there are some differences, right? This heavy band of rainfall extends pretty far into the Indian Ocean in the CSM model, and not so much in the observations. You can see some other differences as well. And there's tons of scientists that are doing work to try and look at these model data differences to try and improve the models. So all this to say that climate models are sort of an imperfect but valuable tool to understand aspects of the climate system. And so I'll be using climate models or using output from them in a way that is perhaps non-traditional. Instead of thinking about simulating future climate change, we can actually use climate models to help us understand changes in the past. And so we can actually use data from these paleoclimate archives that we have, including ice cores, tree rings, or fossil corals, to understand certain aspects of the climate system in the past, including how much greenhouse gases there were, when we had big volcanic eruptions, how bright the sun was over the last 1,000 years or so. And we can use that knowledge from these paleoclimate archives and tune the model and sort of set them as input parameters in the model and run this model forward for 1,000 years or so. And that should give us our best estimate or best guess of what global climate looked like over the past 1,000 years. And really, that's sort of the effort that's been undertaken here in this CESM model that I'll be analyzing. And so for this study, I've sort of used the model simulation here and extracted rainfall over Southeast Asia to look at how it's changed over the last 1,000 years. And so very briefly, I'm going to share just two main results and highlights from this study. First off is the role of the ocean in driving these droughts. And so using the climate model, I'm able to look at periods throughout the last 1,000 years that have extended periods of reduced rainfall. And then I've sort of averaged all of those anomalous periods together to produce a map of what that looks like. So this is the rainfall anomalies that are found in the model associated with droughts in Southeast Asia. And if we look at what the ocean sea surface temperature looked like associated with these periods of droughts, we see a very interesting pattern. So what this tells us that when you have droughts in Southeast Asia, you usually have associated sea surface temperatures that are cooler in the Western Pacific and Eastern Indian Ocean, and then warmer in the Eastern Pacific and the Western Indian Ocean. And the reason why this tripole pattern appears in SSTs and why that might be related to rainfall is because of something called the Walker circulation. And so the Walker circulation is an important atmospheric phenomena in the tropics. And it sort of looks something like this, where it brings moisture and winds, and the winds bring moisture to Southeast Asia and to the Western Pacific. And this moisture rises in the atmosphere and it brings the heavy rainfall that Southeast Asia receives. If, for example, though, the sea surface temperatures beneath this atmosphere were to change and the Eastern Pacific were to warm, or the Western Indian Ocean, then through air-sea interactions, these winds actually weaken or can even reverse sometimes. And that can reduce the amount of moisture that gets brought to Southeast Asia. And so really what this illustrates is that the oceans play an important role in governing rainfall and moisture even far away from where their source is. The second key result that I want to share today is the role of volcanic eruptions. So here I'm plotting again what I've shown previously, the rainfall changes in the CSM model over the last 1,000 years or so. You can just focus on the thick black line, which is the average of all the different simulations for now. And what you see is that you have these dips, these droughts in the model associated with these black triangles, which I'm plotting as times of big volcanic eruptions. And the bigger the triangle, the bigger the eruption. And you see that for a lot of these, the timing of the droughts align with the timing of a volcanic eruption. And why might that be the case? Well, volcanic eruptions actually release a lot of aerosols into the atmosphere. And if they're a big enough volcano situated in the right location, then that aerosol can actually interact with the atmosphere in the tropics and with the Walker circulation. And that can change the moisture delivery and the wind patterns such that it can also lead to droughts in places like Southeast Asia. Interestingly, if we line up the periods of historic droughts that we know from historical records and from scribes and scholars, we see that some of these volcano-related droughts actually line up nicely with times of droughts that we know about. For example, the Ming Dynasty drought, the one that sort of contributed to the fall of the Ming Dynasty in Imperial China, seems to be associated with a small volcanic eruption of that time. So this is a way to directly link a climate event, a geological event really, with changes in human society through the climate system, and really just shows how interlinked humans and the Earth system really are. And so, finally, I want to end with sort of a perspective of, okay, it's cool and interesting to study these past mega droughts and what might have changed it, but why exactly would we be interested? What's the point? And I would argue that there's a lot of reasons to want to study the past. First off, a better understanding of how the climate has changed in the past will help us forecast future changes in rainfall. Specifically from this study, right, we learned that ocean temperatures and sea surface temperatures in the Pacific and Indian Ocean can help us predict when droughts or flooding may occur in Southeast Asia and other places through connections to the Walker circulation. Furthermore, we know that aerosols, either from volcanoes or from humans, can also impact the global water cycle and rainfall. This is just a screenshot that I grabbed from the global volcano database, I believe, and it just shows the list of currently active volcanoes that are going on today. And I don't think any of these are particularly large, like the ones that caused the collapse in the Ming Dynasty. But this just shows that a volcanic eruption can really occur at any moment. We have some lead on that, but we don't have as clear understanding of when they could happen. And so understanding their impacts on the climate system is important for now and even into the future. And finally, studying past climate can help us test and validate the models that we use. So I showed using this model that we're able to reproduce the timing of some of the droughts that we observed in the historical record. But some of the droughts don't actually pop up. And it sort of leads us to question, are there aspects of the climate model that we aren't, there are aspects of the climate system that the models aren't capturing properly, or are there conditions that we aren't exactly tuning correctly? And so that just leads us to try to understand, why is it when we see these droughts in the past, we don't see them in the model? And understanding and reconciling that can help us develop better models that can lead to more accurate forecasts of the future. And yeah, so that is what I have to show. And I just really want to emphasize that the model that I used and a lot of the research that funded me was provided by the National Science Foundation. The CSM model is really built by the National Center for Atmospheric Research, which is largely funded by the NSF. And so none of this could be possible without the support of federal funding from the US government.
Awesome, thanks, Shawn. We'll wait for more questions to trickle in here, but there's one question that sort of addresses I think the importance of volcanic activity, and my sense is volcanic aerosols don't really stick around that long, whereas Pacific SSTs can vary on decadal timescales. Those plots you showed seem consistent with that. This idea that volcanoes maybe cause like a really sharp decline in precipitation, but it's relatively short-lived. I guess how does that kind of fit with your? I guess it depends on how you define a mega drought, but if you could kind of speak to this question of kind of time scale.
Yeah, it's a good question. I think so. Specifically, when thinking about mega droughts and these multi-year droughts, you're absolutely right. The aerosols that a volcano throws up in the atmosphere don't really stick around for 10 or 20 years or anything. And so what we think is likely responsible is an interplay between the two. That it's likely that we might have entered into a phase of Pacific SSTs that might favor a drought, and then a volcano erupts, and that's really the kick that even drives that drought into an even more extreme drought, and then that perhaps exacerbates the situation. And for example, that might also explain some of the discrepancies we see between the CSM model and the real world. For example, it's possible that while the CSM model says there should be a drought at this time, the real world might not have been in a state that was favorable to a drought. It might have actually been a really moist time in Southeast Asia. So even if you have a volcano, it's not really going to change the amount of rainfall. And so really it's an interplay between the oceans and what's going on in the atmosphere that I think is leading to these droughts that we observe.
Right. Cool. Okay. I'll pick another question here. How do we know about volcanic eruptions and CO2 levels hundreds of years in the past? So how can you make that sort of a plot?
Yeah, it's a really good question. Yeah, it's done by really clever work from paleoclimatologists who go out in the field. And so there's a few layers to it, but with greenhouse gases and volcanic eruptions, a lot of where that data comes from is from ice core records. And so these large ice sheets and ice archives from the polar regions, they trap small bubbles of air that lock in the condition of the atmosphere hundreds and thousands of years ago. And so we can use that to determine what the CO2 and the methane concentration was like hundreds and thousands of years in the past. And that can be used to inform what should go into these models as settings. And similarly with volcanic eruptions, I believe because they leave this layer of aerosols that go into the atmosphere, and sometimes those fall in the polar regions, that also manifests as a distinct layer, an ash layer that we can identify and date and sort of use to reconstruct. And so that's also another aspect of uncertainty too. The eruptions that we sort of put in the climate model are sort of based on these a jigsaw puzzle of all the different ice cores we have from around the world. And so some of these eruptions in the model, we don't actually even know which volcano they come from. We just sort of know that how much aerosols they put in the atmosphere. And so there's still a lot of uncertainty even on that front. These forcings are not absolute. So there's definitely a lot of work to be done on the modeling side, but there's also work that can improve our understanding from the paleoclimate, from the geological side. And so I think that's really what's exciting, is that multiple avenues of research can help us constrain these things.
Super cool. Okay, we have time for at least one other question. I'm curious about the anchor droughts.
Yeah,
those are not periods that show up as droughts in the CSM large ensemble, or the last millennium ensemble rather. Like is your sense that these were kind of long-term El Nino-like shifts or warm phases of the PDO or something? And does the last Millennium Ensemble produce sort of that time scale of shift in the PDO or El Nino or however you want to define it, or is there some sense that the model's kind of getting that low frequency variability wrong?
I think it's more of the latter of what you said. So if you take the model results at face value, you would say, oh, the anchor droughts are not driven by any external forcing. They're only sort of like a dozen El Nino events that just so happen to line up, which I think is kind of unlikely. It's sort of just my personal opinion.
Yeah.
And if you look at the climate model, so I had a little bit of model data comparison here, but if you look at a power spectral plot of variability in a climate model versus variability in the real world, climate models have a tough time at getting enough energy, enough variability on that centennial, that low frequency time scale. So I think that because they're not getting that as well, it's possible they're not capturing the right processes that lead to things like the anchor droughts. Right. And again, that's why we need more tree ring records, more stalagmite records and things, because that can help us better validate sort of our understanding of these long-term changes. And yeah, it's definitely a lot more work to be done, and why we need more funding to develop better models.
Yeah, cool. I mean, I think we have 1 minute left. We're kind of currently in this period of a prolonged shift toward the cool phase of the Pacific Decadal Oscillation or more La Nina events, which models also kind of have a tough time capturing, right? So it does.
Yeah.
I mean, there's a lot of debate actually about what's exactly driving that. Maybe it's part of the forced response, but I think this is really interesting. It's able to speak to that question to some degree.
Yeah, I've seen some studies that attribute aerosols to, or this drought to aerosols, and so the limitations of the model in simulating volcanoes probably is related to how they're limited in simulating human aerosols. So yes.
Cool. That's all the time we have, Shawn. That was really cool.
Sure.
Thanks a lot.
Of course.
And I think that's the end. Oh, my clock's a little bit ahead of the other clock. My clock's showing 2 o'clock. So I guess we had maybe 1 more minute. But this is close to the end of my time to switch over to the next host. Oh, is it Liz? I didn't see that.
It's me.
Hey, Claire. Okay. Great.
Liz is going to be our next speaker. Hi, everyone.
Okay, cool.
Nick, thanks so much for your excellent hosting job. Okay, here we go. Everyone, welcome. We are kicking off hour 29 of this live stream. That's crazy. We're almost a third of the way through. I'm Claire Singer. I am a climate scientist, specifically a cloud scientist. So I wore my cloud sweater for you all, some fun spirit. And I hope everyone is having an amazing time at this live stream. I certainly have been so far as an audience member, and I'm so excited to have my first hosting block now. I will be back on Saturday morning as a speaker and then again as your host. So next up, we're going to have a panel discussion, and those guys will be joining me shortly. Mark is going to be back helping me host it, or I think I'm helping him. He's really driving this discussion for now, but I think we'll take a few minutes and just remind everyone why we're here. Or should we jump right into it?
Yeah, let's do, you can do the quick mission statement. I think that's a great idea before we introduce Ellen and Dave.
Okay, amazing. So for those of you just joining us, we are in our 29 of this 100-hour live stream. We're chugging right along. It's very exciting. Thank you everyone who's been here. We have been having amazing talks from scientists who work on climate and weather. We just heard from someone who studies the ocean, and interspersed with that, we're having these kind of fun other events like is coming up right now with panel discussions. But we're really here to just spread the word about the kind of research that we do, the science that we do, and we do it all with federal funding. So all of this work that you've been hearing about, you've heard speakers talk about their work being funded by the National Science Foundation, NSF, by the National Oceanic and Atmospheric Administration, NOAA. Some of our work gets funded by NASA, by the Department of Energy. And really that federal funding is critical to everything that you've been hearing about. So I just want to encourage you, if you have gotten excited by some of the work that you have heard presented, some of the science, if you think it's great, if you want more of it, if you want it to continue, then please look at the banner at the bottom of your screen. We have a link. We have some information about how to call your representatives. Let them know that you are jazzed about climate science and you want more climate science. Because right now, funding for climate research is at risk in the US. This country has had a long tradition of doing amazing scientific research, especially kind of pioneering weather and climate science over the past many decades. But it's not something we can take for granted. It needs to get funded every year by our Congress. And now is the time to let them know. They're starting to think about next year's budget. So now's the time to tell them that you want to keep our climate research going strong. And I think we're going to talk a little bit more about that now with this panel. So I'm going to let Mark introduce our esteemed guests.
Yeah, thank you, Claire, for just talking about our mission for the 100-hour-long live stream. And thanks everyone online for joining us. So before I introduce our panel here, I'm just going to say quickly that this is the start of our kind of keynote session. We have a list of we have a lineup of really incredible talks for you this evening. And right now we're actually starting with a panel. So yesterday we had two panels. One featured terminated NOAA scientists, and the second featured two former National Weather Service directors, Louis Uccellini and Joe Friday. And today we have for you from the American Meteorological Society, or AMS, the current president, Dr. David Stensrud, and the president-elect, Alan Seals. And so I'll introduce them very quickly before we dive into the questions here. And I will also say that the structure of this panel will be, first we'll do introductions, then we'll go over some pre-made questions, and then we will take questions from you guys watching the live stream. So please go ahead and start typing questions, and we'll be sure to save those questions so we can get back to them later. Starting with David Stensrud is a professor of meteorology in the Department of Meteorology and Atmospheric Science at the Pennsylvania State University. Prior to joining Penn State, he spent nearly 30 years as a research meteorologist at the NOAA National Severe Storms Laboratory, where he worked on using model ensembles for forecasting severe and hazardous weather. He has served in various volunteer roles with the American Meteorological Society throughout his career and is presently the AMS president. Going on to Alan, who I'm sure you guys have all seen in his broadcast meteorology made famous. Alan Seals was a retired broadcast meteorologist based in Mobile, Alabama. His meteorology degrees are a Bachelor of Science from Cornell, go Big Red, and an MS from FSU. He is the 2025 president-elect for the AMS. Alan went viral on YouTube for his 2017 coverage of Hurricane Irma. He teaches weather broadcasting at the University of South Alabama, writes a weather column for his local newspaper, and serves as a weather consultant and expert witness. Alan has authored 3 weather books and produced over 100 weather videos used domestically and internationally by K-12 educators. So welcome, Dave and Alan. Thank you for joining us today.
My pleasure.
Dave, is your mic unmuted? I don't know if we can hear you. All right, let's
You
try to...
are very quiet.
You may have to check your settings, Dave. I just went through this. My settings tried to put the audio into my microphone rather than my speaker.
Let me see if I can do it for you. There should be a way to change where your mic is coming from. Maybe it's coming from the wrong option.
Does this work better?
That works.
Yeah.
That is better.
Thank you.
All right. Thank you everyone for the tech difficulties. We're just going off on a fly here.
Doing our best.
Doing our best. We're normally just scientists sitting behind a computer. Anyways, so Alan and Dave, welcome. And I think we should just start really quickly. We want to hear about the AMS. We want to hear about the statements that you both wrote through the AMS, talking about the cuts and the layoffs, how they're affecting the weather and climate prediction and research community in the United States. We would love to hear from you. Let's start with Dave.
All right. Thank you, Mark. And thank you, Claire, and everybody who's helped organize and all the hosts. This is just a wonderful event. So thank you so much. And it's nice to be invited to participate. So the AMS is a professional and a scientific society. And our mission is to advance the atmospheric and related sciences and technologies for the benefit of all people. And so that's really at the heart of what we do. AMS was founded in 1919, so we're a little over 100 years old. Right now, our membership is right around 12,000 members. So roughly a third of those are government employees, so state and federal employees, and also members who serve in the military. Another third are private sector. So it might be somebody at a weather forecasting firm, could be a broadcast meteorologist, such as Alan, but also lots of meteorologists and scientists work in energy firms, either predicting power demand or power generation from renewables. Could be in transportation, insurance and reassurance, agriculture. In lots of different sectors, we play a role. So that would be a third of our membership, and then the remaining third typically is your university staff. And so it really is a very rich environment. And what AMS provides then is we publish 12 peer-reviewed scientific publications. We have meetings and conferences throughout the year. Most years, I would say the total number of meetings and conferences is somewhere in the range of 30 or so. And then we have certifications. So we certify professional certifications for like broadcast meteorologist, consulting meteorologist, a new one in digital meteorology, and then also a certified atmospheric science teacher. And then we also provide resources for K-12 and early college educational instructors. And so AMS is involved in lots of different ways. And so I think it makes it for a very rich place to be a part of. Alan, would you like to add anything to that?
Yeah, I would add to that. AMS, I joined as a grad student back in the 1900s, in the mid-1980s. To me, it has been networking and knowledge. And again, my career has been broadcast meteorology, but it's been so awesome to work on panels and committees and groups with people like David, other folks who are giants within the industry of meteorology. And it's all about sharing information, all of us working together, which ultimately benefits the public. One other small item is we have a lot of international members, and we have corporations that are members. So it's not just the professor or the person on TV. It is all the folks involved within the weather enterprise.
Yeah, I also joined as a graduate student. My first conference and presentation was at an AMS meeting. I would agree networking is a big deal. And of course, our field now to make progress on the research really typically involves a team. And so, walking into, meeting someone in the hallway, having a discussion, oftentimes it leads to an idea for collaboration. And before long, it might be a larger group, a larger team to address a specific problem, and writing proposals then to get funding to do the work and to get the resources. And so AMS, helps all that happen in a variety of ways. So in terms of recent statements, so we started, I would say, becoming concerned probably back in February about what was happening on the federal side of potential funding cuts and just science in general, not just atmospheric science, but science writ large, I think, for the United States. And so I think we started putting out some early statements just about, the weather enterprise, which we often refer to. That's basically the three sectors that work together collaboratively. So the foundation of that is pretty much what the federal government provides. So that's NOAA. And NOAA, if you're looking at your phone for radar, it's probably NOAA's radar you're looking at. If you're looking at weather forecasts, regardless of where they're from, you're probably having NOAA data behind that. If you're looking at satellite imagery, that's likely to be NOAA satellite observations. Surface observations are NOAA observations. So the government provides this rich amount of data that really is essential for making weather warnings as well as weather forecasts. And then the private sector can take those and add value in lots of wonderful ways for specific industries and needs that go beyond just serving the public needs for weather information, for safety, and for general use. But NOAA really is the foundation of that. And of course, the academic sector is part of the weather enterprise as well. We use a lot of NOAA data in our classes, in our research, and then of course work together to advance the enterprise in terms of just the quality of the warnings, as well as the quality of the forecasts and just general weather information and safety and weather impacts our economy in very large ways. I think we've had studies showing that for every dollar invested in the weather enterprise, the American public gets $10 back in added value.
I'll add to that. All of our statements really follow the mission of the AMS, which is for our members and even those who are not members, to strengthen all of us as scientists, as meteorologists, as hydrologists, climatologists, all for the benefit of society, all for the benefit of people. As Dave said, weather impacts everything. I was on a Zoom this morning, and just before I started, we had a thunderstorm. I'm in Mobile, Alabama, knocked out power. So 25 minutes, I had no power. But I used the NOAA data yesterday as a forecaster to look at the map and say, oh, there likely will be thunderstorms over Mobile County tomorrow morning. So in the back of my mind, I knew it was a possibility. And when it comes to weather, that's the big deal, is getting people prepared for all the possible scenarios.
Yeah, I always think back to when I was growing up in Minnesota. Winter storms you kind of knew it was coming, but you didn't know what it would be like. So you wake up in the morning and I'd be all excited because there's 2 feet of snow on the ground and schools are being canceled, basically across the TV and on the radio. My dad would be calling his employees to tell them to stay home today. Nowadays, those decisions are made a day ahead of time.
Sure.
Weather forecasts, closing for schools, canceling of airline flights, all sorts of ways that we see immediate action, a day or more ahead of time based on a weather forecast. And it just shows how far we've come over the past 30 years, which I think is pretty amazing. It is one great success story that perhaps deserves a bit more attention. I think people get used to it and they don't necessarily think back on what it was like 30 and 40 years ago when weather was something you lived with, but we really didn't have a great deal of ability to predict it.
Exactly.
I would call it incredible. The fact that in your pocket, you have a computer and you have some sort of weather app on that computer that in most cases tells you it's going to rain in 30 minutes or lightning is within a 5-mile radius. And all of that is based on research that has been fundamentally done by NOAA, taken to different levels by private industry, by academia. Now people at home can download the source code to some of the NOAA models and run their own weather models. That's amazing. To me, one of the really cool things about data and NOAA's data in particular. I mentioned I'm in Mobile, Alabama, right on Mobile Bay. And whenever we get a strong south wind, the water is pushed from the Gulf into Mobile Bay, and then the bay is sort of shaped like a triangle on the northern end. So literally, we get sort of a storm surge. Now, this happens with hurricanes. It happens with an approaching cold front. And when you look at the NOAA tidal data, it shows you during the new moon, during the full moon, you have a tide range of about 2.5 feet. If you look at the history of that tidal gauge going back 50 years, back to 100 years, it shows in nearby locations that the water level on Mobile Bay relative to the land has come up about 7 inches. Now, that doesn't sound like a big deal, but if you've ever driven across the causeway between Mobile County and Baldwin County, you literally are at sea level, and that surprises a lot of people from out of town. So strong south wind, new moon, full moon, we get over splash onto the causeway, which is US Highway 90, US Highway 98, and it ends up shutting down the highway. Now, I don't have the full data going back decades, but just from the 25 years I've lived in Mobile, it's happening more frequently. And it's a consequence of expanding seawater and higher water levels. And right now, there's no sign that it's going to change. So this is going to become a big economic deal, a big transportation deal for my part of the Gulf Coast. And the data is right there. To me, that's the most awesome thing is the average person can go online. They can look at the projected wind speed and direction from the National Weather Service. They can look at the tidal range from the National Ocean Service, and they could figure out whether you're likely to have the lanes of the causeway closed right there.
Yeah, that's amazing. I think you guys brought up 2 really incredible points. The first one, I mean, Dave, I've heard it described as a quiet revolution. The fact that we can predict the weather so accurately 5 days in advance, that's something that was never done previously 40 years ago. And it's only because we, the American public, have invested in weather and climate research all of these decades, right? This live stream is a reminder that this is what we've been doing. We need the science in order to make these really accurate predictions. And Ellen, the way you tied in climate change to these predictions is so important. And if we're going to try to make better predictions under climate change, we need to be able to study that more. So I think those are just 2 really excellent points. But we can also move on to some pre-made questions. Claire, if you want to get us started.
Yeah, I'll ask the first one. We want to hear from both of you about what the role that scientific and professional societies like the AMS play in advancing science. So,
Okay.
broad question.
Yeah.
I think maybe you touched on bits of it, but.
So Alan, how about I go first and you can,
Sure.
We'll trade off. So I think there's 2 pieces. The first one, as we already talked about a bit, is the networking, bringing people together to have discussions, to learn from each other. It's amazing sometimes what happens just in these hallway discussions, or you go to somebody's talk and you learn something and then you talk to the person after the fact. It really is, I think science isn't done just by a person with a desk anymore. It really is a team effort. And I think our professional societies help motivate and make that happen, right? We provide opportunities for interactions, for learning, and then for building teams. But the second part, I think, is the publications. So AMS with our 12 publications, that's where when you're done with your work and you write it up to share it more broadly, so more than just going to a conference and giving a talk, it goes through a peer review process. And AMS basically oversees all of that. So you submit your paper, an editor who's appointed by the AMS through all of our publications commission, decides who should review that paper. The reviewers have typically 4 weeks to write up comments and send them back, and then you get that, and a decision's made, and sometimes those decisions are pretty tough. I mean, the reviewer's job is to find all the flaws in what you've done. So I think overall, when you submit to an AMS journal, roughly a third of papers are rejected in the first round. Majority is probably major revision, which means you have work to do. You still have to convince the people that what you've done is correct, and then a smaller fraction are minor revisions. It's almost, I I've ever had a paper actually get accepted when it gets submitted. That just never happens. And so but of course, that's an important part, because then it becomes part of the literature. It's around hopefully forever. And sometimes an idea that was published years ago comes to the fore. I always think of Ed Lorenz's paper, non-periodic, deterministic non-periodic flow, published in the Journal of Atmospheric Sciences, which ended up really being the foundation for chaos theory. That 1963, right? That was pretty amazing, and it's part of our literature that you can go back and read on the web if you want to. You can go to AMS Journals and actually download that right now if you had the desire.
Yeah, I would add to that. One of the things you may not think about, and it's really more important than ever, is societies, and I'm speaking especially for the AMS, one of the roles is to create a safe space for those of us within the profession. And even on the most basic level, it's a space where we can communicate in our own geeky jargon, and other people appreciate what you're saying. So to me, that's a really important role that the society, number one, it is sort of a hub to connect different sectors within your science, but it's also a place where you can be your authentic self and share information that makes other people happy and excited, and also smarter.
Definitely.
Actually, Alan reminded me that AMS has what we call convening power. So we can bring different people into the room, and again, in a safe space, and talk. And sometimes there are challenges to face. What should the weather service be doing compared to private sector? Weather firms. Where is that boundary? A lot of those discussions we had 10 and 20 years ago, which really led to, I think, a lot of the growth in the industry, and also we're team players now. So I think AMS offers that as well, and other societies do too.
Yeah, it's amazing to go to an AMS conference and see like all the public federal workers working together with the private industries. I think that is so magical, and it's a great field to be in, I think, for that reason. So our next question, really appreciate those answers. AMS is a big deal, and I think you guys really touched on how AMS kind of like sees everything going on in our community, whether you're in the private industry, the public, or academia. And for that reason, we're really curious what you guys think about these cuts impacting early career scientists at this stage. A lot of people like myself and Claire, I'm sure we all we have a passion to study climate science, meteorology. I mean, I've been obsessed with the weather since I was 5. I'm sure just like you both. And so how do you think these cuts might impact kind of this stage of our career? Do you think it might steer people away, steer people out of country because of the cuts? We'll start with Alan.
I would start with stick with your passion. Don't let this discourage you. The cuts are tragic, and they are certainly putting a bad taste in everyone's mouth about what is the future of our profession, what is my future within the profession. I try to be optimistic, and Dave and I have talked to folks within NOAA, within the government, off the record talks, and some of those folks are optimistic, in particular, that some of the freezes and cuts will eventually be lifted. They may not be as severe. I also advise younger people that even though right now it doesn't look good, there's really no profession anymore where you're guaranteed anything. And that's a sad statement, but it's a reality. And that's why I say, most importantly, stick with your passion, have a plan B, have a plan C. But right now I'm optimistic that things will turn around, and your goal may be a specific area within science. You may have to do a neighboring area in the short term or long term. And as you go through for folks who are still within their academic studies, definitely diversify with other courses, including things like business, certainly artificial intelligence, things that are the future of the whole planet, separate from the science.
And so I'd add to that perhaps that the 2026 budget hasn't been defined yet. And so I think part of the reason for the live stream is encouraging people to use their voice. And we have time to use our voice and let people know what you think. What you think is the right path forward. It's certainly atmospheric science is being threatened, but science in general is being threatened. And my hope certainly is that a lot of corporations, a lot of industry, private sector rely on a pipeline of highly trained individuals in the sciences for lots of different things. And having a threat to that pipeline, I would hope, and I certainly believe that they have to be expressing concern about that. It's in their best interest, right, to have a rigorous, very vigorous, scientific education going on. And I would agree that, this is a great field. I don't know exactly what the next couple of years look like, but I do know that the skills that you get, you have to learn the physics, you have to do all the math, you have to do computational methods. Communication often is a part of what we teach. We have statistics. I mean, with that skill set, you can pretty much go anywhere. I'm always amazed at where our graduates go. Often they're pretty much in the atmospheric science area, but I have friends and colleagues who have gone in the medical profession because they're doing data analysis on cancer studies and all the rest. It's really quite amazing where you can go if you want to with the skill set you are getting in this field. It is really one of the hardest majors that you can have in any university is that degree in meteorology and atmospheric science. So I'd say follow through. We're with you in terms of all the early career scientists. We're hoping for a good landing here. It's too early to tell, but we are encouraging everyone to use your voice. That's pretty much what our statements have been all about. Is ringing the alarm bell and saying you need to stand up now for science. This is important. If you've never done this before, today's the time to start.
Great. Yeah, you heard Dave. Folks on the live stream, please reach out, contact, raise your voice. Thanks.
And I'll say personally, as an early career scientist, thank you both for those words of encouragement. I see a bunch of people in the chat are also saying thank you at various stages, whether they're students or in our first jobs. It is a bit of a scary time to be in this field, but it's good to know we have each other for support. So I think we will start taking questions from the audience now. There are a lot of questions, so I don't think we'll get through all of them. I thought this was a fun one. So we'll go on a little bit of a light note from Mallory Redman. She wants to know, what was the most memorable weather event that you've ever observed or covered? And how did some of these resources from the National Weather Service or other government-funded agencies help give you forecasts or aid you in observing that event?
Oh, I'll take that one. This is the 20th anniversary of Hurricane Katrina. And Katrina, there are probably 5 weather events that are most memorable, but Katrina is one, not just because it was a Cat 5 in the Gulf and it hit land at a Cat 3 and killed over 1,000 people, took over 1,000 lives. But the forecasting 20 years ago was pretty good. It's not as good as it is now, but it was good enough to let people know what was coming. The big tragedy, as you know, was the failure of levees in New Orleans. If they had not failed, the death toll wouldn't have been as high. It still would have been high. But Katrina stands out, and it brought home the fact that we in science sometimes we get so into the data that we forget on the other end of the data is human lives. And Katrina really brought that point home because so many people were impacted physically, financially, communities were destroyed and changed forever. And that event, just like all the hurricanes I've covered, as I was on TV as a broadcast meteorologist, 95% of all the graphics and all the data behind me came from NOAA. It was satellite, it was radar, it was current conditions at airports, it was dropsondes from the hurricane hunters, it was weather balloon data. And that's something people underestimate when they think about TV. Everyone thinks about TV weather as being the whole field of meteorology, but we're sort of the front face of it. But there is such a huge reliance on NOAA data. So Katrina was my vote.
Mine would be the May 3rd, 1999 Moore, Oklahoma tornado. So again, devastating event. I actually lived in north side of Norman, and so I was standing on our porch looking to the north and seeing this giant wedge tornado go through north of me, and I could turn around and look into the house, and there is live coverage on TV of all the radar, storm spotters. Weather Service did an amazing job. But after the fact, the communities really rallied together to bring resources to those who were impacted, and the Red Cross. And so the community response was just overwhelming, but also a very tragic event. But yeah, that'll always be in my memory for, yes, most memorable, but not necessarily in a positive way, but just the power of the atmosphere, right? Which is one reason why it's so important to get these warnings out, because they do threaten lives, on a regular basis. And it's really hard to see.
All right. Sorry, Claire, you can go ahead.
Yeah, definitely some of the most memorable events are not happy. I think we heard from earlier speakers about NOAA's $1 billion weather disaster database, and yeah, we're usually focused on the things that are negative in this. Let's see, someone had a question about the funding and staffing cuts, specifically at the National Weather Service, but maybe could speak more generally across NOAA. Do you know of, or do you have an idea of a way that local communities could step up to, if their radar has been impacted? Are there plans, or should there be plans for local communities to start operating these things that normally have been federally funded?
Well, that's an interesting idea. I mean, the radar systems are, lots of pieces to them. The radar network, the dishes are, 10 meters across. And so they're large, basically parabolic antennas on a fairly high tower. And then there's all the, computational power that goes behind not only writing the radar, but then, collecting it and then converting it into information we can use. So it would have to involve then just a lot of pieces that seems somewhat overwhelming to be able to do that without a plan ahead. Now, of course, some local TV stations have their own radar systems. And so those certainly I would think would continue to operate. Alan?
Yeah, I was going to add, I'm reminded, to answer the question, I hope we don't have to do that. The problem with that sort of picture is it then comes down to, if you live in a rich community, you're going to have more access and more resources than people in a poor community. And that, again, is one of the strengths of the government serving as a foundation, as an equalizer for all zip codes. But there is right now, and there have been a couple of private companies that are selling medium radars for communities or TV stations that literally are designed to fill in the gaps between the NexRad radars. But one of the big strength of NexRad is, I think, its It's free, it's open to the public. It is based on standards where everyone knows the quality of the data and the standard. So that's your argument for not trying to do a piecemeal sort of radar network.
Yeah, definitely. We want the federal funding for these things to continue.
Okay, great.
You want to do the next question?
Yeah, and I was also just going to mention so my local news station growing up in Syracuse, New York, and upstate New York, they have actually their own radar, which is really unique because we live between in like kind of like a dead zone. I don't actually know the term for that, but it was impossible to see like lake effects, snow bands because they're always so low from the Watertown Binghamton radar. So that was a unique situation and interesting that you guys brought it up too. Okay, next question from the chat. This one is quite interesting. Safe funding is no longer in jeopardy and everything can resume as normal tomorrow. How should scientific organizations and individuals change the way they communicate with the public about their work?
Start. The answer is start. And the problem, frankly, for those of us in science is oftentimes we feel our work is just so valuable, people will just see it and they'll recognize it. We don't have to sell what we're doing. But if you look around the world, and now you even look into politics and you look into social media, everybody, even I just saw a clip about two nuns in South America going viral, singing a song. Everybody is a salesperson. Everyone is promoting their cause or their product. So yes, as scientists, we do have to start communicating more to the public what we're doing and what the value is.
Yeah, and I fully agree. I mean, it's talking to your neighbors, it's talking to your civic groups, visiting if you have children, if they're in school, visit the classrooms, talk to the science teachers in the schools to get more information about what we're up to. Take every opportunity you can to try to communicate it. And also for those who can, the new media, social media in various ways to get out the story so people learn more about it. It does seem like we have this great success story and yet it's not recognized very widely of what's happened. And I think we've spent most of our lives talking to each other in terms of all the exciting things we're doing, but we haven't put as much effort into talking to people outside of the science community. And I think that really does need to happen.
And that also will bring in a new generation of scientists when they can actually see the cool things that are happening and actually know that maybe their neighbor is a scientist, but they never figured that out.
Yeah, I think those are really good points. And it's actually one of the reasons that inspired the live stream that we're holding right now, because maybe it's an opportunity to share with the American public, this is what your tax dollars are going to. We're behind the scenes doing the research, doing the forecasting. So I think it's a good opportunity that we're finally maybe learning how to communicate, even though it came as a result of a threat to our research and forecasting.
Oh, one last thing, as I reread Amy's question about everything resume as normal. Normal is gone. Unfortunately, what we knew no longer is. And it's not, except for how it's happening, change is not a bad thing. You have to change, you have to grow. I do a lot of yard work and I have to prune my azaleas every year to keep them from growing out of control. But there's a difference between pruning your flowers and taking a chainsaw and just cutting through the entire garden. So what we hope is that we are, as scientists and as individuals, we are thinking through and calculating how to grow in a healthy way, even if we have fewer resources. And unfortunately, fewer resources is a likely scenario, which goes for all professions, whether it's dollars or people. Everyone is doing more with less.
That's true. And that chainsaw anecdote was really good. I feel like the cuts right now are there's no thought to it. And this was kind of mentioned from the National Weather Service directors yesterday. It's kind of just happening to probationary employees and people like that, even though some probationary employees, of course, are just people who are promoted and they're in a probationary period to start their new job. So we're just losing all of that experience. And I think Joe Friday made the analogy to, we're now like Swiss cheese. We have holes in our weather and climate infrastructure, and that's kind of how we're dealing with the repercussions right now.
Mm-hmm.
Yeah. So my favorite analogy of late is, when I fly on a commercial airline flight, there's a pilot, a co-pilot, and at least one flight attendant, often two.
Sure.
And it seems like in the Weather Service now, maybe there is a pilot, maybe a flight attendant. I'm not sure there's a co-pilot or extra help. And so, moving towards really more efficient doesn't necessarily mean it makes you really comfortable with what's going to happen, because at some point that's just not enough, right? On a regular flight, that's fine. But if the flight gets interesting, the pilot gets sick, that flight is in a lot of trouble. So it makes me worried.
Yeah. Claire, do you want to do one more question maybe?
Yeah, there's one more question here about our international community. So AMS, obviously the American Meteorological Society, but we know that studying the weather and the climate is really a global endeavor, and what happens here is affected and affects everywhere else on the planet. So how do you see that playing out in the research arena and in the professional society arena? Do you have a counterpart in other countries that AMS collaborates with, and what does that look like?
Yes, so we do. We have lots of basically memorandum of understanding or agreements with other professional societies. There's the Royal Meteorological Society in England, the European Met Society, there's a Japanese Meteorological Society, Indian Meteorological Society, Chinese Meteorological Society, Canadian Meteorological Society. I mean, list goes on and on. Some of our meetings when we have conferences are actually outside the US. There'll be one meeting in Canada later this year and another in Italy, if I remember right. Meetings can be anywhere across the globe because, again, AMS has members who are outside the US, but also we enjoy partnering with these groups. And actually several societies have basically written statements in support of what AMS has written, expressing their concern and what's going on with federal cuts to science in the United States because of the global linkages. I mean, weather is a global phenomena, as is climate. So if you want to be able to predict it and understand it, you have to understand what's going on all across this beautiful planet we live on.
Ellen, do you have a follow-up or?
Dave said it well, and that also goes back to people who do get a chance to go to an AMS conference, which is always late January. You get to meet and collaborate and network with so many other meteorologists from so many other countries. And even though the languages might be slightly different, and even though the political culture of each country is different, we are still all there, same team, same purpose, all about being the best as we can as science professionals.
Great. No, thank you so much. So we're actually reaching the end of our 45-minute panel here, but let's definitely close with any last-minute thoughts from Dave and Alan. Dave, do you want to start?
Yes, I mean, we're in a great profession. I've always felt very fortunate to have landed in this profession. The people I work with are wonderful. I think people who gravitate towards this profession are really all about public service. And so I think we have a lot to be proud of. But at this moment in time, use that pride to raise your voice and let people know what you're doing, but also let those who are in decision-making positions know what you think should be done.
Just what he said. And my only advice for you is think of this live stream as covering a hurricane. It may be 3 or 4 days straight, but you'll get through it, and it's for a good purpose.
That's so true. Yes. We just crossed hour 30, so that's very great. Well, great. This was so great, Alan and Dave, to have you on today. We really appreciate you guys taking the time to join us and answering questions from our YouTube streamers. So thank you, and I hope you have a great rest of your day.
All right. Thank you.
Thank you both.
Thanks, guys.
Okay. Mark, are you staying on with me?
No, I'm going to take a 45-minute break, and then
Okay.
I will take over for you at 7.
Excellent.
See you guys then.
That was a wonderful panel. For everyone who is just joining us, welcome. My name is Claire Singer. I am a climate scientist, and I am your host right now. We just rolled into the start of hour 30 of this 100-hour live stream. So thank you so much for joining us. It's been a blast. I am going to be continuing to host for the next 45 minutes. We're in our period of keynote speakers, so these are slightly longer talks, and you get to hear from some really amazing people this evening. But before we invite our next speaker on, I just want to bring us back, remind us why we're all here. So we are spending 100 hours talking about weather and climate, meteorology, research, and forecasting that happens in the United States. And we're talking about this because we, as scientists, all love the work we do. We want to share it with the public, and we want to share it with you guys because of how important the American public has been to this research over the past many decades. All of the work that you are hearing presented here and discussed is funded by federal tax dollars. People have mentioned various agencies that fund their work, whether it's the NSF, the National Science Foundation. We just heard a whole lot about NOAA, the National Oceanic and Atmospheric Administration, on the panel. And you're going to hear from scientists who work at some of these agencies or scientists who are funded by these agencies. And this funding has just led to what I've heard people refer to as magical or miraculous, just amazing advancements in our research. The United States has led the way, really pioneering a lot of developments of weather and climate modeling. Over the years, the first computer weather forecasts were developed in the US. The first models that were able to predict how the climate system would respond to increasing pollution, increasing greenhouse gases in the atmosphere. Those were developed in the United States. And these models, they're really underpinned by a vast network of observations, measurements that we make from weather stations, from satellites, from airplanes, from balloons, from boats, from floats, from underwater robots. Everything there is what drives these forecasts and these climate projections. And all of that is funded by your tax dollars. So if you are excited by the science that you hear shared here this week, please reach out. We have a link here that's scrolling at the bottom. Call your representatives. Tell them that you want to see more. You want to see continued support of weather and climate research and science in the United States. It's just so important. So I think now we're about on our schedule to invite in our next speaker. See if she's ready to join us. So we're going to have a keynote talk now from Dr. Karen McKinnon, and I'm really excited to hear Karen speak. We haven't met before, but I know her work, and she's going to tell us about her research on heat waves, which, as we're rolling into summer here in the US, it's time to start thinking about heat waves again because they're coming. And I'm just so excited for this. So please, Karen, take it away.
Wonderful. Thank you so much, Claire, and great to be here, and amazing that you guys are already at hour 30. So huge thank you to the hosts and the directors and everyone who's presented so far. This is a momentous effort, but I think an effort that matches the occasion right now to just highlight the importance of the work we're doing. And so I'll talk about at the end the importance of federal funding for that work. So my name is Karen McKinnon. I'm an associate professor at UCLA. I study climate science broadly, and a lot of my interests are in the context of heat waves, which is what we're going to talk about together today. My screen will work the way it was working before. 1 second. There we go. All right. So many of you who are in the audience probably experienced either an extreme or perhaps record-breaking heat wave in any given recent summer. So I've given a talk on heat waves, in some of the recent summers, and I just keep having to add years to this list that we had record-breaking heat waves in the summer of 2021, this major heat wave in the Pacific Northwest. In the summer of 2022, we had one in the UK. The summer of 2023, we had one in Europe. Actually, they've started naming their heat waves in Europe so that people take their public health implications a little bit more seriously. In 2024, there's one in the eastern US that's shown on the lower part of this screen. And these are not even the only record-breaking heat waves that happened in those years, just some that I pulled the screen caps out of weather forecasters, just identifying for the public how these are record-breaking events never seen before. There's a real need to prepare and be aware of this unprecedented heat. And so the question that I often get, and I often even think about myself as a climate scientist, is if you think about global warming so far, this number often pops up in the news or in other places where people talk about how much global mean temperature has changed. Now that number, if you're a climate scientist, is high. It's 1.3 degrees Celsius is our current best estimate of warming since 1850 to 1900, specifically anthropogenically caused warming. But if you just think about your kind of day-to-day weather, maybe 1.3 doesn't seem that big. And so you might ask yourself, how do we go from this kind of 1.3 degrees Celsius warming to all of this kind of record-breaking, unprecedented heat? And I'm going to kind of walk you through a story today, or a narrative today, of how to understand that mapping from our global mean temperature change to really how many of us experience climate change firsthand, which is through unprecedented, record-breaking heat. I will note before I jump into that in climate science, or in science generally, we often think in Celsius, but many of us in America feel in Fahrenheit. I certainly am one of those people. So just to map, and I'll make a few mappings throughout the talk, although not always, that 1.3 Celsius is actually 2.3 degrees Fahrenheit. So you can almost double those Celsius numbers to get an idea of what that actually is in Fahrenheit. Now, this is my most boring looking slide, but I put it up here just to note that the question of whether this warming is caused by humans is basically not a question in science anymore. So this is just a screen cap from the most recent IPCC 6th assessment report. And just to point out that it's unequivocal that human influence has warmed the atmosphere, ocean, and land. And that's, of course, affecting many weather and climate extremes. This is a global consensus report. People all around the world have to agree to this. So this is really not up for debate. So we are not going to be discussing whether humans have caused this warming, but rather understanding how to go from that warming to our recent record-breaking heat waves. Okay, so to do that, we're going to talk through basically 3 ingredients. The first one, in a way, is quite simple, but perhaps underappreciated. And that is that land actually warms more in climate change than the ocean. And most of our globe is ocean. And so therefore, land warms a good amount more than the global average temperatures. We're just going to walk through that here in a graph. What's shown here is data from Berkeley Earth. And this blue line is just the global mean temperature estimate going from 1850 to 2025. I've set it to be 0 over that 1850 to 1900 period. We'll think of that as kind of a baseline period. And you can see that this is obviously going up. But if we instead then add another line to this graph, which is how global land temperature has changed, you can see that the land is warming much more quickly than the ocean. And most estimates put that at about a 60% amplification of warming in land over ocean. And again, that global average more reflects the ocean because 70% of our planet is ocean. So as a result, I think everyone here lives on the land. And the reality is that when you think about that global mean temperature number, you have to increase it by about 60% in terms of how much we're actually experiencing warming where we live. Now, why is that? There's probably a decade or maybe a little bit more of work on this topic that's really advanced our understanding of why land warms more than the ocean. And there's two ingredients that I'll talk about right now. The first one in the schematic is if you think about land as that kind of brown block on the left and the ocean as the blue block on the right. Land has what's called a smaller heat capacity. And what that means is when you add additional heat to it from, for example, increasing CO2 concentrations in the atmosphere, it just warms up more quickly than the ocean. So that's one ingredient of why it warms faster. The larger ingredient actually is a little bit less intuitive, and that's that land also warms up more because it is inherently drier. So there's literally less water in the land than there is in the ocean, since the ocean is entirely water. And as a result, the land will warm up more in response to the same amount of heat. Now, scientifically, there are actually a few different ways to explain this phenomena, but I'm going to explain it today through the so-called surface energy balance. And the idea here is that when you add heat to a system and you add heat to the surface of the land or the ocean, the heat more or less does two things. It either goes to evaporating water, that's I have shown as these kind of little droplets, but doesn't increase temperature, or it goes into what's called sensible heat, which will increase your temperature. And a drier surface is going to have more of that heat going into increasing temperature than evaporating water. That's why I have the thermometer being a little bit bigger over the land than over the ocean. And that leads to the land warming up more. So inherently, that drier land surface leads to more warming. Okay, so that's part one, land warms more than the ocean. Part two is that we have observed a lot of global warming in the median person's lifetime. So in the United States, the median person was born apparently around 1986, according to my research this morning. And that person in their lifetime has experienced about 1.2 degrees Celsius of warming over land, or about 2.1 degrees Fahrenheit. I'm pretty close to this median age, it turns out. So that is how much kind of temperature has changed in my own lifetime. The reason I highlight this is that sometimes when we talk about global warming, you say, okay, it's happened since 1850. That was a really long time ago. This is kind of like a slow change. But the reality is that warming has been very recent in recent decades. And so for most of us, the change in temperatures just over our lifetime is really substantial. And I imagine a lot of you have an experience of, when I was a kid, it would snow much more than it snows now. Or, for me, when I was a kid, we never had air conditioning in Colorado, but now most people have installed air conditioning because the summers become a little bit unbearable without air conditioning. So we really are experiencing this change in kind of real time. And it's not gradual, it's actually quite rapid, and the changes are, relevant in terms of the lifetimes or the years that we are living. And the other part of that is that climate change is certainly not uniform across land. And so this is a plot showing changes in summertime temperature, where I've defined summer at each latitude for just the hottest 90 days of the year. So you can think about this as kind of June, July, August in the Northern Hemisphere, and December, January, February in the Southern Hemisphere, and slightly different seasons in the tropics. And this is showing how much summertime temperatures have changed since 1959 during those peak summertime periods. Now, we already talked about the average change being on the order of a couple of degrees Celsius, but that is not true everywhere. And in particularly, there's certain hotspots that really pop out as major regions of accelerated temperature change. So I've highlighted two here. One is where I live in the Western United States, and the other bigger one is really in this kind of Mediterranean region in Europe. And in this region, actually, since 1959, summertimes have warmed 3 degrees Celsius or 5.4 degrees Fahrenheit. And that is a big change. If you think about a day that used to be 95 becoming 100, we can start to see how these extreme heat waves are really explainable by the climate change that we've seen so far. Okay, so far we kind of have two ingredients. Land warms more than the ocean because it's drier and has a lower heat capacity. And then the warming is not just kind of gradual since 1850. We've seen a lot of warming in our lifetimes, and some places, of course, have warmed even more than the average. So part three is going to get a little bit more directly into my own research, which is I've always been interested in this question of whether the most extreme days in the summer are warming faster than kind of your typical or average days. So if you think about wherever you live, maybe a typical day in the summer is like 80 degrees Fahrenheit and a hot day is 95 degrees Fahrenheit. this question is getting at, have both of those days warmed the same amount? Like, is your typical day now 83 and your hot day is 95? Or does the fact that we're having all these major summertime extremes suggest that somehow the extremes are warming even faster than those typical days? And this obviously matters a lot for what we, how kind of contextualizing what we've seen so far, and also thinking about what we might see in the future in terms of these major extreme events. So in order to walk you through that, I want you to briefly put on your statistician hat, and we're going to think about climate like a statistician in terms of changes in distributions. So whether you've never taken statistics or hated statistics or hopefully love statistics, we'll just walk through this gently. What I'm showing here is a time series from just the year 1963 of daily summertime temperature anomalies in Los Angeles, which is where I live. Anomalies means that we're comparing this to basically a long-term average over about 6 decades, and also removing the seasonal cycle. And so what you can see in 1963 is that there's a lot of day-to-day variability, as we'd expect. That's our weather. And then most of these values are falling below the 0 line, meaning that 1963 was a cooler year compared to average. So what we can then do to think about this like a statistician is take all the numbers that make up that time series and put them in a distribution, which I'm showing on the bottom part. So this is basically called a probability density function, and it's just showing the likelihood of different temperature anomalies. And so the peak of that distribution is a little bit less than 0, again, suggesting this is a slightly cooler year than average. Okay, so we're gonna do the same for 2020. 2020 was a hot year. Quite unpleasant. There was a pandemic, there were fires, it was very hot. And this is showing the time series of the summertime temperatures in Los Angeles. And I want to highlight 2 things. One, 2020 was obviously warmer, but we still have weather variability. So there are certain days of the year where in 2020 it happened to be a little bit cooler than it was in 1963. And this is what we expect. Again, this is kind of the weather variability. So if we take those numbers and put them into a distribution, add them to our plot, we can see what's going on is that climate change has basically shifted this distribution towards warmer temperatures. But of course, these still overlap with each other because we still have our day-to-day weather variability. Okay, so now I'm going to show you this kind of crazy looking spaghetti plot, but what we've done here is taken every year, summer times, daily temperatures from 1959 to 2023, and I've just colored them based on the year. So some of these curves that are more purple are from closer to 1959, ones that are more yellow are from closer to 2023. And what you can hopefully see in this kind of beautiful set of colors is that there is, of course, overlap between these distributions. That's our weather. But overall, from left to right, this kind of goes purple to yellow. And that basically is climate change. And so the question that we have is more broadly, not just in Los Angeles, what is the way that climate change is altering summertime temperature distributions? So if we imagine this blue distribution as some kind of historical or past distribution, there's kind of 2 options. One, what I call hypothesis 1, is that the distributions are just shifting towards warmer temperatures, but at the same rate for the mean and the extremes. And I like to call this kind of the rigid shift mode. You just take that blue distribution and kind of just move it to the right, but nothing changes about its shape. So this would be the case I talked about before, where your typical day of 80 and your hot day of 95 both become, say, 3 degrees Fahrenheit warmer. But this still will have a large change in the probability of extremes. So this black line here just shows, I think, the 99th percentile of that blue distribution. And you can see that those historic events are going to become, historically hot events will become much more likely, even with this kind of behavior. But there is another hypothesis, is climate change is causing kind of more complicated changes in the shape of our distribution. So in this case, the red one is both warmer and also wider than the blue one. And this could lead to a very large change in extremes. And so we really want to be able to distinguish between these 2 types of shifts to understand, what we can expect for our summertime temperature extremes. So there is kind of a physical reason to think about this well, in addition to the statistics, is that there have been various physical mechanisms that have been proposed for so-called amplification of extremes, by which I mean that the summertime heat extremes warm more than your typical summertime temperatures. The first one is a change in atmospheric circulation. This one actually is talked about a good amount in the news, so you might have even heard about it, in whatever news source you have. But the idea is that in this picture, all of those brighter colors are showing our mid-latitude jet stream. And when you have those big wiggles in the jet, those tend to be associated with extreme events, either heat waves or major rain events if it's a high or a low. And people have proposed that there's actually changes in kind of the wiggliness of this jet that should lead to more extreme summertime temperatures. On the other side, people have looked at how the land and the atmosphere interact. And this is kind of similar to the land ocean stuff I talked about before, where there's this idea that your hottest days tend to be dry. And so therefore, when you have additional heat on those hottest days from increased CO2 concentrations, more of that heat might lead to increases in temperature. So this has been another mechanism proposed in order to say that maybe we expect these heat extremes to warm more than a typical day. So the question that I had is, what has actually happened? What have we actually seen historically? So I'm going to show you one result from a recent paper here, but before I do, I just want to contextualize what you're about to see. So once I uncover this mystery map, what you will see is a global map, more or less with two colors on it. Any place on the map that's shown as red is a place where we found that the hottest summer days are warming faster than the average summer day. And anywhere as blue is a place where the hottest summer days are warming less quickly than the average summer day. So maybe in the chat, you guys can start a betting pool of what we're going to see. I don't know what the chat is saying because I can't see it right now, but you can start guessing. But as you do those guesses, I just want to emphasize that we're going to be thinking about trends in summertime extremes relative to trends in the summertime average. So I showed you this map before. This is how summertime average temperatures are changing. So your kind of typical summer days. Remember, this is red or positive almost everywhere. So if you see blue on the next map, it's not that summertime temperature extremes are cooling. It just means they're warming less than that average, which is warming in a positive way everywhere. Okay, well, hopefully you've wrapped up your betting pool by now. I'm going to uncover this plot to show you what we found, which is shown here. So this plot is kind of red and kind of blue. There's not a whole lot of consistent signal across. Some places seem to have a little more warming of the extremes, some places a little bit less. And when we went and did the statistics pretty carefully, we more or less found that there wasn't a meaningful or significant amplification or damping of the summertime temperature extremes compared to the mean. And so what that means is that we can go back to this kind of estimate of how mean temperatures are changing, and summertime extremes are following that pretty well. Or in other words, going back to our distribution plot, this supports hypothesis 1, where we can basically think of our historical temperature distribution, warm it the same amount everywhere, and that's how we can understand, for the moment, climate change. I will mention that our climate models suggest that this will hold going into the future for the northern hemisphere, but not the tropics. So in the tropics, our climate models do project that we will eventually see amplification of those heat extremes, which is something to be really cognizant and aware of and concerned about, because the tropics, of course, are already very hot, and it's a place where heat can be especially detrimental to human health. And then I finally want to emphasize on the science side that even though we're not seeing this quote unquote amplification of the extremes, we are still seeing big changes in our extremes due to this behavior of everything just shifting to warmer temperatures. So what this map shows is places that have had their hottest summertime temperature since 1959 in a recent 5-year period. So I didn't have time to update this with 2024's data, but looking at what happened from 2019 to 2023. And anywhere that's red is a place where that location has had their most extreme summer over this period and basically the last 5 years. And there's a lot of red on this plot, the Western US, France, really all over the world, you see red on this plot popping up. And that's really in contrast to if you do the same exercise and ask in the first 5 years of that period, 1959 to 1963, there are very, very few places that had their hottest year. And so this kind of shifting of our summertime temperatures is very directly leading to these record-breaking extreme events. And then I finally want to finish here with the idea that the climate may be behaving what I'm calling linearly, meaning our extremes on the summertime don't seem to be doing anything too unexpected. They're more or less following the median for now. But the impacts of a lot of climate extremes, and especially heat extremes, can be highly nonlinear. So I could pull up a number of different examples, but the one I'm showing today is the impact of temperature on heat-related mortality. So these are plots that epidemiologists produce. This is not my field, although I'm familiar with their approaches. And what's shown here is on the x-axis is temperature. On the y-axis is relative risk of heat-related mortality. So a number of 2 means that a population is twice as likely to have a death related to heat, when you have a heat wave compared to when you don't have a heat wave. So that's a pretty big increase in risk. And these curves look a little bit different depending on where you are. So this shows Sao Paulo, Paris, and Bangkok. But the important thing to notice is that when you get to that right-hand side with these hotter temperatures, all of these curves go up very, very steeply. And so if you imagine, taking this dashed line, the vertical one in all of the plots is showing the historical 99th percentile of summer temperatures. And we're talking about places like Europe, for instance, warming, 3 degrees Celsius over summer just over the past 65 years. So if you kind of, take that Paris line and move it to the right 3 degrees, you have these huge increases in mortality, assuming there's no adaptation. We, of course, as humans, we will adapt and we do adapt, but nevertheless, there is this major, major human health impact of heat that is highly nonlinear. And that's why even if we, are warming 3 degrees Fahrenheit, 4 degrees Fahrenheit, that can still have a huge and obvious human impact measured by a number of things, including, unfortunately, mortality. Okay, so that's most of what I'm going to talk about today. I just want to end with 2 more slides, zooming out a little bit on the bigger picture. So what I showed you today was kind of one subset of work that myself and my group of my collaborators have done on heat. But we do a lot of other things too, and some of it is also about heat. So I'm just pulling out kind of 3 different studies that we've done, also connected to heat that I didn't talk about today. They got a lot of public interest because starting in the left-hand corner, we identified that you could use the state of the Pacific Ocean to get long lead, up to 7-week predictability of US heat waves in the Midwest and the Eastern US. And this is kind of an exciting advance because we haven't really known otherwise how to get more than, say, 7, 10, maybe 14-day predictions of heat. On the upper right-hand side, we identified that in addition to temperatures increasing, in the Southwest, humidity has actually been decreasing, which is a major concern for our fire seasons out here in the West. Hot and dry conditions are 2 out of 3 of the components of red flag days, wind being the other one, that can lead to these kind of rapid spreads in fire. So that was another kind of important contributor to understanding how our climate is changing. And then in the middle on the bottom, we did a study on that Pacific Northwest heat wave I mentioned at the beginning, just trying to understand not only what was the contribution of climate change, but also what was the role of internal variability. And we found that this, even after accounting for climate change, was probably a pretty unusual event. That's good news. Hopefully we won't have something quite as extreme in the near future, but helped us understand how to kind of contextualize that event. And then I've now added to these plots, these images, indications of funding. So each one of these projects was funded by the National Science Foundation. That one on predicting heat waves was also funded by NASA, and they would not have happened if we had not had those funds. The Pacific Ocean Heat Wave Prediction Project was actually part of my PhD work, and that was funded by graduate research fellowships that allowed me to then kind of have the freedom to do my work and kind of led to the career that I have today. And then finally, as a last slide, I just want to end just really emphasizing the people. So I joined UCLA in 2018. I call my lab the Climate Statistics Lab because we actually span atmospheric science and statistics. And I bring in people from both of those backgrounds together to solve cool problems in climate science. So these are most of the faces of people who have been in my lab, ranging from undergraduate students to masters to PhD to postdocs. And you can also see on a lot of these pictures, the NSF logo again pops up pretty clearly. These are people who all are part of their work with me was supported by the National Science Foundation. Also one postdoc there has the NOAA logo. She's supported by a NOAA postdoctoral fellowship. My own work has been supported by NSF, NOAA, and the David and Lucille Packard Foundation. But the important point I want to make here is in addition to the science that we've talked about today and advancing that science, federal funding supports people. And in fact, since I don't run a lab, I just use computers, and these days computers are pretty cheap, almost all of my money supports people. And so these are the people who have benefited from the federal funding supporting my lab, and they've gone on to do a wide variety of things. So, one of them is professors, some of them are researchers, many of them have gone into the private sector and used their kind of technical, quantitative, complex system thinking skills to make advances really in a range of different industries. And so I want to end leaving their faces up here. I will mention that that's my website on the site as well. That QR code will also go to my website if you want to learn more about our work. And I'd be happy to engage in a discussion with any of the folks here. So thank you so much for your time.
Thank you so much, Karen. That was amazing. And I love that you ended by highlighting all the people that you work with. I think that's so important to remember that these grants from these different agencies aren't just going to funding, collecting all the observations, funding the satellites that are in space, funding the balloons we launch, but they fund people who are doing this work. And that's what it's all about. So I hope during this live stream, you guys are really appreciating getting to meet a lot of the people, a lot of the scientists. And yeah, folks really loved your talk. I really loved your talk, and there was a lot of enthusiasm in the chat. People were reminiscing on snow days of their childhood, and there was a lot of voting about what that map would look like. I think the consensus is almost everyone got it wildly wrong. Everyone thought it would be red. And so maybe we'll start with a question. Someone had a really interesting hypothesis about what the map would look like. They said, I think it's going to be red, but maybe it will be blue in places that have higher humidity. So I'm wondering, you mentioned this a little bit. Can you talk about extreme heat and its connection to humidity?
Yeah, so maybe I'll kind of riff off that hypothesis and also bring in the humidity component, which I hadn't really talked about too much. So yeah, I think that hypothesis is great because it was basically based on some of the other stuff I presented that said places that have more moisture, which over the land surface can be kind of often measured by how humid it is, that they have more ability to partition some of that heat into increasing humidity as opposed to increasing temperature. And certainly we were kind of surprised that we didn't see that strong imprint in the data, and we're still actually doing work, also funded by the National Science Foundation, to understand specifically, why don't we see that? Is it because there's other processes that counteract that process? So the climate system is never just one process. It's always lots of things going on at once. And so are there other things that are kind of counteracting that expectation? So I think we still need to learn a lot more. We just answered the question of what are we seeing, but we haven't quite answered the question of why are we seeing it in its entirety. But yeah, I do also want, since you brought up humidity, talk about humidity a little bit as well, because the health impacts of heat do depend heavily on humidity, and that's been shown primarily in physiological studies. And I think that almost anyone here who lives in a hot, humid place, or whoever has, you can kind of know that intuitively, that when you go out and it's hot and really humid, it's hard to cool your body down. Your sweating is less effective because you're not evaporating that sweat into that high humidity condition. So yeah, I, in my own lab, have actually not done a ton of work on the hot, humid conditions. The one that I showed here actually tried to look at the other way of how is the humidity changing on dry days with connections to fire weather. However, what we do know is that in most parts of the world, particularly parts of the world that are already pretty humid, warmer temperatures are associated with increases in humidity. And this is understood at a relatively basic physical level because warmer air can hold more moisture. And so assuming you have enough moisture available, as those temperatures increase, you do get higher and higher humidity levels. And in most parts of the world, we do see that in the observations. We interestingly don't see it as much in the drier regions, and we're trying to understand why right now. That's a really active area of research in mine, some other folks' groups. But in terms of the health impacts, those places that are already humid, that's where we probably care about it the most. And those are getting more humid. And this also is associated with increases in extreme precipitation, because as that air can hold more moisture, when you eventually do let out that moisture and precipitation, there's just a lot more moisture to release. And so these so-called thermodynamic changes of climate change, so increases in temperature, increasing in humidity, increases in extreme precipitation, are really those components that we understand the best and where there's a very, very clear and well understood imprint of human influence on the climate.
Mm-hmm. Thank you. Yeah. Maybe we'll jump to another question that is somewhat related. Someone was wondering about these dry regions. So they said, speaking of the Western US and the Mediterranean zone in Europe, does this change in extreme heat have implications for the chaparral biomes? So this warmed my heart as a former LA resident. We love our chaparral. And then they wanted to know, is there something tying this specifically to the Northern Hemisphere? Is there something about the jet stream? People were making great hypotheses in the chat about some atmospheric dynamics going on. So yeah, I wanted
Awesome.
to talk about the biomes.
Yes, and Claire, I didn't know that you were from LA, and I think the word chaparral did not enter my lexicon until I lived in Los Angeles. So that makes some sense. Yeah, I don't know. I'm not an expert on the chaparral biome, so I'm probably not going to give you a very satisfying answer, except to say that certainly I've mostly interacted with the chaparral scientifically in terms of fire risk in this region. In general, of course, these warmer and drier conditions are associated with drying out that vegetation and leading to increased fire risk. With the chaparral specifically, interestingly, likely because it's already pretty warm in, for instance, Southern California, we do tend to see a stronger moisture, so precipitation signal in terms of year-to-year variability and fire risk in burned area than we do in that temperature signal. And again, my guess is that that's related to the temperatures already being relatively warm. So I think that I don't know the implications for temperature directly, but certainly thinking about the role of fire in these warmer, drier conditions. And in terms of the Northern Hemisphere jet stream, I think that the role of atmospheric dynamics in having any kind of amplification of these heat extremes, I think that we still don't know. So again, there have been hypotheses that have suggested this to be true. They're not necessarily widely accepted, and we don't yet see any observations. But that could, again, be because there's different things that are kind of, counteracting each other and acting in opposite directions. So even though I sometimes say, heat seems so obvious, it's just a temperature, just thermometer, it's so basic, there's actually a lot that we don't know about heat. And that's because heat results from the interaction of so many different processes. So it's not just the atmospheric circulation, it's also going to be, again, that interaction with the land surface and how those two feed back on each other.
Definitely. Great. Thank you so much. I'm going to jump to a very different kind of question. Someone wanted to know about adaptation measures, and they asked, is Paris one of those European cities that didn't have a lot of AC because they typically didn't need it before? And is that what maybe is related to that increase in mortality that you showed?
Yes, so I think that Europe has been a kind of really good example of what happens when you don't preemptively adapt, but then my understanding of how that has changed. So there was the 2003 European heat wave, which was just this major kind of extreme heat wave, and I think the estimate is that it killed on the order of 70,000 people or something like that. It was really, really detrimental. And a lot of that was linked to people who lived, I don't know if folks have been to Europe, but you often have, apartments maybe up in the attic. They're not necessarily well circulated. You don't necessarily have AC. So this is not my field, but my understanding is just someone who studies heat is that, that really large impact in Europe was strongly related to how people have built in the past and the lack of adaptation and kind of adding AC to those building environments. And I think that has, changed in Europe. It certainly is changing quite rapidly in the US. So in the US, California is basically the place that tends to not have air conditioning across the US, while also the Pacific Northwest. And then these are places where the mortality curve tends to peak a little bit at, cooler temperatures. Cooler, I mean, still heat waves, just because people don't have that AC, but people are, making that adaptation now. But I think it's a really tough one from the climate science perspective, right? Because I certainly don't want people to die in heat waves. So, certainly get AC, and it is not worth someone's life to die in a heat wave instead of having AC. But nevertheless, as we know, AC is bad for our climate. And so there's kind of this interesting feedback loop where we certainly need to adapt, but that adaptation, depending on how we do it itself, can also, cause more climate change. And so I hope that we can, as a society, continue to think about how do we make sure that we adapt, that people have what they need, that they can be healthy, that they can be safe, but at the same time, fundamentally changing where we get our energy, how we cool buildings, things like that, in order to not itself, add too much to that climate, the climate change itself.
Yeah, thank you. I think we have time for one or two more questions. I want to take a question from Chris, who definitely put on his statistics hat as you encouraged. He said, I've heard it said that increase in frequency of extremes increases predictability overall. Is that true? Can you explain why? Is it math, observations, or something else?
Cool. Great question. I don't know exactly what's being referred to here, but so I apologize if this does not answer the question that you had in your mind. But yeah, certainly if you think about what allows for predictability in the climate system, there's these different timescales we have to consider. So, we have kind of the weather timescale where we have gotten super good at that. We pull out our weather app. We basically know what the weather is going to be. But after 14 days or so, that predictability tends to fall off. And then we have this kind of so-called predictability desert going towards longer timescales. But as you go to even longer timescales and or make climate change a stronger signal, then you have what's called boundary condition predictability, where basically the fact that the whole system is getting warmer means that it's easier to predict those kind of longer timescales. So, I could give you some probably reasonably good probabilistic estimate of whether or not your location would have a record-breaking extreme, over the next 10 or 20 years, simply because our climate change signal is strong. And so we're just shifting these distributions towards warmer and warmer temperatures. So I don't know if specifically, in some cases people have found more on the weather side that certain extreme events are more predictable than typical weather. But on the climate change side, certainly having everything get warmer, ironically makes things more predictable because we can say pretty confidently that they're getting warmer.
That makes sense. Yeah. Let's take another question. Okay, someone had a keen eye for your map. David wants to know, why was South Australia experiencing a reduction in temperature? I think it was like that one little blue spot.
Yeah, so this is referring to the change in mean temperature plots. Almost everywhere is warming, but not 100% everywhere. In most cases, we view that as internal variability. So one kind of fascinating and challenging thing about studying our climate system is that even without climate change, it would be interesting and complex because the climate system itself produces extreme events, would produce trends, would produce all types of complex behavior, just because you have a chaotic fluid of the atmosphere and the ocean interacting with the land surface. It's just a really cool system by itself. And then we've added climate change on top of that complexity. And so when we look at things, even multi-decadal trends, you might think at that point, this is just a climate change signal. But once you get regional, so once you get to this question on Southeast Australia, you actually do have an increasingly large contribution of internal variability. So I didn't talk about those types of things at all today. That's actually the other major core kind of theme of my work. And that itself is also really important. So if you think about planning for our future, we need to know not only what that climate change is going to look like, but also what the range of conditions are that we could expect just from sampling that natural variability of the climate system itself. So that's likely what happened in Australia, although I'd have to probably write a paper to know that for sure.
Awesome. There's one question from Itty Bitty Nautilus, I like their handle, that's about the internal variability as it relates to the weather we're having right now. So they say there's been an unseasonable cold snap in the mid-Atlantic US. I'm in New York right now. I can confirm the last few weeks have been very cold and rainy for May. Is it climate change or is it this internal variability? Do you know what's happening right now?
I don't know. I'm sitting in California at 70 every day. But this is probably just weather. So we kind of have this kind of weather to climate continuum. And just like I showed with those Los Angeles summer temperatures, even with climate change and a warmer year, you can still have colder days when the clouds come in or the weather systems come together in a certain type of pattern. And so again, this is kind of this natural complexity of the climate system produces all these weather patterns, including ones that seem unexpected. But climate change, you can really think about as asking the question of, are these patterns changing in a systematic way that we can really understand as being due to human influences? So that attribution is a little bit easier for heat because everything is kind of moving towards warmer temperatures. When we think about cold snaps, or this is probably a cold snap caused by a certain atmospheric circulation pattern, that's the bigger challenge for climate science, actually, is understanding if there's a climate change signal in these so-called dynamical changes. But like I said, you could always dive in further to any of these questions. My guess is that it's internal variability, but these are important questions to keep thinking about.
Excellent. I think we're rounding up on the end of the hour, but I think we will thank you, Karen, so much. Thank you to everyone for asking so many great questions. It's so amazing to see people engaging with science. It makes me happy. And that was just a great talk. I learned so much. It was great to have you on.
Claire. Thank you for all the work that you're doing, and I'm excited to see the rest of the live stream.
Excellent. Okay, well, I think we are entering now hour 31 of our 100-hour live stream, and this is concluding my session now as your host. Thank you, everyone, so much for having me, letting me ramble at you from my living room. And Mark will be coming back to take over in a minute. Here he is.
Hello,
Mark.
Hi, Claire. How was the talk? I'm sorry, I missed the 45 minutes.
The talk was so good. People were very enthusiastic. Karen had a little poll going on. She had everyone vote in the chat what they thought the plot would look like, which was very engaging. I loved it.
Oh, that's awesome. I always get those questions wrong. I'm always
Everyone got it wrong. I got it wrong in my head too. It was unexpected. She said that her research group got it wrong too when before they looked at the data. It was not what they thought it would be, which is always a fun science story.
Love that. Cool. Well, I think they're figuring out the slides right now.
Okay, good.
And I guess I could just go over the why we're here. And Claire, I can relieve your duty. Thank you so much for hosting. Let's hear it for Claire in the chat.
Okay, thank you, everyone. Thank you, Mark. And I will be back on Saturday morning.
Nice.
So tune in then.
See you then, Claire. Bye. All right. Hello, everyone. Thank you for joining the 100-hour-long live stream to save America's forecasts. We have an exciting lineup. You just heard an excellent talk from Dr. Karen McKinnon, and we started the keynotes earlier in the evening. If you're just joining, we started the keynotes about 2 hours ago now. We had an excellent panel of the current American Meteorological Society president and also the president-elect. So one was a Penn State professor in the Department of Meteorology and Atmospheric Sciences there. And then the other is Alan Seals. He's a broadcast meteorologist. He's actually kind of TikTok famous, or went viral during his coverage of Hurricane Irma in 2017. So I'm sure you guys are familiar with Alan Seals. And last night, of course, we heard from two excellent panels: the terminated NOAA employees, terminated NOAA scientists who were laid off in the latest round of cuts and firings, and also the forced early retirements. And we also heard from two former National Weather Service directors. All right, so yeah, thank you all for joining. We are entering hour 31, as Claire mentioned, which is very exciting. And we're going to continue with our keynote talks. But first, before we begin, we just want to remind you why you guys are here. And that is really just so we as meteorologists and climate scientists can communicate what we do. It's to raise public awareness about our research, our forecasting, and why that is being affected by the cuts. We need NOAA, we need the National Weather Service, we need the National Hurricane Center to be fully funded, so that we can continue doing the research. You know, a lot of stuff is going on behind the scenes, right? We're just researchers. We're normally at our computers, doing all the coding behind the screens, doing the data analysis, and things like this. And of course, there's a large part of the community that's out there forecasting all the time at the National Weather Service and the National Hurricane Center. We rely on their life-saving forecasts. And right now, those National Weather Service offices are understaffed as part of these cuts and these layoffs, which could, of course, endanger many American lives and livelihoods. So that's part of the reason we're here today. Great. So I'm just making sure we have, we're ready for our next presentation. Just checking the things going on in the background. But yes, just another, why are we also here? It's just a reminder of the fact that we have invested in the weather and climate prediction infrastructure in the United States for decades, right? I mean, many people don't know this, but in the United States, we invented the first computerized weather forecasting model, the first computerized climate model in the 1950s and 60s. And since then, we've been, you know, a leader in this science. So yeah, so that's why we're here today. And it's so nice to see all of you engaging in the chat. That's really awesome. And please remember to ask questions during the talks, and we will star them for you. And we will try to answer as many questions as possible after the talks. All right, so our next talk is, let me just pull up my notes. Our next talk is by Dr. Maria Molina. We're going to bring her on screen, I think. She is with the, hello Maria, thank you for joining us.
Hello, thanks for having me.
Of course. Her primary affiliation is with the Department of Atmospheric and Oceanic Science at the University of Maryland College Park, where she is an assistant professor. She is also an affiliate faculty member with the Artificial Intelligence Interdisciplinary Institute at Maryland and the University of Maryland Institute for Advanced Computer Studies. She is also very involved in the community. She serves as vice chair of the American Meteorological Society Committee on Artificial Intelligence Applications to Environmental Science. And she serves as a member of the World Climate Research Program Scientific Steering Group for the Earth System Modeling and Observations Core Project, among many other things, including working for the U.S. CLEVAR Predictability Predictions and Applications Interface Panel. That sounds exciting. So Maria, we're so happy to have you as a keynote speaker tonight. And I'll go ahead and let you take it away.
Thank you so much for the opportunity to speak with you and with everyone that's watching from home today, whatever time zone you are in. I'm excited to talk about the work that my research group does at the University of Maryland that focuses on the use of machine learning, or more broadly, artificial intelligence for Earth system prediction and predictability. But I did want to share a little background on myself, because before becoming an assistant professor, I actually had a different career. So I spent about 6 years as a broadcast meteorologist on national cable news. The channel I worked for was the Fox News channel, and I got the opportunity to travel across the country as a meteorologist, not only forecasting extreme events and turning to the NOAA National Weather Service to share many of the warnings and watches that were being issued for extremes, but also seeing these events firsthand. And so on the top left-hand side of the screen, you can see me standing out in Buffalo, New York. This was one of the events that we covered, where there was a record set at that time. This was back in 2014, November, for 5 feet of snow. This was a lake effect snow event. And if I were in person, I would tell you that I'm 5 feet tall. And so that's how much snow came down in this region. Since then, that record snowfall has actually been broken. So we've already seen even more extremes since that event that I got to witness firsthand. On the bottom left side, it's me traveling across the country with other media folks that were covering a number of extreme events, including tornadoes that impacted portions of Mississippi, Arkansas, and also Alabama. And so I'm actually showing some of the devastation firsthand. And as a broadcast meteorologist, I also got to experience some more of the social aspects regarding communication of extreme weather events and also climate, where I learned that while it's really important to be there for the public when you are experiencing extreme weather or when extreme weather is expected, when extreme weather is not expected and when things are good, we actually really need to build trust with our communities. And so at that time, when weather was good, I would actually do some fun pieces, like in the top right-hand side, it's me flying on a Blue Angel flight and talking about the science of experiencing G-force on our body without a G-suit. And of course, the Blue Angels love to have any of the people they take on these flights pass out or undergo very uncomfortable situations to poke fun at ourselves. And then we also got to share with the public during my time at the Fox News Channel how we actually have weather testing of vehicles take place. This was me in Detroit, Michigan at the Chevy plant, where we actually got to put me inside some of the weather testing that vehicles that we all drive have to undergo before hitting the roads for our own safety. And while my time as a broadcast meteorologist was just a lot of fun and I learned a lot, there were quite a few extreme events that continued happening, and questions like, is this the new normal? Are we going to see more extreme events? Or why were there so many extremes that specific year? These questions kept cropping up, and I felt like I didn't have the scientific training necessary for some of the answers to these questions that I was facing. My training was primarily as a meteorologist on extreme weather. That was what I loved. And so I actually went back to grad school to learn a bit more about climate variability and climate change, some of the topics that you just heard our last speaker talk about. And some of the things that really stood out to me during that time was that while we know that the global average temperature is increasing, we know that we have more moisture in the air as a result of warmer temperatures, what we experience firsthand does vary quite a lot more. And these long-term trends that perhaps when you're looking at a global average seems like a very small signal, it is quite robust when we're thinking about the impacts that those signals mean for us on the ground. And so here I'm sharing an example of Ida that made landfall several years ago across the Gulf Coast in Louisiana. And this storm remained a Category 4 hurricane for about 6 hours after landfall, which is just absolutely incredible. And not only did we look at extreme impacts along coastal areas, but even much farther north. This is in the New Jersey area. This is Jersey City, an image from Getty Images of the flooding that was left behind by the storm that produced so much rain during rush hour. And so there were lots of people stranded on their way home trying to just, end the workday and go home to their families. And they encountered a lot of heavy precipitation so far away from where the storm made landfall. So these are the impacts that we're talking about on the ground when we are thinking about climate change. And they can be so varied across so many different locations. And we still have so many outstanding questions on some of these extremes that we're going to be continuing to experience here in the coming decades. So my path particularly was quite windy, but many of these lived experiences as a child, growing up in Florida and experiencing storms like Hurricane Andrew, having a weather and climate background, and eventually getting to conduct research at the US NSF National Center for Atmospheric Research Center in Boulder, Colorado as a postdoc, and eventually a project scientist really led me to where I am today, where I get to work with a set of graduate and undergraduate students and postdocs that have so much enthusiasm and knowledge already that they bring with them and creativity to tackle some of these outstanding questions on weather and climate. And what's really exciting about where we are right now is that not only do we have these questions about extreme weather and climate, but we have so much awesome technology that we get to leverage, specifically when we're thinking about deep learning and neural networks, to answer some of these questions and use big data to look at some of these applications that we are interested in. And so training the next generation of scientists at this intersection requires time, requires investments, and requires persistence and continued training of these people, because it takes years to gain that expertise at the intersection of these domains so that we can continue to lead in this space of weather and climate. And so my group broadly focuses on the topic of Earth system prediction and predictability. And I did want to note that there is a distinction between those two terms. When we're thinking about prediction, we're specifically thinking about the forecasts. So for example, the forecast you get from the NOAA National Weather Service. But then as researchers, we also sometimes like to think about predictability, where, for example, what if we didn't have errors in our models? What would be the inherent upper limit for possible skill in our predictions? And so here we're thinking about chaos and simply the system. How predictable is it on weather timescales, and also what are the boundary conditions that we can consider when we're thinking about climate change? So these are just two terms that have a lot of similarities, but there is some small nuance there and difference between them when we're thinking about prediction and predictability. So I wanted to make that clear. And you'll also hear a lot of words that get used interchangeably when we're thinking about AI. And I wanted to note that there is somewhat of a hierarchy of terms here in terms of their scope. So when we're thinking about computer science, that can entail anything from hardware for computers, that can entail development of chips, and so many other topics. And part of computer science is AI. And so here we're thinking about not just our models that can do skillful things with data, but even the theory of AI. Like, for example, what exactly is intelligence? Then we can go a level more specific when we're thinking about machine learning. And machine learning is not a new topic. It was defined back in the 1950s. And the definition that one of the many definitions they gave the field then was that this is the idea that if we give data to computers, they can learn to do tasks without us explicitly programming them to do those tasks, which is extremely valuable for a number of reasons that I'll share here shortly. And then when we're thinking about deep learning, that's a subset of machine learning where we're still giving a computer data to learn from, but now that underlying algorithm is a neural network that has neurons, numerous layers, and can learn this information and perform tasks hopefully skillfully. And machine learning and deep learning have a rich history. These are, again, not new topics. As I showed earlier, we have machine learning defined back in the 1950s, but over several decades, we've had a number of advances and also somewhat setbacks where, for example, in the 70s and 90s, there were a lot of unmet expectations and reduced enthusiasm for AI. And so we tend to call those AI winters and periods of reduced funding where there was just less progress being made, I guess, or just some hesitation in the field on AI advances. But in between that, we had also a lot of advances. We had the backward propagation algorithm or backpropagation algorithm developed and really not only introduced, but sort of established, which we even use today. We've had expert systems get developed. And really in the most recent decades, there's been this confluence of a number of different factors that have come together to build this environment or put us in this environment where we've been able to do so much with deep learning. And some of those advances have included the availability of very large data sets, thanks to the internet, thanks to social media, thanks to folks uploading their data into these shared servers and systems. And so that's really enabled us to have large data sets that we can give to these data hungry models. There was also work that was done by a number of folks at universities, including at Stanford, where graduate students labeled a number of photographs and outlined or labeled when there was a dog in the photograph, a cat in the photograph, and those sorts of labels are what were so useful for training our machine learning models, because now we can give these deep learning models examples of a photo of a dog and we have a label telling it that that's a dog. And so now it can learn to make these associations without us always having to provide those labels. But also the development of GPUs, or graphical processing units. And so that is a chip that essentially allows us to parallelize the training of these neural networks much more rapidly. And also the availability of very large communities that have enthusiasm for developing open source software. And so things like TensorFlow and also PyTorch that initially started out in private industry have been opened up to the community and have enabled folks to take software that it has already been built, been vetted, people find bugs and fix them, and we can take those advances and use them and contribute back to these rich software ecosystems to continue making advances. But for the physical sciences, we don't always have a lot of data. And I know that seems somewhat of a misnomer, because if we think about remote sensing, for example, satellite-based instruments that record data, those are very large data sets because we have data across potentially the full disk or a very high resolution when we're thinking about polar orbiting satellites. And then we also have in situ stations, weather balloons that get deployed by NOAA, National Weather Service, amongst a number of other types of observations. But we don't have them all deployed equally. We've had updates to instruments which create these discontinuities in our data records. And how do we encode that information for machine learning? That can get pretty complicated. And so, yes, we have a lot of data in some domains, but we also don't have a lot of data in other domains, or there's discontinuities in the data that makes it tough to use when instruments get updated over time. But if we do have a lot of data, we can pretty easily work in an environment like where we can use a neural network to train it to perform a task quite skillfully, because it's got lots of examples to work from and learn from. But when we have smaller amounts of data, we have other types of machine learning models that we can work with, such as, for example, symbolic regression, which we refer to as equation discovery. That tends to work quite well when we have smaller data sets. And also tree-based models like extreme gradient boosting, which a PhD student in my group has used quite successfully, and I'll be sharing some of his results coming up in a few slides. But we can also train in a space where we have a lot of data, and we can train a neural network to perform a task, and then we can take it to a scenario where we don't have a lot of data and continue updating its weights, either through transfer learning or meta learning techniques. And so there's just a lot of research here just on this slide that we can talk about, and we can probably spend weeks on. In fact, I teach a course on neural networks for the physical sciences, thinking about these techniques and how we can make our models robust to different types of data availability environments and so forth. But when we're thinking about modeling for weather timescales, so let's say I want to look at the NOAA GFS model and what goes on behind the scenes when we look at model output for some specific prediction. We can think about the physics-based model running forward in time in 3 different stages. So before the model even gets run, when we're thinking again about like traditional physics-based modeling, whether it's weather or climate, we would have to create some initial representation of the system. And so that might entail assimilating a number of observations from weather balloons, in situ weather stations, remote sensing, perhaps ocean sensors, and so forth. And the more data we have, the more robust of an initial state representation we can have. And that can potentially already put us in a better scenario to move forward and hopefully create a forecast that's most skillful. The farther we are from what actually is that initial state, the higher the potential that we're going to create a forecast that has errors as we go forward in time. But for this input stage, once we have that representation of what conditions are on a grid to start with, then we go ahead and run the physics-based model. This will entail the use of high-performance computing to be able to run a global numerical weather model at a resolution that's needed for whatever phenomena we're interested in. And at subgrid scales, we can't explicitly model everything. For example, when we think about clouds, there are microphysical processes that are occurring at the subgrid scale that we simply cannot explicitly compute. That goes also for chemistry and a bunch of other processes. And so that gets handled by the use of parameterization schemes or physical parameterization schemes that essentially are sort of like approximations for what's happening in that grid cell based on a number of different rules. And some of these parameterization schemes most recently have also been created using machine learning. And hopefully that is giving an accurate representation of what's happening at that grid scale and provides useful information to its neighbors to model forward in time. And then eventually we get to the output stage where we're done running the model forward in time. Maybe we ran it for out to 10 days, 2 weeks, maybe at the subseasonal scale, we cared about forecasts out to 3 or 4 weeks into the future. And then we can actually take that information and consider things we're interested in, like temperature, precipitation, or maybe further translate that information to stakeholders that may need that information in another format to be able to use it for certain applications. And for machine learning, it turns out machine learning is quite useful for any of these 3 different stages. So for example, for that initial state where we are assimilating some of these observations onto a grid, we can use machine learning to create more skillful representations of that initial state. Can also try to use machine learning to determine where we could get most value for a sensor, whether that is for weather or climate timescales. When we're running a model forward in time, we can also do things with machine learning like online bias correction, where we can train a machine learning model to learn what are some of the issues that our physics-based model has, and it can try to correct some of these issues as it's running those equations forward in time. And physical parameterization schemes can, of course, also be trained with machine learning to hopefully result in either a more skillful representation or make it cheaper to run those parameterization schemes. And then at the output stage, we can also use machine learning for different tasks, including things like downscaling or making the resolution of our global grid or regional grid sufficiently fine enough that it's useful to a stakeholder at the end of the day. We can also use machine learning for things like offline bias correction. So maybe I ran my physics-based model out to 3 weeks. I know there are some systematic biases. My machine learning can learn those systematic biases and then try to correct them. But there are so many different types of ways that we can use machine learning in each one of these stages. And most recently, we've seen a lot of buzz on the use of machine learning to completely bypass that traditional 3-stage framework, where we can actually start at the input stage and use machine learning to either auto-regressively run forward in time out to some output we're interested in, or even skip altogether that time step modeling framework and simply start at an input and end up at an output, a lead time that we are interested in. And a couple of years ago, the cover of Science was featuring a advancement by DeepMind, or led by DeepMind, for GraphCast, which was an AI-based, or is an AI-based global model. Since then, we've seen continued advancements and push on this use of deep learning for forecasting weather at global domains and in the weather timescale, or even longer timescales now. So it's been quite exciting to see this, but this work doesn't happen in a vacuum, right? AI is only as good as the data that it gets. So we need to continue to collect very high quality observations around the world to be able to inform our models, our AI-based models, and create skillful forecasts globally. And so that involves, at least over the US, seeing what is upstream of the US, what's coming our way. And we also need to know what's downstream of the US. What is, for example, happening over the Atlantic? Is there a high pressure that's sort of slowing things down and blocking things from rapidly progressing across North America? And so again, these observations are absolutely crucial for skillful forecasting and also for training AI-based models and trying to ensure that we don't have any gaps in our data. And so now I'm going to go ahead and give a couple of more specific examples on how my group is using machine learning for extreme weather events and also for climate applications. And I'm going to kind of go rapid fire here at the end with some examples on unsupervised and supervised learning applications. And I'll explain what that is coming up shortly. But one of the questions that we do ask about machine learning is, if I train machine learning in a certain regime, so for example, if I train my machine learning model using data from 20 years ago, and now the climate over a certain region has changed, will this machine learning model be skillful, especially when we're thinking about extremes, perhaps an extreme event that's never happened before, it wasn't in its training data set, and is it still going to be able to do that skillfully? So that's one of the questions that my group asked, and I'll share results now on that project, which was peer-reviewed and published a couple years ago. But something that we were curious about was training a convolutional neural network. At that time, this was just several layers deep and essentially performed a very simple task of classification. It would look at a thunderstorm from numerical weather output. This was created using the weather research forecasting model at kilometer scale. So it would look at a storm from that model and say, is that storm strongly rotating, or is it not strongly rotating? And so this is an important task done often by weather forecasters that are forecasting severe weather, because strongly rotating storms have a higher potential for the production of things like tornadoes or large hail or damaging winds, which are significant impacts for us on the ground and can cause quite a lot of damage. And so we were curious about, if we trained a model to do this task and it could do it skillfully in a current climate, could it still remain performant in a future climate? So could it remain just as skillful in a future climate? And when we did this task, it turned out that the answer was yes, it could remain skillful in a future climate. But in this case, there's a very important caveat, which is that we had a lot of data. So we had over 1 million storm examples. And so that led to a pretty robust model. And once we got that answer, we were curious about why it was able to do that skillfully. And so then we took a closer look at the storms that it was looking at, and we use explainable artificial intelligence methods, which allow us to look inside deep learning models and evaluate why the model performed the way it did. And so in this case, I'm sharing an example of a correct classification by that convolutional neural network. And when we took a look at what the neural network was looking at, we actually found that it was looking at what I, as a human, would have looked at, which is the U and V winds in the thunderstorm core. And I would detect as a human whether or not it looks like there's strong rotation. And in that case, that would be a storm that potentially has a greater likelihood of producing severe hazards. So it turns out that without me explicitly telling the model that this feature was really important for detecting whether a storm could produce severe hazards, it was able to learn this on its own by looking at a very large sample size of examples. Some other applications or questions that we have about deep learning include how well can a model that was trained with one data set perform when it gets a new data set. And so in this case, we had another type of convolutional neural network that was trained using a reanalysis product, and then we gave it climate model output that was different from the data it had been trained on. And so we were curious about whether it could detect fronts. So these are cold fronts, warm fronts, stationary, occluded, so various different types. And we looked at climatological distributions of these fronts, and it turns out that the answer is yes. This particular model could actually generalize to a new data set that it was not trained on, even though it was trained in an observational setting. And what was exciting was that then, given that we saw that it was robust to a new data set, we were able to ask questions about climate trends and also extreme precipitation associated with fronts. And we were able to study how these fronts would change in a future warmer climate. And so there were exciting results over North America. More recently, we did also ask a question about continued generalization with a new data set. And for this example, we focused on detection of mesoscale convective systems. And we had data only over North America. So we had various different variables over North America, and we had labels or maps of where there were mesoscale convective systems. These are organized thunderstorm clusters. And we trained an image-to-image model. This is a UNet, pretty classic type of architecture that would look at these images and then detect where there was a mesoscale convective system. But we needed to be able to do this globally, and we only had data over North America. So we ended up employing some tricks that we've learned from the computer science community, where we can flip some of these images to help make the model more robust to storms that are moving in a different direction in the Southern Hemisphere. And we also employed, we were very careful about how we pre-process our data so that it would be more general in a different data set. And so this allowed us to participate in a model intercomparison where we considered mesoscale convective system tracks over different kilometer scale global simulations. And another exciting thing about this project was that we trained with a reanalysis data that was very coarse. It was like 32-ish kilometers. And the models were in the kilometer scale that was about 3 to 4 kilometers globally. And so again, still able to compete with many traditional methods that are not deep learning based and perform skillfully. So that was, again, exciting in terms of a generalization question that we think is really important as we move forward in the continued use of machine learning. And now I'll do quickly some examples on the use of machine learning in an unsupervised setting. So when we're thinking about unsupervised machine learning, we're talking about cases where we don't have labels for our data, meaning I don't have an answer. I just have data. And so in this case, we said, okay, I have lots of large scale patterns over North America. And I am curious about which ones are more persistent, because potentially if I identify the ones that are more persistent, I can use that knowledge to extract information about likelihoods of certain temperature or precipitation anomalies over North America. And so what we did was we trained k-means clustering. So this is a machine learning approach to do grouping of our data. And we identified in pre-analysis, so an observational type product, certain large scale patterns. Then we went to our global climate model and applied that method that was trained on reanalysis to see how the model stacked up compared to observations. And it turned out that it was quite similar, so that was a promising signal. And when we took a look at the surface precipitation anomalies for a specific regime, this one being the Alaskan Ridge, we saw consistent patterns where there was more precipitation over California and drier conditions over British Columbia, which suggests that we could potentially use this method for subseasonal prediction. And when we considered the community Earth system model as we increase lead time, we were also able to uncover some biases in that model, where during early lead times, the community Earth system model was very consistent to the reanalysis product, as would be expected. But as lead time increased, we actually saw a drift in the community Earth system model, where there was an over-occurrence of the West Coast high regime and an under-occurrence of the Alaskan Ridge and Greenland high regimes. So that means that there is something happening in our physics-based model that is making it produce too many West Coast highs. And now we can go back and try to understand why this is happening. Why are we seeing this bias? And why is there this issue with predictability for these types of regimes at that lead time? And when we considered other details in this project, like ensemble member spread over time, we found something quite odd. So when we consider the typical scenario, we would have some physics-based model that we're going to start at the initial time. There will be some small perturbations to try to get an idea about potential errors for the initial state and how that might propagate forward in time, leading to some larger spread at a later lead time. And so this would be the typical scenario where we have small spread in the beginning, and once we get to our lead time of interest, we have greater spread. But for certain initializations, there was actually something else that happened where we noticed, and this is all again still in this k-means clustering regime, we noticed that we had small spread in the beginning as expected. We saw ensemble member spread increase and then decrease during later lead times. And so that led us to ask, why does this happen in our forecasting systems? And it turned out that there is a physical reason for this, where predictability or prediction skill can actually propagate forward in time, and certain patterns like the Madden-Julian oscillation as propagates forward in time, if it's captured properly by the physics-based model, can lead to convergence of ensemble members at a later lead time and forecast skill. So this is to say that there is still a lot that we have to continue exploring on the use of physics-based models and the intersection with machine learning providing a new lens to look through and identify these types of patterns. So again, this is pretty exciting stuff, and I at least for me, and I'm looking forward to continue working on these topics with my group to uncover why we tend to see some of this behavior, and if there is potentially some information in there that we can leverage to improve predictability moving forward, or prediction skill of our models. And so now I'll continue giving some quick examples. This is a project that was led by Jairon, who's currently a PhD candidate now in my group. What he ended up doing was asking if this schematic that many of us take as truth for predictability at the subseasonal lead time was consistent when we were thinking about weather regimes. So these large-scale atmospheric patterns over North America. And it turned out that as he created this experiment, he had an XGBoost model, so a tree-based model that would take in certain variables either from the atmosphere, land, or ocean. It turned out that his results showed that for weather regime classification, this schematic could look quite different depending on the season or the weather regime being predicted. So sources of predictability do vary seasonally and also can vary depending on the actual target that we're interested in predicting. And so he's had quite a lot of work that he's continued on down this path. And most recently, he has a project where he linked these large-scale North American patterns to extremes at the surface and was able to find that certain patterns not only have increases in trends in the current climate, along with associated extreme heat signals over North America, but also have projections for continued increases in the future. And this is for specifically the winter and spring seasons over North America. And still using the similar framework with k-means clustering. So again, just a lot of work to be done to continue disentangling these signals and the linkage of extremes and the large-scale atmospheric pattern. Another example application of unsupervised learning, where again, we do not have the answers, was a project led by Alice Duvivier, who is a scientist at the NSF National Center for Atmospheric Research. And she was interested in identifying patterns that are called polynyas over Antarctica. And this is specifically in the Ross Sea. And polynyas, I am not an Antarctic expert, but I learned a lot through her. Polynyas are these areas of open water that can develop from sea ice being pushed away from the coast. And these are very important for life because of nutrients that are there and also for deep water formation. And so what we did was we gave sea ice concentration to a self-organizing map algorithm that is an unsupervised neural network. And what we did was we found what the dominant type patterns are in the community Earth system model. And then, even though we did not give this neural network any information about time, we actually spotted trends in certain patterns. So it turns out that polynya events, which again are very important, are decreasing over the Ross Sea, or at least that specific pattern. And cases where we have increased sea ice concentration and not the development of polynyas, we saw an increase in those events, which is not good for life that depends on these polynya events occurring. So, so these neural networks can uncover quite a few signals, even if we don't give it certain information. But it does take a human going in and deciphering all of the information that was learned by the respective AI. Another project that we're working on, this is led by John Sarfelt, who is a PhD student in my group, is on the topic of urban heat. It turns out that while we know a lot about urban heat islands, we don't know enough about urban heat at the very local level, meaning at the street level. In fact, when we think about our geostationary satellite that provides full disk images of the Earth, this is at 2-kilometer resolution. That is not fine enough to get heat signatures at street levels. And at that case, even if we do get temperature information, it's land surface temperature, not necessarily the temperature that we as humans are experiencing near the surface via near surface air temperature. And so we are developing an AI-ready data set. This is a project that's funded by NASA to enable the development of AI algorithms to fuse together many of the different land surface temperature products that exist from geostationary and polar orbiting satellites to try to address some of these missing pieces of information. Another really critical thing is that many of the measurements of land surface temperature come from infrared sensors on remote sensing. So that means that they cannot see through cloud. And we want to train machine learning to be able to see through cloud using microwave information from other scientists at NASA that they are sharing with us. And so again, there's just a lot of work to be done. We know a lot about urban heat islands, but we don't know enough to be able to inform folks at the street level on extreme heat that they are experiencing. And I know I'm going to be pushing time here, so I'm going to pick up the pace a little bit. I am just so excited about AI for extreme weather and climate. This is another project. This is led by Kyle Hall, who is a PhD student in my group, who has actually created a customized knowledge-guided autoencoder. So he took an off-the-shelf autoencoder that's a type of neural network that can learn signals in a latent space, and he's customized the loss function used to learn that latent space and made it knowledge guided. So he's encoded some of his own desired properties of climate modes of variability and actually moved us towards a situation where we can disentangle modes of climate variability like the El Nino Southern Oscillation and the Pacific Decadal Oscillation more neatly in a nonlinear way so that we can better understand the onset mechanisms of both of these phenomena and how they interact with each other and exactly what is distinct from each one of these. So this is other exciting work. Emily Wazinski is also a PhD student in my group, and she's working on better understanding the El Nino Southern Oscillation diversity and specifically thinking about how can we characterize the different flavors of ENSO in an unsupervised way. And this one is being done with generative AI so that we can also extend our existing limited record of ENSO events to be able to have a much larger set of ENSO events learned from AI. So we can generate synthetic El Ninos and La Ninas to better understand onset mechanisms and so forth. So this is all ongoing work by my group. And two more to go. This one is Maddie, who is a PhD student in the University of Maryland. And her project focuses on developing a lightning prediction model. And this one is a parameterization scheme because it's meant to run online with NASA GEOs to predict lightning. And lightning, of course, is of interest for humans because it's dangerous, but for the climate system, it's also really important because it can produce NOx or nitrogen oxides, which then can lead to the creation of ground level ozone, which is very dangerous for humans and an air quality concern. And so what's been really exciting is that she was able to train a neural network that can do this task quite skillfully, this prediction of lightning within the NASA GEOS model. And so we're excited to move that work forward and move towards a space where we're using it for air chemistry. Matt Chan, this is the last example, is a PhD student in computer science at the University of Maryland. And he published or led the publication of a paper in NeurIPS last December that focused on uncertainty quantification for weather prediction over North America. And this is a project that was funded both by the University of Maryland and also by the National Science Foundation. And this project focused on the use of a diffusion model, which is one of the state-of-the-art models out there for deep learning, and coupled it to a hypernetwork. And what this coupling of two different neural networks enables in this case is the decomposition of uncertainty into aleatoric and epistemic components. So we can generate uncertainty estimates using ensemble methods like I showed earlier with slight perturbations to the initial state, but we don't know where that uncertainty came from. And so in this case, now we know that there are certain contributions to uncertainty that are epistemic, meaning we could actually reduce this uncertainty if we had more examples of those events. And then there's aleatoric uncertainty, in which we can say, okay, that event is just really challenging to predict and really difficult to reduce that uncertainty, if not impossible, because it's just inherent to the task at hand. And so this framework allows us to do this decomposition. And I'll quickly note that here we're looking at a toy example where he artificially imposed this tremendous amount of warming near Greenland, and it shows up in epistemic, showing that success of this method. And when you have high values of epistemic uncertainty in a location, you should disregard the aleatoric uncertainty at that location. So that's a way to interpret these specific toy examples. But with that, I'll leave here this slide where I want to communicate that while I shared a lot of little vignettes of different projects, it's really important that we continue to research the interpretable and explainability of these methods, because we still don't know so much about how robust AI can be, not only for extremes and a changing climate, but also for scenarios where we simply do not have data to verify that our model is performing well. So thinking about AI ethics, and it's also really important that we take all of this rich knowledge that has been created by communities over time for physics and weather and climate, and incorporate that into our AI systems so that they can hopefully serve the public and do good in society. But of course, we have a lot of work to do, and thank you again for the opportunity to share the work that my group is conducting, and I look forward to taking any questions.
Thank you so much, Maria. That was an excellent talk and a great look into using AI in climate and weather science. Okay, so we will start taking questions from the chat. If anyone has a question, you can go ahead and put it in the chat for Maria. We do have some questions already. Let's see. Let's go with this question from WYRDY. Are there any citizen science initiatives for tagging data for input into AI ML weather models? Or is that more a grad student funded research thing?
Fantastic question. There have been some awesome projects in recent years focusing on doing citizen science for some of these methods for labeling campaigns. So for example, Berkeley National Lab out in California led an effort where domain experts would get together and hand label where they thought an atmospheric river was located and where they thought a tropical cyclone was located. And that information was used to train a deep learning model. The challenge with physical science data is that we may all agree on whether a photograph contains a cat or a dog, right? That's pretty straightforward. We may not agree on exactly where a tropical cyclone ends and where it begins, right? So there is another layer of complexity that gets introduced with labeling campaigns of this phenomena. That said, even with labels that have slight differences, machine learning is still able to use that information and even leverage it for some uncertainty in terms of the domain expert definitions. But more recently, I know that the National Center for Atmospheric Research, that's funded by the NSF, has a campaign that's led by Christine Shields, who is outsourcing or doing these joint campaigns to be able to get labels for atmospheric rivers in polar regions, because we're seeing moisture intrusions that can lead to quite some pronounced changes in polar areas. And I'm sure there's many other out there that are occurring, and it would be fantastic to get more of these efforts funded and supported and advertised so that we can have engagement and labeling of perhaps what the public thinks some of this phenomena looks like.
Amazing. Thank you, Maria. Let's see, we do have other questions. This next question is from Sarah. Did you ever do any test on machine learning modeling for paleoclimate? It would be interesting to see how the model manages with a really different climate regime.
Yes, I love it. We do have a project. This is not led by me. This is led by Mary Grace Albright. I did have her photo in one of the slides, the specific one that focused on the detection of mesoscale convective systems. And so what she's done as part of her PhD is in collaboration with scientists at the National Center for Atmospheric Research, they've run these higher resolution paleoclimate simulations to understand the weather of past climates. And so her task is using this deep learning model to track mesoscale convective systems in these paleoclimate simulations and understand how they looked and evolved and so forth. So I don't know that I mean, that would take quite a few different projects and different assessments of robustness of deep learning, right? We're just looking at mesoscale convective systems, but yes, that would be another exciting application of deep learning and testing its robustness when we're thinking about making sure that they perform well.
Amazing, thank you. Let's take one more question. Let's see, this one is from Phil. How much training is required for a model until it reaches a desired level of accuracy?
Yes, this is a question that many people ask and has not satisfying answer, which is it depends, right? So it depends on how challenging the problem is. It depends on the exact task and the complexity of the neural network that you are employing. But in general terms, if you have a smaller data set, you should be using a simpler model. If you have a bigger data set, you can potentially get away with a more complex model. However, having a lot of samples doesn't necessarily mean that you have a big data set. And what I mean by that is that if a lot of your samples are of a very small part of the population of possible events, that's not really helpful, right? So you have to assess the effective sample size when you're thinking about how much data do you actually have. It's ideally better to have more diverse examples, even if they're fewer, so that your model gets exposed to different possible outcomes. I will also say that something my group is currently exploring is this contradiction in that advice I just gave about smaller data set, use a simpler model, bigger data set, you can use a more complex model, where there have been studies in computer science illustrating that sometimes over-parameterization of a deep learning model can be good, but we'll see. Again, ongoing work.
Amazing. Well, thank you so much, Maria, for joining us this evening. Let's give it up for Maria in the chat. She very graciously donated an hour of her time and that very amazing talk and answering those questions. So we really appreciate it, Maria. Thank you. All right. All right. So thanks, everyone, for if you're just joining, this is the 100-hour-long live stream to Save America's Forecasts. It is an opportunity for climate scientists and meteorologists to share their research, raise public awareness about what we're doing behind the scenes. And it's just an exciting time to remind the public also that, hey, this is what we've been doing for decades. We've been investing in this research and our weather and climate prediction infrastructure since the 1950s. I mean, the United States developed the first computerized weather and climate model around the 1950s and 1960s. And it's really paid off since then, right? It was a quiet revolution in our ability to predict the future, whether that's over the next 5 days or 100 years from now, to see the effects of climate change. And so the reason we're having this live stream, of course, for 100 hours is because we know that there are cuts going on, and we know that these cuts are damaging our ability to do research behind the scenes, but they're also affecting our ability to forecast. And especially, at the National Weather Service, we have the National Weather Service is very short-staffed currently. There are many National Weather Service offices without a meteorologist in charge, partly due to layoffs, partly due to forced early retirements. And we also, of course, are heading into into hurricane season on Sunday. That's the first day of the Atlantic hurricane season. So we need to make sure that our National Hurricane Center, National Weather Service is fully funded so that we can continue issuing watches and warnings and alerts for every American citizen. And of course, you can see it at the bottom of the live stream right now. If you're in the United States and you're looking at these talks and you're going, oh, wait, this is something I want to keep funding, we need to make sure NOAA, the National Oceanic and Atmospheric Administration, keeps being funded. Its research side, its forecasting side. Then go ahead and you can just go to this website here, wclivestream.com/act. There's a pre-written script you can send to your representative to remind them, hey, can you please support funding for climate and weather science. And again, this is a nonpartisan event. No matter what your political alignment is, everyone is affected by the weather and also affected by our changing climate. All right, so we are in the middle of our incredible list of keynote speakers for this evening. Thank you guys again for joining us. We're gonna bring on stage next our next speaker. Hello, Dr. Amy McGovern. Thank you so much for joining us this evening. We're actually kind of continuing the AI and climate and weather science tonight, which is really exciting. So just a brief introduction, Dr. Amy McGovern is a Lloyd G. and Joyce Austin Presidential Professor jointly appointed in the School of Meteorology and School of Computer Science at the University of Oklahoma. And she is also the director of the National Science Foundation AI Institute called AI2ES. I don't actually know what that stands for, Amy, if you also want to share that. But
it's the next slide.
Oh, it's the next slide. Okay, great. All right, so let's give it up for Amy and take it away, please.
Okay, great. Thank you. So I'm going to talk. They didn't have titles up, so I didn't know Maria was going to give a great opening for AI. So I'm also going to talk about AI. I'm going to specifically talk about trustworthy AI and weather, climate, and coastal oceanography. And I'm sharing slides in a different mode. There we go. So the full name of our NSF AI Institute is the NSF AI Institute for Research in Trustworthy AI and Weather, Climate, and Coastal Oceanography. And since the focus, we're going to talk about the science, and I'm also going to talk about the funding so that you understand how all these things are funded. So this is one of the original NSF AI institutes that were created starting in 2020. They are a $20 million investment. There are 27 of them across the United States. Each one of them has a specific focus, but they're all focused on making new AI and different themes around that AI. So we were the first one, we were funded in that first cycle in 2020. And our theme is on trustworthy AI. And then each of them has what they call a use-inspired theme. And our use-inspired theme is weather, climate, and coastal oceanography. The AI2ES part of our name, by the way, was a shorter version of our name, but NSF renamed us when they funded us. So it did stand for something. But for now, it's just an acronym. But the goal of what we're doing is we're developing novel physics-based AI techniques. So AI that's using the laws of physics, because that's what weather does, that is demonstrated to be trustworthy. And we're understanding what it means to be trustworthy, because that's a real key question. What does it mean to have trustworthy AI? And the whole goal of that is it will improve understanding and prediction of everything that we're doing with the weather and climate hazards. I promise not to have too many of my slides be super crowded. This one's crowded because it has all of our partners on it. And I wanted you to see, because we're talking about funding, how that $20 million is spent. It's spent with a lot of partners. That whole top row is all of our academic institutions that are partners. So each one of them has grad students and postdocs and professors working on different aspects of this project. That second row is all of our private industry partners. They work directly with us on our research, and in many cases can transition our research into private industry directly. And then that third row is our government and federally funded research partners. And so again, that's another way to do research transition. They can take our research and put it into the government labs, of which we have done several of with our NOAA partners. So I just wanted you to have an idea of how that ecosphere works. When that $20 million comes in, it doesn't just all go to that one university. It's collaborative projects across a wide variety of partners, which I think is really important. So what do we do with this with our AI Institute. So this is our graphic that is intended to summarize all the things that happen inside AI2ES. So the left-hand circle, and I think you can see my mouse if I'm doing this, the left-hand circle has the trustworthy AI researchers, those are the foundational AI researchers, which, by the way, I know that Maria gave an opening on their training. I'm actually trained in AI. My PhD is in computer science. And then I've come to the meteorology side because it's an application of AI that I really enjoy, because we can save lives, we can save property, and we can really make a big difference to people. And I've always liked earth science. So those trustworthy AI people are primarily computer scientists. And then the atmospheric and ocean scientists are the meteorologists that you've been hearing from, and the ocean scientists that you've been hearing from. And then we work directly with risk communication people. These are social scientists. They understand how people think. We work together in a cycle. And I think that's really important, because when AI people tend to develop something on their own and then they kind of head down, bury, work on that thing, they think they have an idea of how the people are thinking and how they might use their methods, but they're wrong a lot of the time. So working with social scientists who actually know how to talk to our end users and actually know how to ask them why it's trustworthy or why it's not trustworthy is really key to creating both an understanding of trustworthy AI and creating that trustworthy AI itself. The other part, I heard a speaker earlier today who was talking about her career grant and how NSF breaks the different pieces of the grant. That is true for these AI institutes as well. So we have the key foundational research, and then they really care about the broadening participation and the outreach that we're doing. And so we have a strong component of broadening participation and workforce development, that is bringing the current workforce up on AI for weather. And all that's accomplished through those partnerships. So those are the two circles that are together. And then we put that big blue circle around the outside, because we want everybody to understand that everything we're doing is making sure that it is ethical and responsible and use-inspired AI. So I'm going to talk about the different circles, and then what I'm going to do is dive into some example stories of what we're doing. And so looking at the first circle, the trustworthy AI and machine learning. For the rest of the talk, I'm just going to call it AI, because the general news when you talk about it is really AI. And Maria already gave you a Venn diagram of how AI and machine learning are different. But the vast majority of what you hear out in the news that they call AI is machine learning. I'm just going to stick with AI. I want to start with, is that earth science, weather and climate, all of these that are doing things that are applied to the atmosphere, have different needs than the AI that you're doing on your phone. When you look at your phone and you use Face ID to open your phone up, your face does not have the same differences over space and time as a weather forecast does. There's what we call a high spatiotemporal autocorrelation. Yes, the different parts of your face are your eyes are going to be here, your ears are going to be here, etc. But like if you're looking at weather doesn't change dramatically from pixel to pixel, and that's one of the very different needs from AI, traditional AI. And another of the very different needs is that AI for weather forecasting can be used to make life or death decisions, and that's something that's not traditionally used for AI. And so it's really important that everything we're doing is making sure that we're understanding that it's used ethically and trustworthy. And so we have foundational research areas of making sure it's robust, making sure it's incorporating laws of physics. We're looking at the generative AI methods. I saw a lot of discussion in the chat about that before this. Generative AI methods are generally what people hear about when they are hearing about AI, because that's ChatGPT. You could ask it questions, it generates answers for you. That's not generally what we're doing. We're working more on the incorporating AI to give you better forecasts. I'll try to explain that a little bit as I go through the graphics, but I'm trying to keep it at a high level. Figuring out how to explain whether or not your AI is certain about what it's doing, figuring out how the AI explain what it's doing, that's the explainable AI, and then making sure everything's ethical, and what does that mean? And I said that these things were use-inspired, and what does that mean? They're use-inspired by specific applications. I grabbed some photos of some hazards. I think everybody's seen tornado photos. What I want you to understand about that hand in that picture is that is my hand. That is my hand holding hail at my house. Those of you who don't live in the Midwest, the hail really does fall big here. I have lived out here for 21 years, and I'm on roof number 4. And that's the kind of stuff that destroys your roof. So it's really something, we can't stop the hail, but if we can improve the predictions of the hail, that will be really important. So it's one of the things that we are inspired by. Convective weather just means all these thunderstorms and all the hazards that come with it: tornadoes, hail, wind, lightning, flooding. Winter weather is another one of our cases that we're looking at. Again, that upper left picture is my picture. That is freezing rain. That is a bush in the backyard that is covered in freezing rain. And if you've ever experienced freezing rain, you know what it does next. It destroys everything because it's so much weight. It breaks all the trees. It takes down the power lines. When you're making a forecast for freezing rain versus rain, let me back up and think about today. If I gave you a forecast for today in Norman, Oklahoma, I think it was supposed to be a high of 73 and it might have reached 72 today. No one cared that it was a degree off. If I'm making a forecast for rain and it is 33, it is a radically different forecast than when it's 32. So it's really, really hard to make that forecast and make sure that it's right. Freezing rain is really tricky to forecast. And it's something that inspires us because we want to be able to do a better job, make sure it's trustworthy. And then winter weather in general is really impactful. I just grabbed a couple other pictures from some snowstorms. I think that bottom one might be Buffalo. I'm not sure. I grabbed it off online. Tropical cyclones, also known as hurricanes in the United States, but tropical cyclones everywhere else. There's another one of our use-inspired areas because they're clearly very impactful. And then if my movie will play, everybody loves turtles. I don't know if the sound plays, but you don't need the sound anyway. I'll turn it off because it's playing for me. This is a little sea turtle in Corpus Christi, and it is getting released into the ocean. And if I talk long enough, he'll actually get out into the ocean. And one of our use-inspired areas is trying to save more of the sea turtles. So we'll talk about that in a minute. Every time I show this movie, everybody's like, go turtle, go turtle. He's going to go. Watch this. He disappears. He flies out. He's gone. He's swimming out into the ocean. I say he, I'm not actually sure. It's a small turtle. One of the other coastal oceanography inspired areas is looking at eddies in the Gulf, which have strong effect on the shipping industry and the oil industry in the Gulf, and then also looking at fog. So that picture there is the aircraft carrier that's in Corpus Christi and with it's closed in with fog. So we're going to talk about all of these areas. But I'm going to go back to that circle diagram I had because I said that we were looking at the AI, we were looking at the use cases, and now we're looking at the social science. So I'm putting the social science together as this interdisciplinary communication team. We have this interdisciplinary team between the AI and the atmospheric and ocean scientists and then the social scientists. And what they do is they take the methods that we have in development and they are interviewing our end users who are over here on the right, the decision makers. We're looking primarily at professional decision makers like the National Weather Service, NOAA, Army Corps of Engineers, et cetera, the different use cases, and asking them why they trust the AI, why they don't trust AI. They use the AI and we observe what they're doing and we use that feedback to understand why they trust it, why they don't trust it, and what we need to do to adjust our methods. So what I'm going to do for the first half is talk about a sampling of the science stories that we have, and then I'm going to talk about impact so that you understand where the science is going. So looking first at and I said this is a sample, inside a large institute with a number of institutions that are involved, there's a huge number of people, and I cannot possibly talk about everybody's thing today. So I just picked a couple of samples that were salient to explain. Across the bottom of each slide, I tried to put in every institution that is involved. And in fact, your previous speaker, Maria Molina, is a co-author on the paper on this one. So University of Maryland is involved in this one. The question for this one is, can AI, when you see an AI forecast, when you see the real forecast, when you see the weather that's happening outside, when you see your TV meteorologist giving you weather, you're seeing something that's sharp, it's reality. When you see an AI forecast, typically what it's doing is giving you something that's very blurry. It might have low error, but it's very blurry. And a question you might have is, well, why does that matter? Who cares if it's blurry, if it's still good enough, right? Maybe temperature blurry doesn't matter. But it turns out for weather, blurry really does matter. And the reason is that the physics of the world are not blurry. And so if you want your forecasters to understand and trust your forecasts, they don't tend to like the blurry forecasts because they consider it to be non-trustworthy because it's not following the laws of physics. So for this project where we're looking at the sharpness project, we worked on developing a whole bunch of metrics that measure the sharpness of the meteorological imagery. And the thing is, meteorological imagery is different than your typical AI imagery. You can't just use sharpness from photographs because if you're taking a photograph of a person, for example, a person has a defined boundary. I actually tried to use the virtual background on this and it was really crappy because it was having trouble with the defined boundaries. But a person has a face, right? Your face ends, your hair is there. If you've ever tried to look at a cloud and tell me where the cloud starts and the cloud ends, some of them are really clear. Some of them are very fuzzy. So the sharpness is different from meteorological imagery in some cases. And so we were trying to look at what does sharp mean? What does blurriness mean? When is blurry bad and when is blurry okay? And what are the trade-offs when we're trying to make the images sharper? And so we have a paper that's coming out and it's been accepted. It should be out anytime. That will be talking about the different metrics so that people can actually measure their sharpness of their images and say, this AI image is producing something that's actually really sharp in a meaningful way, and this one's not. And these are like a broad sampling of projects, much like Maria was doing. So there's going to be like 6 different samples. So this is moving to the second one. the question of how do we create ethical and responsible AI for weather? Why? Why do we need ethical and responsible AI for weather? And that's a question I get asked because people are like, well, you know, it's not like what you see in the news because there's not racism to your weather. We can agree with that, but there's ways in which the AI can go wrong, and it needs to be trained carefully to produce trustworthy results. And we need to really understand the sources of these systematic errors. Because if you put out a forecast that's a bad forecast and it has a systematic error, it could lead to people losing their lives or having property lost. And if you know about the errors in advance, then you can prevent them, or at least attempt to prevent them. So we have a categorization that organizes the common errors that occur when you're developing AI models for weather. I'm only going to show you a couple of examples of this for the purposes of giving the talk in a reasonable amount of time. It has 4 main categories. This is a good time for me to pause and say that anybody who wants to see any of the papers that are published, I'm putting citations to the papers there, and there's also a QR code. So if you take a screenshot, you can go back to the QR code later and you can grab it. So that's the QR code for this particular paper. We're going to dive into just a couple of examples that are interesting for weather. So one of them is looking at the biases that exist or errors in your data. And I'm going to show you one of those. So one example is that the humans, I didn't talk about the human biases, but the humans are involved in everything you're doing in the AI development life cycle. The humans are picking what model you're choosing. The humans are picking what data you're choosing. The humans are involved in saving data in the first place. So if they don't even save the data, it's not even available. So this bias is looking at something called selection bias, where the humans are choosing that selection. If a human doesn't know the meteorology deeply, they might not understand what the implications of their choices are. So this graph on the right is showing something they call rapid intensification of a tropical cyclone, which means that the tropical cyclone deeply becomes a much more intense tropical cyclone in a 24-hour period. So you've seen some of these in the last few years in the news where they went from a Cat 1 to a Cat 5 almost overnight. And that's scary, and we want to be able to predict them. And if you were just saying, well, I'm just going to throw all this data to the AI model because AI likes lots of data, you might just throw it all in there, not realizing that the hurricanes behave very differently across the different basins. We in the United States are used to looking at hurricanes in the Atlantic basin because that's what hits the East Coast of the United States. But there are a lot of other basins out there for hurricanes. They're more than just shown in this diagram. And if you look at how they behave in their changes in wind, if you were to train on one of those basins, you wouldn't get a good description, a good prediction for the other basins. And so it would be better if you're training individually by basin. But if you, the human, didn't know that, you might train an improper AI model. Here's another fun one. When you're training a face, if you don't have enough faces in your data set, they typically do something called data augmentation. And that means they just make changes to your data set. And one of the changes they do is they take the face and they'll flip it like this. Or they'll take the face and they rotate it a little bit, like a little bit back and forth, right? It's still a face because people can do that to their head. I can't really flip my head around, but you understand that it's still a face. If you do that to a storm, it doesn't work very well. So what I grabbed here was a radar image of a hook echo, which is where you typically get tornadoes down in here. And if you take that hook echo and you rotate it just a little bit, it's okay. But if you take that hook echo and you rotate it all the way around, it's not okay because it's no longer based on the laws of physics in the hemisphere that you're in. And so if you're trying to train your AI model to do a prediction of a tornado and you're giving it data that's completely physically implausible, it's not particularly useful. And it could train your AI model to do wrong things. Here's another example of a physics-based bias that probably one you haven't thought about, which is that if you have satellite data, and so you're trying to look at your hurricanes, your tropical cyclones, and you have data coming from 2 different satellites. You have one that's geostationary, so it's there all the time, and then you have a polar orbiting satellite that passes over a couple of times a day. Well, it turns out that polar orbiting satellite can give you a much better picture, but only gives it to you a couple times a day. And so what you're seeing in this graphic is that you're getting sort of a hurricane, this is Hurricane Dorian, that's coming in and it's both fuzzy and clear and it's alternating between the two. The real world doesn't do that. So if your AI model sees that, it doesn't understand the laws of physics. And so it could be giving you some really weird answers. Again, the whole point of this is just that we need to be able to understand these errors and these biases. And by the way, when you hear the word bias, it isn't always wrong. Bias is just like a statistical tendency to do something, right? And a bias here is something you could correct for, but you need to know that it exists before you can correct for it. So the public needs to trust that these models are tested before they're released, and we need to have a way to recognize and measure these and then mitigate for these. And that's what this work was focused on. Now, another fun graphic for you. I talked about the winter precipitation. I talked about the difference between 72 and 73 degrees not mattering, and the difference between 32 and 33 degrees mattering. The question you can ask is, the AI models are really, really good at giving you a confident prediction, even when they're wrong. Anybody who has queried ChatGPT and then found out that what it told you was wrong will know that it confidently told you that it was wrong. You'd like the AI model to be able to tell you when it's not real confident. ChatGPT wasn't trained that way. So one of the things we've been working on is understanding when the model is confident in its predictions and when it's unconfident in its predictions. And this is a graphic of a prediction of rain, which is in green, and snow, which is in blue, and then the freezing rain area, which is that red area. And then it's got the uncertainty overlaid on it, so that if you were giving this to a forecaster, they would see that there's discrete lines, but they would also see where it is confident about those discrete lines versus where it's not confident. So that if you were looking for freezing rain areas, you would know that they aren't exactly where these red line areas are, but it's pretty likely to be snow down here and pretty likely to be rain over there. And so this has been applied to both the freezing rain, snow, and rain question, but also for impacts, looking at power outage predictions and land modeling. And there's, if you want some code for it, there is a public open source code available there. Okay, told you this was the 10,000-foot view. We're going to move to another one, which is ocean, understanding the ocean. So ocean prediction is really challenging because there's a very big lack of sensors and validation data. All we have for sensors on the ocean are the occasional buoys and the satellites. And the satellites can't see a lot of the things that are happening in the ocean, really just the surface. But the ocean predictions are really, really critical to shipping, to all the other industries. Oil and gas, for example, is one of the ones I'll show you. And the ocean strongly interacts with the land. So, whatever's happening in the ocean is affecting what's happening on the land. You might have heard that the tropical cyclones are getting stronger, and this rapid intensification that I was talking about, part of the reason they're intensifying more rapidly is the ocean temperature is warmer. But if our model doesn't have a good model of what's going on in the ocean, how can it give you a better prediction of what's happening on the land? So the ocean really matters. One of the things that we've developed is 2 fully data-driven models. If you have been seeing in the news when they talk about AI models, and you've seen something like New York Times has been, oh, AI is going to predict weather prediction better. What they're talking about are these data-driven models. They don't have the laws of physics. They've trained on like 40 years of data. We now have 2 of those for the ocean. One's called OceanNet, one's called OceanWaveNet. And they predict circulation in the ocean, the temperature of the ocean, and then the wave height. All of these are really important for all of the applications like shipping that I was talking about. So I have an animation of some of the data that has come about that it's trained on. So it's trained on a reanalysis data set, which I know some of the other speakers have talked about. What that does is it takes all the sensors that are available in the past and puts it together into some consistent state that is the best guess as to what really happened in the past, because you don't have sensors everywhere. This is in the Gulf, so you don't have sensors everywhere in the Gulf. You have to give a best guess, high resolution estimate. And then we take that and we put that into the predictions, and we're able to, the left-hand column is considered the truth column, and then the right-hand column are the predictions out here for OceanNet, and then the other predictions that we're comparing to. And OceanNet is doing really, really well. I don't have time to go into details. I just wanted you to see that it is doing a good job of predicting these circulation phenomena in the Gulf. Another quick one to show you, visibility estimation. Visibility estimation is a hard question. Trying to estimate visibility from a 2D image, that is just, you take your camera, you've got your Nest camera, you've got all of your web cameras that are out there all the time. It's really hard to figure out what the depth of that is. But why does that matter? It's a safety critical for transportation. I'll give you an example. My son is a pilot, so I know about how much it matters for visibility for the pilots. In the United States, continental part of the United States, we have a fair amount of visibility sensors, although they're very expensive. There's still a lot of people who are flying with general aviation who don't necessarily have those, for all the small airports, they don't have that data. But also in Alaska is not very well censored or instrumented at all for aviation, and there's a lot of visibility problems up there. And if we could use a camera to just give you a visibility estimation, it could help save a lot of pilots' lives up there. So one of the questions we had was, can we do this? Can we train this on the cameras that we know that exist? We know what the visibility is for them, so that we can then test it on new cameras and see how well this could work in a general sense. You train it using noisy labels so that it can train with new cameras that it's never seen before. And we developed a way to have humans integrated into this approach so that you knew you could trust it. The picture here is not very big, probably for most of you, especially if you're watching on your phone, but it's from Manhattan, and you can look at different, it's from a camera that's mounted on a building in Manhattan, and you can see between 0 and 10 miles, and you're trying to give visibility estimates every quarter mile. And then we tested that on a completely different camera, and this should be an animation that shows you for the New York State Mesonet, which is a fabulous instrumenting across the state of New York that it has stations in every county in New York. And one of the things they have are these cameras. And we were trying to do the visibility estimation at the New York State Mesonet. This worked from the model that was trained on the other stations and then applied to this Bativa's Mesonet station. Works really, really well in many cases, but there's a problem. And that is that it learned how to deal with it up until it can see this back tree line. And then when it can see the back tree line, there's really nothing else that it can see to be able to tell the difference between a half-mile visibility and 10-mile visibility, because it's the same on a cloudy day as long as you can still see. So that's an interesting question that we still need to tackle, but I think the results are really promising because it's working really well for what it can see. And then I promised turtles. I promised turtles at the beginning. I gave you a video of turtles. Can we save more sea turtles? Everybody loves turtles. In South Texas, so for those of you, I know you're listening from all around the world, here's Texas. South Texas is really far down in South Texas. This is in Corpus Christi, Texas. It doesn't get cold very often. Like, it's hot there and it's humid. When it gets cold, these things like Winter Storm Uri and all these winter storms that have been coming down and making us really cold, it cold stuns the turtles. And the turtles, they rise up to the surface of the Laguna Madre and they get run over by the shipping and they're just vulnerable to being killed. And so there's some numbers there about the number of turtles that have been cold stunned. So Winter Storm Uri was 2021 and they had 13,000 turtles that were reported that were rescued, some of which are up there. That one's a 2018 storm that are up there. You can see some of the turtles. So the question is, can you use AI to improve the predictions of when these cold stunnings are about to happen so that then you can, with your stakeholders, stop the shipping and go out and rescue the turtles? And this is an example from January 2024's cold spell, where we were able to use the AI model. It's a neural network-based model that says exactly when the cold stunning is going to start, exactly when it's predicted to end. And you have to do this multiple days in advance. We are able to stop the traffic in the bay and say, you can't come in. This is going to be such an impactful event. There's going to be 10,000 turtles floating. We need to be able to rescue the turtles. And they have an agreement with the Bay of Corpus Christi to do this, but they need to be very confident in their models because you imagine this also costs a lot of money to stop the traffic. So one of the other questions you could ask is, well, how confident are you in your model? Well, the problem is that it actually is really hard. This gets back to the variability of those temperature thresholds. This is just based on one particular temperature. When it gets below 8 degrees Celsius, the turtles are vulnerable. Well, in this case, if you have an 8-hour window where it could get below 8 degrees Celsius, when do you stop the shipping traffic? And you have a 13-hour window where it's going to go above it, but you don't know exactly when. And you need to figure out a nice, trustworthy way to communicate with your stakeholders about when they should stop the traffic. So being able to show them visualizations of what the models think and how the models are trending is really important for these communications. And I think this is my last example of science, and then I'll talk briefly about impact. A lot of these global AI models that are being that are running right now, they're not being produced in a way that people can go out there and play with them on their own. And so sometimes they put out the weights, but not the code. And so if you want to go out and like learn how these models work or just use one yourself, there isn't an existing way to do that, except now there is, because this is released. So Credit is the community runnable Earth digital intelligence twin. And you can get the URL for it from that paper that is there, and you can download it and run it. And what it does, there we go. It is an open framework that is a community framework that allows scientists from all over the world to investigate their ideas on how they can better develop AI models to do weather prediction. And they could focus on, specific areas. I have a postdoc who's working on trying to look at drought in Africa, for example. Like, what are you interested in? You now have a model you can run on your laptop and you can investigate. And I think that's really awesome. I forgot that was a movie. Okay, so to end, I wanted to talk about impact so you understand sort of how the funding gets used and what the impacts have been. We've been here for 5 years. We're under renewal right now, which is an interesting, challenging time to be under renewal. So we hopefully are going to get 5 more years of funding. I talked about the science. I talked about samplings of those different sciences and how they're impactful. I wanted to say a few more things. We've transitioned products to private industry and to government. One example is looking at fronts and identifying fronts, like the cold fronts, the warm fronts, the other kinds of fronts. They matter to shipping, they matter to aviation, and they matter to everybody because those fronts, when they come through, they change your weather and they can start the severe weather. And we have, that one's been adopted by both NOAA and the Weather Company, and it's purely an AI-based product. Sometimes I get asked questions, are we replacing forecasters? And I want to use this as an example to say, no, we are not replacing any forecasters' jobs with that. What that product is doing is enabling the forecasters to do their jobs better because it's giving them a first guess of the fronts, and then they can spend the part of their job doing the parts that they're better at. the human stuff that they're better at, that the AI isn't good at, the decision making and all of that, the support services. Those are really important. And it gives them more time to spend on it. We have a startup company that has started from AITS, Fathom Science. We have over 125 papers so far. You can get them from our webpage, and almost 400 presentations, and our students have won more than 20 awards, which is impact on the workforce. We've been working on K-12. We do K-12 outreach. We have coding camps for middle schoolers. We're training middle school and high school teachers on how to take AI back to their schools and have more AI in there. There's just some pictures there from some of our coding camps. We have developed a community college training program for AI. That means that you can go from your workforce back and get a community college training certificate and take that back to your workforce. And you can also do that as K-12, because K-12 also enrolls community high school students through the dual enrollment. And we're working on taking that nationwide. We've been mentoring students. These are just some samples. We have had 34 REU students, and of those, there's 5 of them pictured on this slide. But we mentor them. I know that some of the other speakers have talked about the Research Experiences for Undergraduates program. This is an amazing program that brings in our promising young students and gets them excited about research. Paul Markowski yesterday said he wouldn't be doing what he was doing without an REU. I think I agree with that. I was also an REU a long time ago. And this is a critical program. We also get internships for our students, and we've had some international trips to jumpstart collaboration with international experts. And we have postdocs. We have funded 23 postdocs and worked with additional ones, and they go on to go into private industry and faculty jobs and help bring the AI for weather science out to everybody. And then I just grabbed a couple of quotes. These are on our website from 2 of our undergraduate alumni and our postdoc alumni talking about their skills. AITS gave me the skills to transition smoothly into industry, where I get my leverage, my new experience with AI, with new and exciting frontiers of weather forecasting. And the communication and technical skills I learned helped me collaborate with researchers from a wide array of expertise at Google. So it's important that we keep funding things like this, because we really need a critical AI trained workforce. Even if they're not going out to do AI for weather, they need to understand how AI works. And this is my final impact slide. We've supported across the whole of AITS 24 faculty, 12 research scientists, 22 postdocs. I think it's 23. I forgot to fix this slide. 36 grad students and 68 undergraduates, and that's huge. I just grabbed some pictures of our leadership team here. And I will, I think, stop right on time and take questions to just end on the note of, AI for weather is really transformational. It's the new frontier for what we're doing for weather. And I'm not out there to replace the weather forecasters. I'm out there to augment what they're doing, do things that they can do with huge amounts of data that they couldn't do on their own. And they couldn't do in a reasonable amount of time on the current supercomputers, because the AI, once it's trained, can be much faster. We need to make sure that what we're doing is trustworthy, ethical, and responsible. And we need to continue the strong support for the foundational science, because if we don't, we're going to be stuck in the 2025 science. We don't want that. So thank you. I look forward to questions.
Awesome. Thank you so much, Amy, for that excellent talk and great overview of the science you guys are doing with this really nice NSF opportunity. All right, so we do have some questions in the chat. You guys have been very engaging. A lot of love for Amy's talk, especially the turtle part. That was very popular.
The turtles are always popular. Do you want me to stop sharing slides?
Sure, we can take it down. Oh, sorry.
Okay.
The director behind the scenes. Anyways, okay, so we'll go ahead and pull up some questions. We'll start with a question from the beginning of your talk from Luca Zaid. How has unethical AI affected research that uses ethical AI, considering the stigma surrounding all AI due to the unethical practices of popular programs?
Ooh, so that's an interesting question. I thought it was going to be mostly about weather, but just sort of AI in general. I think that everybody is worried about the unethical AI, because the worry I hear among the AI researchers is that somebody is going to do something really terrible with an AI method that is going to kill people. And then that's going to put us back on the AI research, because all of a sudden people are going to say, oh, AI can kill people. Anything can kill people. That's not our goal. Our goal is to make sure that what we're doing is ethical and trustworthy. But my concern is that such things that are showing up in the news are going to stigmatize the AI research so that people don't want to keep doing it, when in fact, as long as we're doing it well, we can make it better. I hope that answers the question.
Yeah, no, I thought that was a great response. Okay, our next question is, let's see, from Maggie Powell. Is it possible to modify the machine learning model's loss function to avoid smoothing and the double penalty problem?
Yes, it's not as straightforward to make sharp models as to just modify the loss function. The It's an interesting question because you can actually train with some of the sharpness metrics that measure the sharpness of the image. You can train with those as a metric on the model, and it actually generates really terrible images. So it's not as straightforward as just modifying the loss function. And in some cases, yes, but I didn't talk about the different kinds of AI methods. So diffusion models are ones that get used a lot to make sharper images, and I'll just throw this out there in an example so that people know about them. I think you've probably seen them where you can just like put an image in there and then you can sharpen it. You can like select the image and tell it to sharpen it. That's a diffusion model. What it learns is to try to diffuse away the noise and to give you what should have been the underlying image. And that can use a loss function that can incorporate pieces of sharpness, but it is also incorporating other errors like physics-based knowledge, and that can give you a better answer in meteorology than just flat out giving you the sharpest thing, because the sharpest thing is often not the most physically based answer as well.
Right. Okay. Awesome. That makes sense. I was just thinking, I'm going to invoke my host privileges and ask a question that got me thinking. I feel like I see a new AI weather forecasting paper from Google or NVIDIA or even academia once every 3 months or so. Do you think
it feels like it's more than that?
It feels like it's like every month or every other week. Do you think that is the field advancing from that stream of papers? Do you think there's some real promise in AI weather forecasting?
Yes.
What's your thoughts? Okay.
Yes, I mean it really is. It's a really interesting question because some of the things that are hitting the major news are a little bit hyped up, but that is the way the news works. It's just the news cycle. You can't blame them. But I think, because there was one of the very first papers that came out said something like AI forecasting is solved, and it was literally forecasting one variable, it was pressure levels. And I was like, no. But since then we've come a long way, and each one of these papers is making further steps along that chain. And I'm actually doing advising with private industry and getting to see from that side how they're developing things, and also in the process of working on a benchmark suite. We're calling it an extreme weather bench, and extreme weather bench is going to be helping us validate a lot of these models on the same benchmark suite, so that everybody can actually say, because this is one of my complaints right now, is that everybody comes out with these papers and they say, well, I did great on this tropical cyclone. The next paper comes out and says, I did great on this tropical cyclone. But they're not comparing it on apples to apples, right? How do you know how well the models compare to each other? So we're going to have a benchmark suite out there that they can do that. And that'll help, I think, also push the science forward.
Yes. Oh, that's awesome. Okay, great to hear. All right, more questions from the chat. There are many.
I hear there's going to be turtle questions.
There will be turtle questions. What is it? Have any of the mainstream media channels reported on this epic amount of science and live streaming?
That's a you question, I think.
That is kind of a big question. Yeah, no, the good news is there has been a lot of attention on the live stream, which is good. I think that the New York Times did something, CNN, so it's good.
I saw the CNN article.
Yeah, no, it is getting good attention. Yeah, so, okay, sorry, I should probably read them before I pull them up. Okay, here's another good one. Would it be able to predict any changes in the major currents and their temperatures? This was posted.
This was the ocean one. Yes. Yeah. Yes. So it's doing specifically the ocean models are trying to predict something called a loop current eddy, which is a huge change in the current and they want to do it at least 30 to 60 days in advance. So yes, they're able to do that predictions. They've already verified it on that.
Excellent. Okay, here's another question. Out of all these different applications of machine learning, what are you most looking forward to in terms of impact?
Oh,
good one.
That is an excellent one. I like them all. I want to be able to save lives and property. So I don't want to pick that I want to save the tornadoes or save the turtles. I think the answer is I'm looking forward to things that help people be better resilient to the weather, especially as the weather is changing and becoming more extreme. So more flooding, faster intensification, tropical cyclones. If y'all saw the news yesterday about the hailstorm that hit Austin and just dumped feet of hail, I mean, those kinds of things, it's not a specific application, although I personally would like to save my roof. But I would like to, you can't move my house, so all I can do is tell you there's coming, right? I would just like to help people better protect their lives and property.
Do you think one of the projects I guess you can't like pick your favorite, but do you think one of them will like really achieve this mission of saving property and lives?
But I think all the I mean, the Turtle project already is saving turtle lives. It's already deployed, right?
Of course.
And the fronts project, I don't know that fronts directly save anybody's lives, but the downstream impact that is, right?
Yeah.
Because you're downstreaming, you're getting more time for the humans, and you're also identifying the fronts better. I think eventually the tornadoes and hail will save lives. The tropical cyclones will save lives. Those ones aren't deployed yet, because what happens is you got to go through extensive testing, and that's what you want, by the way. When you were asking about trustworthy AI earlier, we don't want to just deploy an AI model that we haven't tested. That would be bad. So these tornado and hail ones, I think downstream, they really will save some lives, but they have to get through the testing. And the way NOAA does the testing is they do them in the test beds every year, and then you go back and you refine your models, and then you put them back into the test bed, and in 2 or 3 years they can adopt them. So long term, I think the high impact weather has the most impact in terms of saving lives. But I wanted you to know that some of them are already out there. The turtles' lives are already being saved.
That's so true. We're so thankful for that. Okay, let's see. Here is another. This one's interesting. Might have less to do with how unpredictable are hurricanes in general, and how long would it take for someone to fully learn of its habits to predict it? And maybe we could relate this to AI.
Sure. I think that is an AI question, right? It's also a chaos question.
Yeah.
Figuring out where the hurricanes are going to okay, I'm back up. We're actually really good at hurricane prediction already. Hurricane prediction in terms of landfall is really good, and it has gotten so much better in the last 15 to 20 years, right? And the AI models are only improving that even more. One of the things the AI models are doing is actually predicting the formation of the hurricanes earlier. So that's also really cool, right? So whereas the physics-based models might have said about 5 days out there's likely to be a hurricane, and they're going to start predicting landfall at a certain location, now it's looking like some of the AI models are starting to say 7 days out. And so you get a little bit more warning. I don't know what they mean by a habit of a hurricane, but maybe the trends of the hurricanes in certain basins.
Yeah.
I think that we're already pretty good at that. Now you might ask, why are we messing up forecasts? I don't think they actually do. I think what's happening is the impacts are so strong. I'll take Helene as an example. Helene was really well forecasted. There were warnings out and everything. Helene interacted with another rain system that came in a couple days earlier that already provided a lot of flooding. Then Helene came in and got flooding. And I think a lot of people the warnings were out there, they weren't hearing them.
Yep.
So there's it was well predicted.
Yep.
And it's just the question of how do we get the people to pay attention to it?
That's
because
true.
it was unprecedented what happened with it.
Yeah, I also like that you brought up the fact that hurricane intensity and also the path of hurricanes has improved forecasting wise so much. I keep reading this statistic that was like the first advisory of Hurricane Milton last year predicted where it would land in Florida days later by only 12 miles away of where it actually made landfall, which, I mean, that is incredible that we could literally see the future like that using our suite of models. That's amazing.
The hurricane predicting is really good, and I've been really impressed with it. Now, by the way, a question you could ask, and an audience could ask, why can we do hurricane forecasting well and we can't do tornadoes as well? Right? I can only give you a tornado warning 15 minutes in advance, and it's still like not completely clear where it goes. There's a completely different scale. Hurricanes are this enormous, giant scale thing that we have a huge amount of sensing data. We're flying the planes through them. We can see them on the satellite, and they don't turn on time. A tornado is a very small scale feature that we don't have as much sensing information about, and we still don't know why some storms might form a tornado and why some storms don't. And it's much harder to do that prediction for the tornado because of the size of the phenomena.
Right. All right, amazing. Well, our time is up. Let's give it up for Dr. McGovern in the chat. We really appreciate you spending your evening with us, Amy. Thanks so much for that excellent talk.
Thank you.
All right, we are going to get ready for our next talk shortly. But of course, before we go there, if you're just joining us, this is the 100-hour-long live stream event to Save America's Forecasts. It's an opportunity for climate scientists and meteorologists to share not just their research, but also some of us are forecasters out, at the National Weather Service, National Hurricane Center, trying to issue watches and warnings to save American lives and livelihoods. And again, why are we holding this event? It's because there are cuts going on that are affecting our ability to do research, are affecting our ability to make forecasts, and we need to be sure that we are fully investing in NOAA, the National Hurricane Center, the National Weather Service, if we want to continue to improve our forecasting ability, whether that's the next few days or, of course, to know how climate change is going to look regionally in the United States over the next few decades. So we also, if you want to take some action, you can go ahead and we might get this up at the bottom of the screen. There's a website you can go to, wclivestream.com/act. There it is right there. If you live in the United States, you can go ahead and go to this link if you feel so inclined, if you feel so inspired from the talks today. And it basically, if you go to this website, it has a pre-filled kind of script that you can just send to your representatives in Congress, because of course they are the ones that control the budget for NOAA. And so this hopefully will push them to continue to fully fund these agencies that we really need. And you just saw Amy's excellent talk focusing on how she's the director of this NSF funded project, which of course funds undergraduate students, graduate students, postdocs, PhDs, professors, a lot of people in the research infrastructure in the United States. So it's very critical that these agencies remain funded. All right, so thank you for joining us. We are in hour 32 still. And our next speaker, we're going to go ahead and bring on stage. Welcome. This is Dr. Adam Sobel. Thank you so much for joining us this evening.
Thank you, Mark. Can you hear me okay?
Yes, we can hear you. Great. Okay, so just a brief introduction. Dr. Adam Sobel uses he, him pronouns, is a professor at Columbia University's Engineering School and Lamont Doherty Earth Observatory. So we are very excited to have him as a keynote speaker tonight. Adam, I'll go ahead and let you take it away.
Thank you, Mark. And thanks to all the organizers for the huge effort to put this thing on. And it's an honor and a pleasure to be here. So, yeah, I thought I'd start with a little personal history to give you a sense of why I'm talking about what I'm going to talk about for the rest of the time. So, and it's going to relate to the discussion about funding and everything else. And the past two talks were a really good introduction, even though I'm not going to really talk about AI. So in the earlier part of my career, when I was young, which was a long time ago now, I did basic research. I mean, I was just trying to understand how the weather and the climate behaved. I wasn't working on forecasts, or I wasn't working on risk or with the insurance industry, which I'm going to talk about in a minute, or any of that. It was just curiosity-driven research, you know, the physics of the atmosphere. But then in 2012, about 13 years ago, Hurricane Sandy hit New York. It was a huge disaster. I was here studying hurricanes and grew up in New York City. So it affected me very much. And I was suddenly in the media a lot for a little while. And I ended up writing a book, and I ended up, all that sort of engagement with the public that happened around that time got me thinking much more than I had before about how our science is used. I had thought about it before in abstract ways, but this was very concrete. And a couple of my colleagues and I started working with the insurance industry. A couple of people from that industry contacted me and asked me to give a talk, and we started getting to know people, and we went to a bunch of conferences, and we started working with them. They funded some of our research. I'll come back to that. And basically we added some bits to the tools they use to price extreme weather risk, and thus to price insurance. And we're still working with some of those partners. And how that relates to government-funded stuff is going to be a theme here. So I've come to think, long story short, over the last decade or so, I've come to think through those experiences and others that if a scientist like me, and I mean by that somebody who studies the physics of the climate system, wants to make a big impact on societies, do something positive that's not just understanding, but actually help, is through climate risk science. And I'm going to describe what that is. But it's the kind of science that's designed to work with people who are actually doing climate adaptation. Climate adaptation can mean a lot of different things, but here I'm defining it very broadly as anything that makes the climate risk less. So if you want to make climate risk less, you have to know what it is first, and that's what we're doing. So I'll try to make some of this concrete, but I just wanted to give my sort of evolution here because it does relate to a lot of the other themes of this event. So what is climate risk and how do we model it? So a little bit of math here, but without actual equations. It's sort of a symbolic one. If we think of the loss or damage from an extreme weather event like a hurricane or a tornado or any of the things Amy was just talking about, you know, how much damage happens to a house. You can think of, for a single event, the financial damage to a house, that's loss on the left-hand side, is the hazard is whatever is the bad weather, measured in whatever numbers. So let's say it's how big was the hail that fell, how strong was the wind in this event, how deep was the flooding, whatever it is. You take the maximum of that over the event, and then you have your exposure, which is whatever the thing is you're worried about. So let's say it's a building, or it could be a whole bunch of buildings, or it could be all the buildings, in the country, whatever. And then the vulnerability is a thing that tells us for a certain amount of hazard, how much of your building value will be destroyed. So, if the wind speed is, 100 miles an hour, it's going to blow my building down. But if the wind speed is only 20 miles an hour, my building's going to be fine. And in between, it's, gets more and more. And so that's we have to have numbers for all these things. We have to predict or model all these things. And then if we can do that, then obviously how we do that might depend on what kind of weather we're talking about, what kind of assets we're talking about. But if we can do that, then we can do the statistics. And then we can say, well, what's the probability of an event like this? And how much damage would it do over this whole state? And then how much, for example, if we are thinking about insurance, how much should the contract cost to give so much coverage? And a theme that I will talk about a little bit is that a lot of people do this kind of work in a lot of contexts. It's not only insurance, there's a whole spectrum of people thinking about climate risk, because all adaptation on some level is about this, and people do it very, very differently. And although I'm not going to talk too much about it here, one of the things I've been thinking about is how can we make a sort of overall science of this, because people do it very differently in the different fields and sectors where they do it. But let's get a little more concrete. I'm a meteorologist by training, so I think about the hazard, and most of this talk is going to be about the hazard. That's the meteorology. But we will talk a little bit about vulnerability and exposure at the end, because that's really important, and it's interdisciplinary piece that we've begun to learn about. So if you want to know, let's say I want to know what's the probability of a Category 3 hurricane hitting New York City, or let's make it Boston, so we don't have Sandy. I mean, Sandy wasn't Category 3, but let's say Category 3 hurricane hitting Boston. What's the probability of that? Well, you can look at the observations. That's the historical record, and you can say how many times has it happened so far. And the great thing about that is it's real data. You don't need anybody's model. You think it's true. The bad part is we don't have enough data to capture the really extreme events that do most of the damage. So a Category 3 hurricane has never hit Boston in modern times that we have data. So you would say the probability is 0 if you just counted, but it's probably not 0. It's probably just a really rare event, and we don't have enough, our observations haven't been going on long enough to see it. So that's a problem. And also the historical data isn't fully representative of today's conditions, because, the data 100 years ago, the climate was a little different, and that matters. So that's the problem with doing things in the historical record. And the insurance industry very much is familiar with this problem and has a whole way of dealing with it, which I'll talk about in a minute. But first, climate models is a totally different way of doing it. And you've probably heard, if you've been listening to this at all, you've learned something about climate models. Climate models are physics-based. Well, now there's AI ones too, but let's talk about the physics-based ones. They simulate the whole climate system. They know about everything, the ocean, the atmosphere, the clouds, the radiation, and that you increase the CO2, they get warmer. Everything just happens organically. It's a very beautiful, pieces of code, if that's a strange sentence to say. So you can put in your CO2 and say, how do the hurricanes change? How many? But the problem is that you'll probably get the wrong answer, because these models aren't very good at simulating lots of kinds of extreme events, including hurricanes, because what's called their resolution isn't high enough. It's like the number of pixels in a digital camera image. If it's not enough and you can't see the person's face, it's sort of like that. They don't do a good job on the hurricanes. They also have systematic errors. I think our climate models are really shockingly good considering what they do, but they do get some things wrong, and in ways that are sort of persistent over decades. And I'll show you an example of that in a bit. And also, they don't represent impacts at all. They don't tell you what happens to people or their buildings or anything like that, because they're just models of the climate system. So then for the insurance industry, they've developed another thing for their purpose. It's called catastrophe models. And this is a kind of science that's really interesting, because it was developed mostly in the private sector, although all with people who came out of academic programs like mine and others that you've heard from. But they were designed to estimate risk for the insurance industry, and they represent everything: hazard, exposure, and vulnerability. The hazard is mostly based on historical observations. They don't just use the historical observations, because they know that there aren't enough, like just the reason I just said. But they take the historical observations, like what's the record of hurricanes in the whole United States, and then through some sort of statistical algorithms, what's called Monte Carlo, they make more events like that. You can think of like, well, if the hurricane had hit this part of the coast and it hit that part of the coast, but it never hit the part in between, well, it probably could have hit in between, so let's put another one there. It's things like that. So you generate a lot of synthetic events that are somehow like the ones that happened, but they haven't happened. And then you just make history longer, and you do a better job of getting the, the probabilities of rare events. They still don't know about climate change because they don't have the physics of CO2 and all. They aren't simulating things physically. These are very much empirical statistical models. They're starting to put climate change in the last few years, and our group's been a little part of that, but this is what they've historically done. They have probably the best data on exposure and vulnerability, at least in rich countries like the United States, where there was a lot of insurance, because they get data from their clients. But a lot of that is, or most of it is proprietary, and I can't get it as an academic researcher. So that's a problem for sort of open science and general understanding of how these models work. Another problem is that the models themselves generally are country specific, or at least region specific, and only exist or only are good in the places where there's a lot of insurance. So these models are fit for purpose, built in the insurance industry. That's great, but maybe not adequate for sort of global accounting of all climate risk, where you want to include climate change and you want to do it all over the world, and you want to do it in an open way. So we've been trying to contribute this, and this is a model that we built. It was really built primarily by my outstanding young colleague, Jiaying Li, some years ago, with input from Mike Tippett and Susanna Camargo and me. Just to name drop a little bit, I'll put people's names at the end. But we call it the Columbia Tropical Cyclone Hazard Model, or CHAZ, and it's sort of a hybrid between what the insurance industry does and how we think in academia and in climate science. So it's a model that you can think of it as, we have our climate models that take like emission scenarios and then simulate, on a grid, everything, and give us answers about the climate, but we don't believe the hurricanes in those models for reasons I just talked about. So we have a model that knows what all the past hurricanes did, how they formed, when they formed, how they moved, and whether they got stronger or weaker, when, and how that relates to what the climate was in the spot they were in at the time that they did those things. And we built some sort of rules, and I'm not going to show you the equations, but we built some equations. So they're not fully physical models, they're statistical models, but they're statistical models that are aware of climate in the ways that the industry models at least didn't used to be, and maybe some of them still aren't. So if we have a climate scenario and we simulate it in climate models, then we can downscale and produce gazillions of hurricane tracks like this. Imagine these are all hurricane tracks hitting, I don't know if you can see, but I think this is Texas here. And they're color coded by intensity. And then we can do our risk modeling, get our probabilities of rare events. Okay. Here's my first result plot. And this is from a paper that we published a few years ago. And when we first came up with this result, Jiaying said, no, we can't publish this because it shows that we don't know what we're doing. And I said, no, we have to publish it. And it's gotten a lot of attention since then. And I'm happy that we did. What it shows is, this is time here on the x-axis, and on the y-axis is the number of storms, number of tropical cyclones of at least tropical storm strength that form on the whole planet each year. And so the black is some historical data up to, I don't know, 2012 or something, when whenever this up to almost the present. And then these shaded colored regions are from our model, and of course it agrees with the observations back here in the historical period because we designed it to. But in the future, some of the simulations predict more hurricanes, some of them predict fewer hurricanes. The number even goes up or down, and none of them predict in the middle. And it turns out that this is not because of downscaling different climate models, although we did that. This is for a particular global warming scenario where you have a lot of warming. Maybe we think now more than we'll really have, but we're just hitting the model with a big, giving it a big change to see what it would do. And the different colors are different climate models, and they all give this same two branches, these same two predictions. And it's because what I didn't tell you is that our model has a bunch of predictors. It has things it needs to know about the climate to decide whether to form a hurricane or not. One of those things is humidity, and there's two different ways we try to measure humidity. One is called the relative humidity, which you may know from your weather forecast, and one is called saturation deficit, which is just a different way of measuring the same thing. But it turns out that which one you use in your statistical model as a predictor gives you different answers under global warming. And we don't know which one is right because they give the same answer in the past. And so we can't tell from past data. And it's a long story, but this is our quirky model, but there's much more expensive and sophisticated models that try to predict this using all physics. And some of those increase and some of those decrease too. And it comes down to the fact that we don't really know why the number of tropical cyclones historically is around 80 or 90 per year and not, say, 20 or 200. We don't know that. This is a little review paper we wrote about this problem. And so you can imagine that it's sort of hard to know what the answer will be in the future if we don't even know that. And I found in working with real world users, in our case, the private sector, the insurance industry, they really like knowing when there's things we don't know as much as knowing things that we do know, because that's part of the risk calculation. You have to think about everything. You have to account for everything you don't know as well as what you do if you have to price risk. So anyway, this was a result that we haven't solved this problem yet. And so when we do projections, we have to consider both possible answers. And here's an example of that. This is some work we did with our sponsor, a reinsurance brokerage firm, Aon, and we're predicting, we give them our storms and they put it through their exposure and vulnerability, which we don't have access to. This is proprietary data on all the buildings and, and the history of loss claims and so on. This is for two different climate scenarios. The one on the left has a little bit less warming in the future than the one on the right. These are both predictions for 2070 of how much the hurricane loss, economic loss in the US due to hurricanes will change relative to history. Different metrics. The AAL is the average annual loss, so it's annualizing it per year, or the 100-year event or the 200-year event, and how much that changes. And there's two different answers, two different sets of answers for each scenario because we have those two solutions that I just showed you. So it's pretty embarrassing. They pay us, money to do this research, and we can't even tell them whether the answer is, plus or minus. But there's still information here because these changes are actually kind of small. So first of all, our model never predicts huge changes. Other models might, but this is what we get. Another interesting thing is that these are averages over many, many, many simulations. So we know this is the result of the climate change. It's not an accident of natural variability. And yet the scenario on the right that has more climate change, for the one that increases, this is the branch of the solution that increases the number of storms, it still has less of an increase in loss. So why is that? If the change is due to global warming, this one has more warming, why is it increased? Well, we have a few reasons why that might be. One of them has to do with aerosols and the difference between aerosols and greenhouse gases, which is a long story I'm not going to tell. But the other possible answer, remembering that this is the Atlantic and the United States, the Atlantic hurricanes affect the United States, has to do with the next slide. And that's an example of where working with real world users has caused us to rethink even the basic research that we're doing and do some new problems. So what happened was we did predictions of tropical cyclone change for the Atlantic and the Western North Pacific. And here's the lower plot here is what we got from our model. So this is for the model that increases the number of storms globally. And what it shows, it's the track density trend change for 2021 to 2050. What that means is if we think there will be more hurricanes in 2050 than 2021, it's red. And if we think there's going to be fewer, it's blue. Okay. And so our model is predicting that in a future climate over the next 30 years, we're going to have more storms in the Pacific and fewer storms in the Atlantic. And our insurance industry colleagues looked at this and said, this is interesting because if you look at what the observations over the last 40 years have done, it looks like the lower plot here. This is the opposite. So actually the number of storms in the Pacific has gone down. The number of Atlantic has gone up. So why is that? I mean, it could be that this is the past and this is the future. But upon thinking about it, we realize that's probably not the reason. The reason is instead that if you look at how the sea surface temperature in the Pacific only changes in the models, it looks like this. The models predict that it'll get warmer everywhere in the Pacific, but the maximum of warming along the East Pacific equator. And that looks like an El Nino event. I'm not going to go into detail about El Nino events, but those are year-to-year fluctuations that have a pattern of change that looks like this. This is a long-term trend. And in an El Nino event, historically, you do get changes in hurricanes that look sort of like this. But they, so maybe the models are responding, as we would expect. The trend looks like El Nino, so the hurricane changes look like El Nino too. But we had colleagues down the hall at our lab at Columbia called Lamont, who had been telling us that they think the models are wrong about this. And one of the reasons they think they're wrong is that the observations, again, look like the opposite. So this is the observations of change in sea surface temperature in the upper plot over the last 40 years from one particular observational data set based on buoys and satellites and whatever else. And it shows, it shows that the East Pacific is getting colder, actually, not warmer. Rather than being the maximum of warming, it's the place that's not warming at all. Only the West Pacific is. And in fact, this looks like what's called the La Nina event. And in a La Nina event, indeed, the hurricanes look like this. So we now think that the models may be fundamentally getting this wrong. It's not only us now, a large fraction of the field thinks that this may be something the models are getting wrong. We're not 100% sure. And if they are getting it wrong, we don't completely understand why. But this is a big problem, and a lot of us are working on it. And one possibility is that it's interannual variability, and it's just an accident they're wrong. That's what this plot is about, but I think I'm going to skip that. I'm also going to not going to talk about this in detail, but I just want to show this plot because our colleagues, this is Richard Seeger at Lamont down the hall, and Mark Kane, who, by the way, invented El Nino prediction with federal funding at Columbia, have been arguing about why the models are wrong, and they have one particular hypothesis that has to do with the so-called model biases, and Amy mentioned model biases, and this is an example of model bias in a physical model. And we have a particular theory about it, and we've been testing it, and this is a paper we wrote with our excellent postdoc, Jingyi Zhou. But I don't really want to talk about that in detail. All I want to do is use an example to say this is a case where we were doing something for a very applied purpose for the private sector, but the questions that came up and the cause of that caused us to go back to our basic research and ask more fundamental questions, so including in some of our government-funded projects. So there's a real back and forth between these types of research that's been really inspiring for me over the last few years. I've been talking about hazard so far, but I promised to talk about risk and vulnerability and exposure, so I want to say a few words about that. This is what a vulnerability curve looks like. So if here's the wind speed on the x-axis, here's the fraction of the building that gets destroyed, or fraction of whatever your asset is that gets destroyed, and all you can ignore the equation here, but all vulnerability curves look like this. So if your hazard is small enough, if your wind speed's low, your building's fine, you destroy zero value, but eventually it starts picking up, and it always increases because a higher wind is also always more damaging than a lower wind. Same thing if it was flood or hail or whatever. And eventually, it hits one, you've destroyed your whole building. And so there's a shape to this curve, but how fast it starts rising and when it starts rising is a sort of adjustable parameter. You can decide like what is the value where you start getting destroyed. And so we're going to tune that. This is a theoretical curve that comes from a great hurricane researcher called Kerry Emanuel, who I've learned a lot from in my career. I just want to say briefly, I don't want anybody to try to read this slide, but this is a slide from a great industry scientist about how you do it if you really had a lot of data and a computing power and you knew about your whole building, you knew everything about your building, and you could put it in a wind tunnel, at least or a simulation of a wind tunnel. We can never do this if you want to do the whole world because you don't know about all your buildings everywhere in the world. You don't have data. This is an example of where it's the opposite of the situation with weather and climate data, where the government gathers the best data and gives it to everybody. This is data that comes from private sources and everybody can't get it. And that's, that's a problem for this kind of work. But it also shows how good the converse situation is with weather and climate data. Anyway, this is some work from our former postdoc Jane Baldwin, who's now a faculty member at UC Irvine, and this was work that was funded by the Swiss Re Foundation, so that's a reinsurance company. It was about wind-related tropical cyclone in the Philippines. So what we were trying to calculate the risk, to build a model, to learn how to model risk, and we picked the Philippines just because they get a lot of cyclones there. So we have some tracks. In this case, we used the observed historical tracks. That's what these red lines are, because we wanted to be able to compare it to observations. And then for each track, we know what the maximum wind speed is, and we use a sort of empirical model to unfold that and sort of paint what the whole swath of maximum winds would look like across the island for that storm as best we can. You don't have enough data to do that 100% from observations, but you know roughly how strong the storm was, and so you can do that knowing the track. And then we took that vulnerability curve of that shape, and we adjusted the free parameters of it, when it picks up and how fast it picks up. And in this case, there's two curves, one for what's called the capital region, or NCR, and one for one for basically Manila and one for everywhere else. And the Manila one is the blue one, and the red one is everywhere else. And you can see that you start getting damage much sooner. And I'll say why we did two, but we had an exposure map. We don't know everything about all the buildings in the Philippines, so we use a data set that comes from a Swiss group that uses economic data, gross domestic product, and then sort of distributes that across the map of the country using night light seen from space. So that's a very clever thing they did, because they don't don't have data on all the buildings. And then knowing that, we can figure out, okay, for each storm, what were the winds? And then we have where's the value, how much dollars per square kilometer worth of buildings, and then how much of it would be destroyed. And we can calculate, what we think the damage should be for all the storms. And this was done in collaboration with the World Bank, I should have said, a great economist there that helped us. And this is Jane's main result. So this is taking all the historical storms, and that's Jane in the lower right, and calculating how much damage we think there should be, and then comparing to the actual damages as best we know it from the historical observations of actually how much economic loss there was in these real events in the Philippines. And then this is a sort of statistical comparison where, and I won't explain exactly what the statistic is. It's an overall measure of how good our agreement is with our loss predictions and what we actually get. But the red means we're predicting too much damage. And the blue means not enough. But this is in the left when we use only one vulnerability curve for the whole country. And what happens is if you use the vulnerability curve for the southern Philippines, in the northern Philippines, you get too much damage. Basically, you think the buildings in Manila should blow down when they really don't. And so the one on the right is where we use two vulnerability curves. You want to use as few as possible because you don't have that much data to constrain your problem. But two is a lot better than one because basically there's more money and stronger buildings in Manila than everywhere else. And we actually had some social science called household survey data from the World Bank to sort of confirm that the roofs are sturdier in the Manila area. And so using two vulnerability curves and tuning them separately, we got better agreement. And that's a model that we're now going forward with to think about climate change and climate risk. But I just use it to sort of show that we're meteorologists trying to learn about how to model economic loss, and also to illustrate some of the games you play when you don't quite have enough data, and you have to do it anyway, which is often the case in this type of work. So I'm almost done. I just wanted to say one more thing, just to give you a feeling for this field. This is a screenshot from a paper by an economist named Bill Nordhaus, who won the Nobel Prize for economic modeling of the risk of climate change. And you don't really need to understand this equation. What you want to say is, for him, he was modeling the damage to the whole economy, that's the left-hand side, based on just the global mean surface temperature. That's this T on the right-hand side with a simple equation. Now, there's more this is called an integrated assessment model. There's much more complicated versions of this now, but he won the Nobel Prize for this, and models like this are still used. I would say this is still a climate risk model. His hazard is just global mean surface temperature, and his exposure is the whole world economy, and the vulnerability is a simple function. Compare that to what I just showed you, which is like modeling each storm separately, and you can imagine doing that for all the hurricanes, then doing that for the heat waves, and doing that for everything, the hail, everything you can think of, and then adding that all up. It's hugely different levels of complexity. And that's the status of this field. Different people who are thinking about climate risk do it very, very differently. And I think what we're missing is what we have in basic climate science, which is a so-called hierarchy of models. So in climate science, we can model the whole planet, or we can look at observations. We can model the whole planet with a climate model. We can use a model that doesn't have any land on it, or we can make it not have any water at all in the atmosphere and just a dry model. And by understanding how these different models behave and what they can do and what they can't do, we start to understand how the climate system works, because we can't do experiments where we try these things. All we can do is in models. And I think, but the level of complexity being different is what the hierarchy is about, and the fact that we have access to that and that we do this in a systematic way makes us understand a lot of things. And I think in climate risk modeling, where we're going further to model impacts, there are models at very different levels of complexity, as I just showed you, but it's kind of a little more disorganized. And I think there's room in this field for us trying to be a bit more systematic about it, but it's still early days on that. So the last thing I want to say is about the private and public sectors, because this is an event about funding. So, and I've been talking about our work with the private sector as well as with government funds. And so I've put at the bottom, I didn't put it the first slide, but this is a list of where our funding has come from for the work that's gone into the things I described, National Science Foundation. I put the government ones on the left. At one time or another, we've had funding from NSF, the Office of Naval Research, which is the Navy, NOAA, NASA, Department of Energy, but also from Aon. I showed you work from them. That's a reinsurance broker. Swiss Re is a reinsurance company. I showed you stuff from them, and also Willis Towers Watson is another one. So we've worked with all these, and my characterization of what the difference is like this. The private sector does its own science to meet its needs. And there's lots of companies doing catastrophe modeling, as I described to you, for the insurance industry. And occasionally some of these companies will go out and fund a university partner like us to do something that they're not getting elsewhere, to help them think about climate change, or to do something else that they're not getting. But all of it is built on top of government-produced public research and data. The historical observations that they use to build the catastrophe models, some of the data about the historical losses in the events, the climate models that are used now, including by the insurance industry, to update their risk estimates. Not to mention the PhDs, who the private sector is full of, that are doing work for the private sector, but wouldn't have the skills to do it if they hadn't been trained at universities on research projects that almost inevitably were government funded. So it's fair to say, and I think anybody in the private sector in this field would tell you this and would not argue with it, that the private sector as we know it in weather and climate would not exist without the base of federally funded science in all those ways. So I'm going to end there with a slide where I left those points up, but it's a list of my collaborators, and some of them anyway, and some funding. And I have a podcast and stuff, and I put that all down here. But thanks so much to the organizers for letting me be here and talk about this.
Excellent. Thank you for the wonderful talk, Adam. Let's all thank Adam for the great talk. For those who are just tuning in, I'm Henri Drake. I took over for Mark, the previous host. I'm an oceanographer and climate scientist, and I would maybe say Adam's #1 podcast fan. I've listened to every episode, signing him twice. Check it out, Deep Convection. Okay, so we have some great questions for Adam in the chat. I want to start off, Adam. So I don't know if you know, but Carrie Emanuel actually was a keynote speaker yesterday around the same time, talked about a similar topic, but actually had a pretty different take. One interesting difference I noticed is that he emphasized a lot that the changes in damage due to storms are from like the few most damaging storms, and that actually a lot of the change in damage over time is due to development of the coasts, and not necessarily climate. So I'm just curious what your take is on that, and to what extent does the insurance industry take into account the climate effects as well as all those other things, and how big of an effect do you think those two relative things are?
Yeah, first of all, I agree with Carrie about everything you just said. I just didn't emphasize it, but it is true. I mean, so if you look at the losses due to hurricanes over the last, 50 years, they have skyrocketed. It is almost certain that the majority of that is due to huge increases in development along the coast. There's just a lot more people and buildings and stuff in harm's way. That is true. No argument at all about it. That doesn't mean climate isn't doing anything. It just means that it's sort of hard to tease it out from the data on top of this huge signal of development. So, the industry is acutely aware of this. I mean, they know, they don't necessarily know the answer to that last question, but they're certainly aware that development is a huge issue. So, but they're still thinking about climate change anyway, because they know that's there. And so, they want to know that answer. So I should have said the results that I showed you were assuming exposure doesn't change. And you could see that we didn't get huge changes in loss. So that's sort of consistent with what you're saying. I mean, I guess another way to put it is, if I'm as a citizen, I'm hugely concerned about climate change, but I don't actually think that hurricane risk, at least from wind, is the #1 problem. I mean, I'm much more concerned about heat because it affects everybody and such a huge health risk. Hurricanes do a lot of damage because of flooding, and that wasn't actually included in the result I showed you. And there we have sea level rise and stuff, and Carrie probably talked about increases in flooding.
Yeah.
But so, all these things are true. But I think, there's no way how much of a problem climate change is to hurricane risk unless you try to model it, because you can't extract it from the observations in a simple way. Any way you try to extract it from the observations involves some form of model, whether it's a physical model or an empirical model or some other way. So, it's a scientific problem, but in big picture, I completely agree with Carrie.
Yeah. So to that, to the point about the modeling, we have some questions about how these models actually work. So one of them is from Larkin: how are you using AI in your prediction models? What do you see for the future for AI and climate predictive modeling?
Yeah, that's a great question. So we are not using AI yet. I mean, in the results I showed you, there was no AI. I mean, the Chaz model, unless you think sort of Poisson linear regression is a form of AI, which it isn't. I mean, some people would argue it's technically machine learning, but we are not using AI yet, except in experimental ways that we're starting to think about it. But I think it is absolutely the wave of the future because, and people are starting to do this, and I'm sure we're going to get into it in soon. We're already thinking about spinning up projects on this. The new AI weather models that you've probably heard about, the models that are actually predicting weather using AI, on the full globe, they've just improved so quickly, so amazingly. They're so amazingly good after just a few years of development, and they're super cheap to run. I mean, they're expensive to train, but once you've trained it, they're super cheap to run compared to the physical models, which means you can do lots and lots of years and lots of, simulate huge numbers of storms very, very cheaply. Maybe not the climate change influence that well just yet, but that's surely, only going to get better. And so that's what you want in risk modeling, because you want to do lots and lots and lots and lots and lots of storms. You want to have lots of examples of data so you can catch those rare events that do most of the damage, like Carrie talked about. So, whereas the CAT models are sort of cruder statistical algorithms to make new events that look like the old events, the AI weather models are a way more sophisticated statistical technique for doing that. And so, I mean, I feel like they're not, the first research papers I've seen trying to do this show that they're not quite good enough yet, but they're really close. I mean, give it another couple of years, I think this is going to be very widespread.
Yeah, I agree. So we have some questions about people who are interested in getting into the field. So one of them is from Jackie. If climate risk science like this is an interest area for an undergrad, what kind of coursework would be important to pick up during an undergraduate degree?
Yeah, I mean, so for the type of science, I mean, for an undergraduate degree, yeah, that's an interesting question. I'm biased because I was a physics major. I mean, I think basic quantitative training at the undergraduate level is the best. So I like physics and applied math and the very quantitative engineering disciplines, because I feel like the sort of meteorology knowledge, I mean, that's great too. I mean, look, programming, statistics, applied math, physics, all these things are tremendous foundations. Of course, meteorology and earth science and all of that, machine learning, all that stuff is great too. But I think you can learn that later. But if you don't have the sort of quantitative foundations, it's hard to do it. Now, of course, there's things one can do in this field that are less quantitative, but you're talking to me as a physical scientist, so that's what I think of. So if it were me, I would say be a physics major and an applied math major or something like that before go right into meteorology or earth science. But I'm prejudiced because that's what I did.
Yeah, unfortunately, I had the same bias as you as a math major, and then got into the field. But what I tell my students now is, if you can double major or do a minor at least in applied math or something.
Yeah,
starting out in science. Yeah. Okay, so we have some other questions about the modeling. So Maneli Nayak asks, this may be beyond the scope of the talk, but how do you quantify hazard and exposure? And you talked a little bit about this, and you also talked about vulnerability and how you modeled that. But could you kind of walk us through how you combine all of these things to quantify risk again?
Yeah, it was very fast. So hazard is whatever the geophysics is. So if it's hurricanes, I have to generate a sample of data about a gazillion hurricanes. Where did they go? How strong were they? Whatever aspects of them are causing the damage, whether it's wind or flooding or whatever, you have to do that. And people do this also for tornadoes and hail. They do it for earthquakes. you have to build up a catalog of events, and to do risk, you generally need more events than have really happened. So there's synthetic events. So however you do that, the hazard is like a physical science, an earth science problem. The exposure is what's the stuff you're worried about. So in insurance, it's typically, extreme weather insurance is mostly about property and casualty, which means buildings, which means you have to know about the buildings. And sometimes, depends on the nature of the business, of the contract, and I'm not an expert in that side of it, but sometimes you can insure individual buildings. Sometimes it's a reinsurance contract that covers a whole portfolio and they don't really know about every single building, but somehow you have to characterize what are those buildings. Now, but climate risk in general could be anything. It doesn't have to be buildings. You can have exposure and vulnerability that's forests or ecosystems, human health, anything. Climate risk and adaptation are about anything affected by climate. So in principle, it could be anything. But, if you're talking about insurance, it's buildings. So as much as you can know about those buildings, and sometimes you have good data, sometimes you really don't. And then the vulnerability, let's see, I'm still showing it, but this is a serious wind engineer's paper about how to do vulnerability. All these things about your house. Is it 1 or 2 story? Is it is it made out of metal? Is it industrial? Is it high rise? And about all these things, and then you put it in a simulation of a wind tunnel, and you figure out when the roof's going to blow off and when are the windows going to break. In reality, you may not be able to do any of this. In our work, we don't have the information or the ability, because imagine doing this for every building in the world. You can't, even if you had the computer power, you probably don't have the data. But so there's what I would say is for exposure and vulnerability, the standard in insurance is one thing. They're probably the best at it because they're spending a lot of money on it and they've been doing it a long time. But in climate risk modeling generally, there's a huge spectrum of things that you might call exposure and vulnerability, and very different types of science and data that you might use to characterize those. And I think we're still just kind of in the early stages. But there are economic models that try to model a wide range of these things, that'll model different sectors. What's the effect of heat on labor productivity? There's economists that have a vulnerability function for that. They call it a damage function. But how much less will our workers be able to work if it's really hot? And that goes into a climate risk calculation if you're thinking about sectors where that matters, and so on. So yeah, it's a long answer, but
great. Well, thank you so much, Adam, for the talk and for answering questions for me in the chat.
Pleasure.
Yeah. All right. So, and also thank you for pushing us into, what are we at? 33 hours and 30 minutes. So we are officially more than a third of the way through our 100 hours of the live stream. Thank you for tuning in. And yeah, we're here to talk about science, learn about science, and also its value for society. We've seen a lot of great talks so far. The last one was no exception, and the next one, I'm sure, will not be an exception either. But before the next speaker joins us, let's all remember why we're here. It's really all about the value that this science serves to society, and a lot of that is through forecasts. We are forecasting the weather, so we are just entering hurricane season, and we can now forecast hurricanes pretty well several days into the future, and that provides an enormous value to society. But more than that, as we just saw from Adam's talk, we're also making climate forecasts to understand how things like hurricanes change, not just in the next few weeks, but decades into the future. And those are being used by people like the insurance industry, and many other groups. And that doesn't come for free. It takes a lot of investment. A lot of that historically in the US has been the federal government, through grants, through supporting federal research labs, supporting public-private partnerships like we just heard about from Adam. And that's to build the models, to improve the models, but also to fund the observational networks that provide the data that these models rely on. The models would be no good if we had no way to validate them, right? We have to compare them against what actually happens in the real world, and that's what these observational networks allow us to do. And this is all paid for by you, the public, the taxpayers, and also that funding is at risk right now. So there are proposed budget cuts and layoffs at federal research laboratories that are all at risk of being cut. And that would completely undermine these forecasts that we rely on. So we need your help to save our weather and climate forecasts. We have a banner right under me that says you can go to wclivestream.com/act to call your representatives and advocate for weather and climate science. And you can go to our website and learn more about the issues. And this website will give you a template that gives you some language to kind of draft your ideas around. But really anything you can do to call your representatives, it really goes a long way. Okay, let's see. Oh yeah, so that was just the link flashing around on the screen. You can see it in the chat. Okay, with that, it's my pleasure to introduce our next speaker, Professor Anand Gnanadesikan. Anand is a professor of oceanography at the Johns Hopkins University in Baltimore. Before coming to Johns Hopkins, he spent over 15 years at NOAA's Geophysical Fluid Dynamics Laboratory in Princeton, New Jersey. His work spans physical, chemical, and biological oceanography, and he's going to touch on all of these topics here. And just to give you a personal anecdote about how fundamental Anand's contributions have been, one of the questions on my PhD qualifying exam was actually taken from his famous 1999 paper. So we all know about this. It's okay, I have studied it before, so I did okay. But we're very lucky to have him. So please join me in welcoming Anand to the stream.
Thanks, Henry. Can everyone hear me?
Loud and clear.
Okay, great.
Can we see your slides?
Great. Okay. So I'm going to talk to you today about how the Southern Ocean shapes our world. The Southern Ocean has played a huge role in my career, even though I've never been there. Now, when you think of the Antarctic, you might think of penguins or icebergs. If you're my daughter's beloved little goddaughter, you might think of the fact that it doesn't have any turtles. Probably you won't think of the fact of Antarctica when you're eating your tuna sushi, or when you're looking at a hurricane in the Gulf of Mexico, or if you're looking at the eponymous rock of Glen Rock, New Jersey. And yet the Southern Ocean has an impact on all of these as well, and I'll talk a little bit about why. This is a picture of currents and winds in the Southern Ocean from yesterday. All of these are using data and output from models that are generated by NOAA from the nullschool.net. And I'm just going to have us look at it for 10 seconds and see what patterns we see. Now, some things that I want to just call to your attention here. The first is that if you look at a latitude circle of between about 60 and 55 degrees, you can go all the way around the globe without running into land. So that's the first thing I want you to notice. There's this band of open latitudes in the Southern Ocean. The second is that the winds in that band, you can see these streamlines are much longer here than they are to the north or the south. And they tend to be blowing from west to east in the same direction that the Earth is rotating. Okay, so they're moving from this view clockwise around Antarctica, and underneath there's this strong current. Okay. And the thing about having winds in the same direction as the Earth's rotation is that just as if you take a lasso and whip it up faster and faster, it will drift and expand away from your hand. Or if you take a pendulum bob and spin it faster and faster, it'll move further and further from the vertical. If you try to spin water on the Earth faster and faster, it'll drift away from the axis of rotation. It'll drift northwards. Now, in regions further north or further south than this band of open latitudes, that northward flow can get returned by a flow along the boundaries. But in the Southern Ocean, there's no boundary at the surface to return that flow, so it has to be drawn up from below. The water has to be drawn up from below to replace that water that is being moved northward at the surface. And why does that matter? Well, it matters for a lot of things. We're going to talk a little bit about some of them today. The first is that it matters for ecosystems. If you're a tree, you have a fairly easy job. You sit there, you collect the sun, you drop your leaves in the winter, the nutrients fall on your roots, you pick them up the next year. If you're a plankton in the ocean, you have a much harder job. Nutrients and upwelling will bring, mixing and upwelling will bring nutrients to the surface where biological activity caused by things like this cyanobacteria and this diatom on the right will take up those nutrients and take up carbon with them. But then they sink. And they sink into the ocean interior. And once they're in the ocean interior, away from the light, they're no longer available for biological activity. So mixing and upwelling, in particular this upwelling in the Southern Ocean, is critical in bringing nutrients back to the surface. I should also say that this process produces 1 out of every 2 breaths that we take. So for about 3 of the last 6 minutes since I've been speaking, you've been breathing the output of these, largely these diatoms here on the right. If we look at surface nutrients across the globe, this shows a map of nitrate, which is one of the key drivers of biological productivity. We need nitrogen to make our proteins, so do phytoplankton. You can see that the highest values are in the Southern Ocean. Very, very high values all across the Southern Ocean. So the Southern Ocean is the place where nutrients stored in the deep ocean return to the surface. They are then exported from that to the rest of the low latitudes where they fuel the productivity that, among other things, gives you your teppanyaki sushi in the end. But what goes up in the Southern Ocean must go down somewhere. And one of the ways in which we can see that really well is by looking at how much oxygen has gotten used up in the deep ocean by the material raining from above, the so-called marine snow, named by Rachel Carson, a Johns Hopkins grad. Go Blue Jays. This marine snow falls down and rots, and as it does, it consumes oxygen. And what you can see, looking at the oxygen utilization at 3,000 meters, again, we've got lower values in blue and higher values in yellow. The lowest values in the youngest waters in the North Atlantic. There's hints of a local maximum in the Southern Ocean, implying that there's some sinking of some dilute ventilation of oxygenated waters from the south, and no ventilation in the North Pacific. And this is associated with a well-known feature, the global overturning circulation of the ocean. This is a 3-basin model of it, where you have the Atlantic here on the lower left, the Pacific on the right, and the Indian on the upper left. And the colors reflect temperatures. So one thing I want you to notice is that there's one place here where the warm water moves north and gets converted to dense water and goes back to the south. There's really only one place where that conversion is happening. Everywhere else, the water is coming up to some extent, but there's the dominant place where that water is turned into lighter waters is in the Southern Ocean. I should just point out that the first author on this paper, Lumpkin Spear, Rick Lumpkin, is one of those who was forced out of federal service, this past March after 25 years. When we talk about the impacts of cuts on federal workers, it's not just the data, it's the scientific expertise and the careers of people who spent their lives trying to understand the planet better. Now, if we look at the overturning, and we might have some questions about it. For example, like, why is it asymmetric? Why is the dominant place where the light water is converted to dense water, where warm water is converted to cold water in the North Atlantic? Why is it there and not the Pacific or the Southern Ocean? What are the impacts of this asymmetry? And how might this overturning change in the future? And part of the answer, and this is probably what Henri got asked on his qualifying exam, is that asymmetry is driven by the Southern Ocean. That upwelling of water in the Southern Ocean, it's relative. We're looking at salinity here along a section 30 west, right down the middle of the Atlantic. So fresher waters are in blue and saltier waters are in yellow. And you can see there's highly saline waters near the surface. And then there's an upwelling of moderately, what for oceanographers are fresh. Oceanographers are weird. We think 34.9 is fresh water and 35.3 is salty water. It's all relative, folks. When that water upwells, it gets freshened by the fact that it's cold. So water doesn't evaporate very well at cold temperatures, but there's rainfall in that region. And so that water becomes fresher and lighter. And then it gets injected into the main thermocline, as intermediate water and flows northward. That water then becomes saltier as it moves across the tropics, it gets warmed, and then it sinks in the north as North Atlantic deep water. And the result of this circulation is to transfer heat from the southern hemisphere to the northern hemisphere. And that's really important. And one of the ways in which that's important is shown here. The plot on the left shows the tracks and intensities of tropical cyclones from 1851 to 2006. The individual tracks are lines, and the colors, the redder it gets, the stronger the tropical cyclone or hurricane. So we start at tropical depressions and go to category 5, super destructive typhoons and hurricanes. And one thing that you'll notice here is that, first of all, there's a lot more of these in the northern hemisphere than there are in the south. And there's basically no hurricanes in the southern Atlantic Ocean. And this is pretty clearly linked to that overturning circulation. So that upwelling in the south drives a flow to the north and heat to the north, and that basically sweeps the hurricanes out of the South Atlantic and concentrates them more in the North Atlantic. This phenomenon also matters for tropical precipitation. As you push more heat northward, tropical precipitation shifts towards the northern hemisphere. And this shows an example of how this works from work by Tapio Schneider and a couple of paleoceanographers, and Bishop and Hogg. What they did was they took sediment cores from this basin here off of South America. And what they did was they looked at the titanium content in that sediment over time, going back about 1,000 years. And that's this. They also had a reconstruction of north to the south temperature gradients, which looked something like this. So what you see is that there was a cooling through this period, followed by a warming, and that as that we get a cooling and a warming, we get first a drying and then wetter northern hemisphere. And these are probably pretty important in human history. Carrie talked yesterday about how the past is not always a good guide for the future. One of the things that we've seen is that we're in a point right now where the northern hemisphere is wetter than it has been for past 400 years. It's quite likely that at some point in this minimum here was associated with, for example, the abandonment of the Chaco civilization in the southwest United States. So these kinds of changes, small though they are, can have civilizational scale impacts, especially on communities that are living close to the brink. We know that overturning circulation has shut off in the past. This is another classic record from an ice core. Time is going backwards on the horizontal axis here. So we go from about 7,500 years ago to 36,000 years ago. And what you're looking at is the concentration of methane in that ice core. And what you see is that as we go back 20,000 years, there was much less methane. And then as we move forward into the present, moving from right to left, there's first a big increase and then a massive drying of the tropics. And this is a big deal. This is a massive climate change. This is associated with a period of time known as the Younger Dryas. And it's been proposed that this Younger Dryas was caused by glacial meltwater flooding into the Atlantic and shutting off the global overturning. And so it's been proposed that that might happen again in the future, most notably in this incredibly sensationalized and unrealistic movie, The Day After Tomorrow. Watch it for a laugh, but don't take it seriously. The standard theory, though, for why the overturning collapse would be that a warmer atmosphere holds more water, and so there's more transport of water from the tropics to the Arctic, which makes the Arctic light and slows down the overturning, which allows more fresh water to build up, which makes the Arctic lighter. And going back over 60 years, it was suggested by Henry Stommel that only 2 degrees of warming could cause a collapse of the overturning. Is that true? Well, this again depends on how you think the overturning is driven. And so one of the things that my group has worked on and that we published in the last year is a simple, quote unquote, box model of the overturning. So this is a schematic of the ocean. So we have a single deep box, and on the left, you can imagine this extending as an arm into the North Pacific. And on the right, you can imagine extending it as an arm into the North Atlantic. And we imagine that the light waters, the salty, warm waters of the tropics are a single box of water that's well mixed and has some variable depth. And that it drains into the North Pacific and North Atlantic, and it has the potential to sink. But that sinking is supplied in part by that upwelling in the Southern Ocean. Now, it turns out that if we were to allow all of that upwelling to drive overturning in the North Atlantic, we would get too strong an overturning. We'd get far too much transport. So we balance that by turbulent storms called eddies. I'll show you an example of that in just a minute. We also have upwelling in the tropics and mixing. We allow for some exchange between the basins, and we allow for the atmosphere to transport fresh water. And interestingly enough, what we find in this model is that when we warm the planet and allow all of these fluxes of fresh water to increase by a realistic amount, that we don't see, that's the blue lines here, we don't see a change in overturning. The overturning is basically stable between cooling of 5 degrees and warming of 10 degrees. However, when we allow the Southern Ocean to cool or warm more slowly than the North, because it is pinned to the deep ocean by this deep upwelling, then we can actually get a tip. And in this particular version of the model with this particular set of parameters, that tip is at about 5.8 degrees. We can try to simulate this in more complex models. And I know Adam talked a little bit about models. I'll just give you a little bit of a discussion about what they are. The models that I ran when I was at GFDL and worked on for years are what we call general circulation models. And much of this initial development was done at 2 laboratories, the Geophysical Fluid Dynamics Laboratory in Princeton by Suki Manabe, who won the Nobel Prize a few years ago, and Kirk Bryan. Also at NASA Goddard Institute for Space Studies by Jim Hansen and others. The idea of a model like this is that you divide the world up into boxes, each of which might be a degree on a side, maybe a few hundred meters, maybe a kilometer in the vertical, in the atmosphere, generally less than that in the ocean. You tile the whole ocean and atmosphere with that. And then you start off with 3-dimensional distributions of heat, mass, and maybe water vapor. In the ocean, it would be temperature and salt. This determines the density, which can then determine the pressure. So you take your background state and compute where's the pressure high, where's the pressure low. You then compute the flows that result from this pressure field, and you use these flows to transport the quantities that determine the pressure field. And you do this again and again and again, millions upon millions of times, which requires lots and lots of computation. And for a long time, the main places that provided that computation were federal laboratories. And one reason that we need lots of computation is that it turns out that the resolution of our models really matters. This is a computation I did with Bob Hallberg at GFDL back in 2006. The simulation on the left is a 1-degree simulation of surface currents in the Southern Ocean. You can see that there's a current that goes around the Southern Ocean, very much like what I showed in the nullschool.net video right at the beginning. This is what the video on the right is what happens if you run this at 1/6 of a degree, so about a 12-kilometer resolution. And you can see that there's much more phenomenology there. There's lots of turbulence. There's eddies. The thing is, this simulation on the right is about 200 times as expensive as the simulation on the left. It took a couple of months of computer time on what was then one of the fastest computers in the world, about half of that computer. So about a month of time on the fastest computer in the world to produce this. This was a landmark calculation at the time. And at the time, it was really only possible at federal labs. Now, there's another reason that we might care about the Southern Ocean, and that's because the storage of nutrients in the deep ocean is also associated with storage of carbon. So this shows nitrate. I showed you a plot of nitrate, a cross-section of nitrate in the Pacific earlier. So this is the nitrate concentration in micromoles per kilogram and the carbon concentration in micromoles per kilogram. There's a couple thousand micromoles per kilogram, which means about 20 or so grams of carbon in every ton of seawater. And you can see that they are related to each other, but there's a break in the slope. And that break in the slope occurs where southern source waters occur. And this is because nutrients are not used up in the Southern Ocean. They're not used up because the Southern Ocean lacks iron, which we'll get to in a little bit. And that means that some of the stored carbon leaks out in the Southern Ocean. Simultaneously, though, since we're putting extra carbon into the atmosphere, there's a flux of carbon into the ocean. That outgassing flux is reduced a little bit. And the carbon concentration of the ocean is actually going up. And again, it's going up in places where you expose this old water to the surface. If we were able to use up that nutrient, we would change the slope of this curve and we would store more carbon in the ocean. And we believe that this is what happened during the last glacial period. Iron-bearing dust was deposited in the Southern Ocean, caused more productivity, caused the nutrients to go down at the surface, and that actually resulted in more storage of carbon at depth. And that lowered atmospheric CO2 by about 100 parts per million and acted as an important feedback in the northern hemisphere glaciation that deposited this rock in Glen Rock, New Jersey, not too far from where I grew up. And so one of the things that we want to do with our models is understand how this is changing now and what will happen in the future. So we can do this, show two parts to this. One is we can look at how carbon is changing in the ocean. This shows results from an ensemble of these general circulation models that have a carbon cycle included. And it shows the change in dissolved inorganic carbon added to the ocean during historical times. And basically we see a pretty consistent picture with carbon building up in the mid to low latitudes. This is a big deal. There's something like 120 to 130 gigatons of carbon that goes into the ocean. It's about a third of what we put into the atmosphere. This is acting to actively slow slow greenhouse warming. We're putting about 2.5 billion tons of carbon into the ocean every year. Given the price of carbon on the European market, this is a tens of billions of dollar ecosystem service. So we actually have a pretty good idea. I don't show the data here, but the data actually agrees with this reasonably well. On the other hand, when you look at biological cycling, we're not there yet. So the black lines show two estimates of phytoplankton biomass, those little green things that I showed right at the beginning, that are the marine organisms that do photosynthesis. We can estimate their concentration from space. So there's 2 satellite estimates here in black, one solid line and one dashed line, and 7 different models that are state-of-the-art, and you can tell they're all over the place. Some of them have a decrease between the Southern Ocean and the North. Only one of them really has the right slope here. So we're a long way from actually being able to predict accurately the biology in the ocean. We can ask why that might be. And this is work that we're doing now in my group. One of the things that we can do is train machine learning emulators to try to understand what the drivers of these patterns are. And one thing that comes out from those emulators, if we look at the black lines here, this is the impact of iron on this distribution. So what this is saying is that iron acts to increase biomass in the north by about a factor of 2, and then it acts to produce a decrease as you move towards the south. Okay. This is not true in any of the models except this one. And this one happens to be the one that I worked on when I was at GFDL, and we got it right mostly because we cheated. Okay. So I want to then conclude about my part here about the Southern Ocean. So what I hope I've shown you today is the Southern Ocean is an important controller of Earth's climate. It helps to keep the Northern Hemisphere habitable by driving the global overturning circulation. It controls carbon dioxide concentrations in the atmosphere. It stabilizes climate by taking up excess carbon. But there's still a lot that we don't know about the Southern Ocean and its impacts. Right? I showed you one result of a tipping point. The tipping point depends on how much the Southern Ocean warms relative to the North. How does that actually work? We've used simple models to understand that, but we don't understand what's going to happen in the future. And that's potentially really important. It's also important because it points out that we need to measure this remote part of the ocean. I showed you a high-resolution model which had lots of ocean storms and lots of structure in the ocean. Those models are expensive. We really don't know what the effect of modeling ocean eddies or modeling the ocean at the appropriate high resolution is. We're just beginning to push into that physical domain. And there's reason to think that it might matter. And finally, as I showed you, we have trouble simulating ocean biology, which is absolutely critical for understanding the impacts of climate change. So some bigger picture messages here. If we're predicting drought or climate or hurricanes or fisheries, not on the short term, but over human lifetimes, we need to think of those as a global problem. The climate that your children and grandchildren will face is going to be affected by things that are happening right now in the Southern Ocean. Tracking where carbon goes in the environment is a global problem. The size of the global warming problem is determined by processes that are happening in the Southern Ocean. And that means that we have to measure in these places that are very remote. My mentor, Jorge Sarmiento, who recruited me to oceanography 40 years ago this fall, was saying this for a long time. You've got to measure in the Southern Ocean. You've got to measure in the Southern Ocean. And finally, one of his observational colleagues turned to him and said, Jorge, you want to measure in the Southern Ocean? You go down to the Southern Ocean and measure it. And well, he had a point. It's not a great place to measure. What we've done in the last decade is actually started to deploy robotic floats that start to measure both the physics and biology of the Southern Ocean, this critical region. This is one of the many programs that is under threat right now. Both NOAA and NASA have played a lead role in gathering data to track the processes that I'm talking about, and both NOAA and NASA science is desperately threatened. And both NOAA and NASA played a lead role in developing the models to understand their effects. And one of the things I hope you noticed in this talk, it was somewhat sub rosa, is that this work counters climate denial on the one hand, the idea that climate change is non-existent and it's a problem, but it also can counter the extreme alarmism. My estimates of when the overturning collapses are much less serious than other people's estimates. I don't know if that's right, but that's part of my job, is to try to give the best estimate, so that, because overreacting to climate change can be as bad as underreacting to it. And so there's still significant work to be done. And this is something I particularly want everyone in the room to know, but particularly the younger people in the audience. We've got a lot of work still to do to understand how our natural world works and to answer the questions we need to respond intelligently to climate change. So I'm going to finish off with thanks for you all for being here, and for the American people for funding my work, and particularly the federal agencies and their employees. My graduate work was funded by the Office of Naval Research. I spent 15 years working with NOAA, and the work in the Southern Ocean has actually been sponsored by a bunch of different agencies, including the National Science Foundation, NASA, DOE, the Defense Advanced Project Research Administration, and the Environmental Protection Agency. So thank you for all of this, and I'm happy to take questions.
Excellent. Thank you, Anand, for that wonderful talk. I want to start by asking what some people have asked in the chat, which is, how did you cheat to get the right answer in the, I think it was the biological production plot?
Sure. One of the things that we did in that model was that we didn't model zooplankton explicitly. What we did was say, as you go to more and more favorable conditions for phytoplankton, how do large and small phytoplankton change relative to each other? And we had the zooplankton do what produced the desired result, which is that if you double the concentration of small phytoplankton, small phytoplankton, large phytoplankton go up by a factor of 8. So we put that relationship, we sort of hardwired that relationship into the models, and that's really important in getting this contrast, because then in most models, most of the current generation of models, different phytoplankton compete with each other. A rising tide doesn't lift them all. And so that ended up being really important.
Thanks for clarifying that. I have a question for you about the tipping point work that you did. So I noticed that there, I didn't see any sea ice or ice sheets like Greenland or Antarctica in your plot. And my understanding is that some people think that it's melt from those that could tip the overturning circulation.
Yeah, I am unconvinced. If you actually look at the volumes of fresh water that you need to cause a tip, it's substantial. It's Amazon sized. At least if I take my simple models and calibrate them to the modern world, you basically need a 25% increase. And the size of the freshwater inputs we're seeing now is relatively small, and they tend to get mixed under the ice sheet as they mix up. So they tend to be diluted. So I'm not convinced. The other thing is that, again, no employees recently this year have been monitoring the transport through Drake Passage. Sorry, not Drake Passage. The Florida Current between Miami and the Bahamas. There's a submarine cable that can be monitored for volume transport. And they recently realized that if they corrected for the drift in the magnetic field, they don't see a trend in that transport, which is exactly what you expect to see if the overturning is in fact collapsing. So we don't actually have evidence that the overturning has been declining, which is consistent in a way with my own results saying, well, if you're pumping water from the Southern Ocean into the thermocline, it's going to be fairly hard to shut off the overturning. The good news is it's hard to shut off the overturning. The bad news is that you don't get any warning when it shuts off.
Ah, okay. I see.
So, yeah.
Great. Okay, well, let's turn to some more questions from the chat. Okay. So we have a question from Marcel, which is, how large a role do the shape and positions of the continents, also bathymetry, have on the locations of upwelling/descent?
That's a great question, and the answer is huge. So we do know that at one point, South America and it was connected to Antarctica, right? That the Drake Passage opened up sometime maybe 40 to 35 million years, 43 to 35 million years ago, I believe, is the rough time scale. And that opening was associated with the formation of permanent sea ice on Antarctica, or permanent land ice on Antarctica. Exactly when that happens and how that relates to other bathymetry is something that people argue about. It's not straightforward. You know, do you need a band of open latitudes, or if you can trace a particular pathway around, is that good enough? How big is good enough? All of these are are the kinds of detailed questions that people like me focus on. But we do know that isolating Antarctica from the rest of the world allowed it to have permanent ice and place us what is in the context of Earth history, an ice age. It has not been true for much of Earth history that you have permanent land ice on Antarctica. And so, yeah, so it does play a fairly significant role. The relative widths of the Atlantic and Pacific are something that people have talked about as being potentially important as well. That is actually one of the things I'll probably write a proposal on this summer. So, great question.
Cool. Just a clarifying question, we have a follow-up from Carolyn. Are you saying AMOC isn't quite the concern it's being portrayed?
I think I'm going to give two answers to that. I would say that there is, on the one hand, good reason to think that it's not quite the concern that's been portrayed. Okay, so if someone comes down and says, you know, I don't think it's the concern that's been portrayed, that's not necessarily false. The thing that keeps me awake at night is that there's a potential that we may be systematically deceiving ourselves, right? When we run these climate models, we take them and we run them out for 2,000 years to try to get a stable situation. If they were to tip during that point, we would retune the model in some way so that the model didn't tip. So we may be consistently pushing ourselves away from the edge. I do think that the extreme concern about the decline and overturning the AMOC is probably overblown. But yeah, I would say that there's also a sociology where if you can publish a paper showing that the AMOC is collapsing, that tends to get more attention than the ones that say, no, actually it's stable. And so, yeah.
Right. Okay, so we have some other questions. Z asks, what are the best models currently available? Do you know anyone working on creating better ones?
So the answer is that no model does everything perfectly. And this is what the modeling centers do. This is what people in the modeling centers don't sit around thinking about how to run the world. They sit around thinking about how to make the models better. Right? When I ran a modeling team at GFDL, I ran the ocean modeling team at GFDL when I was a Fed for 4 years. We had 25 people on that team. And so we put probably 60 to 70 human years of time trying to improve the various things about the model. Right? That's what people at the modeling centers do. And currently I'm on a DOE team that is doing that for their model. And if NASA ever gets money, I've been told that I will be working with their model to try to improve their model as well. So model improvement is something that we do all the time.
Yeah, and I'm now working with that same ocean modeling group at GFDL, and I would say they make the best model. But okay, so let's see, maybe one. This is an interesting question from Andre. Does climate and ocean research funded by DoD adjacent agencies get as widely disseminated as NASA, NOAA, et cetera research? Is it possible those agencies can pick up the slack of the science cuts?
That's an interesting question. I think one issue with agencies like DARPA, so I did have some DARPA funding. The tipping point work I just showed you was funded by DARPA. They tend not to be good at long-term support. They tend to want to do tend to want to really push the envelope a long way. They have not been as good at long-term support. NASA and NOAA are the two agencies that have been consistent in their support over decades. And that's the thing. It takes a long time because of the length of these simulations. It often takes a long time. It'll be interesting to see what happens as we do get some of these AI models, if they have any skill, which I am still of the belief that garbage in, garbage out is what describes probably 90% of AI. There may be opportunities there. I will say that the DoD is quite aware of climate change, right? Sound propagation in the Arctic is very different now than it used to be, and that is a major concern for the Navy as they chase Russian subs around the Arctic. So the Navy is completely aware of this. Whether they are able to convince their higher-ups of that is another question.
Great. Well, I think that wraps up our Q&A. If you have any last things you'd like to say.
Thanks for organizing, Henri.
All right,
Good to
great.
see you.
Thank you so much, Anand. Great to see you. And let's all thank Anand for the great talk and Q&A in the chat. Okay, so if you're just joining in, thank you for joining the Weather and Climate live stream. We are at hour 34 out of 100, more than a third of the way there. And yeah, thank you for joining us. It's been a great vibe. We're learning lots of climate science, lots of weather science, learning about the forecasts that make society run. We've seen a lot of great talks so far. The next speaker is no exception. But before they join us, let's just take a moment to remember why we're here. Weather and climate forecasts are important. And we have in the US been leading that for decades. As Anand just showed, we have been doing really pioneering ocean climate modeling research, for example. We also, in the US, invented weather forecasting, numerical weather prediction. This is something that started out as kind of a crazy idea in the 40s and 50s, and then over the decades, it's actually become so reliable that now you have an app on your phone that tells you what the weather will be in a couple of days with pretty accurately, and so you can rely on that. And all of that has been funded by the US government, a lot of that research, and that is through funding grants to research universities, to government labs, to institutions, to public and private partnerships. And a lot of that funding is under threat. And right now there are budget cuts that are being proposed to fundamental science in weather and climate, but also to weather forecasting operational centers. We have short-staffed weather stations. We have weather balloons that are not being deployed when they should be. All of this is undermining our weather and climate forecasts. So we need your help to help us save those forecasts. So please, you can see the banner under me. It says you can go to wclivestream.com/act, and there will be instructions on how to call your representatives and some template text you can work around to craft your message on how you'd like to advocate to support this science. Okay, and with that, I'm very pleased to introduce our next speaker, who will tell us exactly how these observations do help with weather. So I am pleased to introduce Chris Vagasky, who is a meteorologist who previously worked as the North American Soundings Solutions Manager for Vaisala Inc. Chris holds a bachelor's degree in operational meteorology and a master's degree in applied meteorology, both from Mississippi State University. In addition to his general expertise on meteorological measurements and their application for weather forecasting, Chris has specialized expertise on lightning and lightning safety. One of the main themes of this event is the importance of real-time and continuous monitoring of Earth's weather and climate for the forecast that society relies on. So I'm so excited to have Chris here to tell us about just that. Take it away, Chris.
Okay, well, thank you, Henri, and thanks everybody for sitting in and enjoying this live stream over the last 34 hours. I'm here to give you the lowdown on weather measurements up high. So we're going to be talking about those weather balloons and all the important things that go into measuring the weather in the upper atmosphere. But I want to start with a very simple statement. Measurements are the basis of weather and climate. And I think if you've been sitting in these talks, in almost every one, there is some sort of measurement that is being discussed, whether it's ocean salinity or ocean temperature or air temperature or relative humidity. Measurements are the basis of weather and climate. And that's something to keep in mind as we go through this presentation here. And as you sit and listen to the other presenters over the next 66 hours. So whether you're a farmer or a home gardener and you need to know, do I need to water my plants today? Do I need to fertilize my plants today? When should I fertilize? How much should I fertilize so that I don't send nitrogen and phosphorus down the river and cause algae blooms? When can I expect pests to start emerging? When do I need to apply pest control? If you are running a race, if you are the meteorologist or the emergency manager that is supporting that race and letting the race director know you have a line of storms coming in, you can't start, or the line of storms is far enough away that you'll be able to get this race in. If you are a pilot and you're flying from point A to point B, or you're this crazy pilot here who is flying over waves upon waves upon waves over the Rocky Mountains, or you're a passenger on a plane, or if you're just deciding, if the weather is good enough for you to take a hike on any given summer or fall day, or if you're just going out for a run after you get off work and it was raining, but now the sun has started to emerge and you've got a nice double rainbow. You are one of the 8.2 billion people on the planet that is affected by weather every day. So we need to have not just weather measurements, we need to have good weather measurements. So as you're listening to all of the talks over the next couple of days, keep that in mind, keep the measurements in mind, because as I said at the very beginning, weather and climate is based on measurements. So measurements are in everything that we are doing, no matter who the scientist is that's talking. Now, it's pretty easy to measure surface weather. If you've got $500, if you've got $5,000, if you've got $50,000, we can find you a weather station that you can go and set up somewhere, whether it's in your backyard, whether it's next to a farm field, whether it's at an airport, and you can measure all sorts of different measurements. Like on this weather station here, you'll see up at the top is an anemometer measuring the wind speed, the wind direction, the wind gusts, letting you know how breezy it is. You have a pyranometer measuring the amount of solar radiation that's coming in every millisecond. You got a temperature and humidity probe to let you know how hot and sticky or cold and dry it is. A rain gauge to let you know how much rain you've received in the last day, the last week, the last year. Barometric pressure, so you know how much weight the atmosphere is pressing down on you with. Soil moisture, soil measurements, to let you know how warm, how cool, how wet, how dry the soil is, which goes a long way to supporting your plants, your farms, to understanding, will there be flooding, will snow accumulate? If you have any amount of money, you can come up with and set up a weather station somewhere to collect surface weather data. And that's great because, well, that's where we all are. We're here sitting on the surface of the earth. So having a lot of really good information about the weather at the surface of the earth helps us to live our lives, helps us to accomplish all of those things that we went through in the first few slides, whether it's farming or gardening or running a race or flying an airplane. But, we've been measuring weather at the surface for about 150 years or so. This is the first weather map that's available in the Weather Map archives, January 1st of 1871. This map, if you can read the pencil handwriting up there, was at 11:35. I think that says PM. And that would have been Eastern time in Washington, D.C. Because all of these stations that you see, and there's just a handful of them, Nashville and St. Louis and Cheyenne and Omaha and Milwaukee and Detroit, they would telegraph in the weather conditions to the Smithsonian. And there would be multiple people there at the Smithsonian in Washington, D.C. that would interpret the messages that came across on the telegraph and plot it up on a map. And people would go to the Smithsonian just to look at the weather map and see what the weather was somewhere else in the country. But, it's kind of hard to go through and make a forecast or make any kind of understanding of what's going on with the weather when you have so few pieces of data. You might do fairly well in the Great Lakes region. I mean, you've got Duluth and St. Paul, Milwaukee, Chicago, Detroit, Toledo, Cleveland. So, you could get a pretty good understanding of what's going on in the Western and the Lower Great Lakes, but what's going on in Santa Fe or what's going on in Fort Benton, Montana, you just don't know. Lucky for us, there's a whole lot of history that happens. So after 1871, the automobile, the Wright brothers fly for the first time. There's a couple of world wars thrown in there. Computers are developed. We fly to the moon. All sorts of history happens, and weather plays a big role in all of this history that happens. So we have to continue to develop weather measurements and expand weather measurements. And eventually, 154 years after that map that I just showed, you get a map that looks like this. And this is global weather stations that are providing data to a company called Synoptic Data that aggregates and sends out all of the data coming from all of these different weather stations. There's a lot of dots on this map. They counted them for me, so I didn't have to count them, but there's over 140,000 dots on this map that are primarily surface weather. But this doesn't include every weather station. There will be a lot of backyard weather stations that people don't have connected in a way that gets to Synoptic, or there's some countries that that haven't provided their data to Synoptic. So, the 140,000 weather stations here is just a sampling of the data that we're able to collect at the surface. So, like I said, it's fairly easy to measure weather at the surface of the earth. $500 you can go on Amazon, or you can go to Farm and Fleet or your favorite store and pick up a fairly good quality backyard weather station. Or, if you really have a lot of money in your wallet, you can go and get a whole airport weather station and find somewhere to put that and measure all sorts of different things. But weather doesn't just happen at the surface. I've been telling people, a lot lately that weather begins above you and somewhere else. So here is the atmosphere. We live in the lowest 2 miles of the atmosphere in general. There's not too many people that live above 10,000 feet on the planet. Some people in Colorado and in the Rockies and in the Himalayas do, but most people live in the lowest mile of the atmosphere. So in the lowest 1 mile of the troposphere, and that's where all of the weather, the raindrops that keep falling on your head, the snowflakes, the hailstorms, the wind, the hot temperatures, the cold temperatures, that's all happening in the troposphere, which is the lowest 6 miles or so of the atmosphere. But we're only in that lowest mile to 2 miles. Unless you're one of those adventurous folks who go up to the top of Mount Everest and you're about 10 kilometers above sea level at that point. But look at all the rest of the atmosphere that's above you. And all of that weather that's happening down on your head, that's happening up above you first. And it's usually coming from somewhere else. Here in the United States, weather tends to move from west to east. It could be northwest to southeast or southwest to northeast, but it generally has that west to east flow. So the thunderstorm that rains on you and sends hail at you, that usually developed somewhere else and moved over you. It doesn't typically develop right overhead. So it happens, the weather happens above you and somewhere else. So that's the weather that we need to go through and measure. But it's impractical to build 20-mile tall weather stations. It's expensive to do that. People have only gone 6 miles up if you climb Mount Everest. You put 20-mile weather stations up all over the place, which I did in this image here. So here's our 20-mile tall weather station that towers over thunderstorms. It towers over Mount Everest. It impedes on commercial air traffic. It impedes on spy traffic. It goes through the ozone layer. I know a lot of really good people who do a great job of putting weather stations in. Not a single one of them would want to climb a 20-mile tall tower to attach weather stations or weather instruments all the way up and down that 20-mile tall tower. So we need to have a different way of measuring the weather that's above us and somewhere else. But we're really good at that. We've been measuring data above the ground for almost 300 years now. Back in 1749, Alexander Wilson started flying thermometers on kites to start getting an understanding of temperature above the surface of the earth. 3 years later, Benjamin Franklin was flying his kite and found that lightning had electricity in it. In the late 1700s, before people took hot air balloons, they would release pilot balloons to watch and see how the winds moved those balloons, so they knew how the hot air balloon was going to move around. And in 1892, a couple of scientists started attaching instruments to unmanned balloons. So those were the first weather balloons back in 1892. But you had to go through and recover the balloon and the instruments to collect the data. And that could be a multiple day process to go through and find the balloon, find the instruments, collect the data, and interpret it. So none of these techniques, except for maybe Ben Franklin's kite experiment, provided real-time data to the ground. Anybody read Morse code? I don't read Morse code anymore. But luckily, the telegraph was invented. So the same technology that went into wired telegraphy helped transmit data from the weather balloon to the surface. So thanks to the telegraph, we can now transmit data in real time from a weather balloon back to the surface of the Earth. This is Professor Vilho Väisälä. In the 1920s and 1930s, he developed the operating principles of the radiosonde. The radio part of the radiosonde means that it's using radio to communicate back to Earth. And that's him with his first radiosonde back in the 1930s. And we've been flying weather balloons with radiosondes ever since. The first radiosondes, they transmitted pressure, temperature, and humidity measurements back to Earth. And then the operator of the radiosonde had to track the balloon using a theodolite. So a little handheld telescope that you just track the weather balloon with, and you tracked it until the balloon got too small or till it went behind clouds. And that was how you derived wind measurements. An interesting thing about this is the humidity sensor used to be a strand of blonde human hair. Not anymore. We've gotten a little bit more technical since then, but this was how we were doing balloon measurements in the 1930s. So we just release really big balloons. I like to call them the world's biggest party balloon. This is me holding a balloon that I could stand up in and still have another foot or two. So these balloons are very big, very stretchy. When it's inflated, it's at least 5 to 6 feet in diameter. So most people, if you could fit through the neck of the balloon, you'd be able to stand up in it. As it rises through the atmosphere and it gets to 110, 120,000 feet, as it rises through the atmosphere, it continues to stretch and it reaches the size of a Ford Taurus. Some of them can be even bigger, be about the size of a school bus, at which point they can't stretch any further and they just rip themselves apart. And they're filled with helium, or they're filled with hydrogen to go through and be lighter than air or less dense than air and rise through the atmosphere. And they carry the radiosonde. So it's this small little instrument package that acts like an all-in-one weather station. So instead of having 20-mile tall weather stations, we just send an all-in-one weather station up those 20 miles. And this is what they look like. They're launched twice a day, every day, most of the time, from around 900 locations around the world. So if you see one, don't be afraid. It's harmless. It's not going to hurt anything. It's just a little instrument package that has some sciencey things on it. A platinum thermistor, so a really small, thin piece of platinum that allows us to measure temperature as electricity passes across it. There's a capacitor that changes the amount of electricity that is able to be stored based on the amount of humidity that there is in the atmosphere. We use GPS and sometimes barometric pressure sensors to measure the atmospheric pressure. The GPS helps us to track the balloon, so we know the wind speed and the wind direction. We know how high it is. And all of this data transmits back through a radio antenna. So the little skinny strand there, that's a radio antenna. And these can be tracked for hundreds of kilometers to hundreds of miles away. All of this data gets transmitted back to a computer where all of the data gets processed. You have a couple of antennas, a radio antenna and a GPS antenna to keep track of everything in real time. And then you get measurements every 15 feet through the atmosphere. The data get plotted on thermodynamic diagrams. They get plotted on maps, ingested into computer models to help meteorologists and other scientists visualize and understand the structure of the atmosphere. So this is a thermodynamic diagram. This one was released out of Midland, Texas this morning at 12 UTC. So that's 7 a.m. in Midland, Texas. To give you an idea of what's going on here, The numbers on the left-hand side that go from 1,000 up to 100, that's air pressure. So as you go higher and higher in the atmosphere, you have less and less of the atmosphere above you, so those numbers get smaller. The red line is the temperature measurement of the radiosonde. The green line is the humidity measurement from the radiosonde. And then these barbs are telling you the wind speed and the wind direction at each of the different heights. And you get all sorts of different information back, including how quickly the temperature is cooling off as the balloon rises, how moist, how dry is the atmosphere, how warm is the atmosphere. Is the wind turning with height? Is the wind changing speeds with height? And this helps meteorologists to make a forecast and better understand the forecast, especially in this case with regards to severe weather. And this sounding is what we would call a loaded gun type sounding, where you have a layer above the surface of the earth. So the surface is the bottom of the measurements. Right above the surface is a warm layer that will prevent storms from rising. So you want cooler air aloft for clouds to be able to rise and to form into thunderstorms. But this warm layer is what we would call a cap, and it prevents those air parcels from rising and turning into thunderstorms. But above that warm layer, there's a big area between the red line and this dashed line that is the amount of energy that's available for a thunderstorm to develop. And if a thunderstorm can get above the cap and go into this atmosphere where there's energy, it can turn into a big storm and start producing hail and lightning and all the things you associate with thunderstorms. So this is what meteorologists look at as they're looking at the weather balloon data for severe weather. But you can also look at things like all of the data from the same elevation, the same pressure level all across the country. And so this is this morning's weather map from the jet stream level. So this is where airplanes fly. And so you can see all of the locations where a weather balloon was launched with its temperature, its dew point temperature, so the amount of moisture in the atmosphere, the wind speed and the wind direction, and you get a picture of what the atmosphere is doing. Now, these balloon launches happen at the same time around the world every day. So meteorologists get a complete picture of the atmosphere all around the world twice a day, every day. Now, the launch that we saw from the Midland, Texas balloon launch, that sounding that we showed, they said that was a loaded gun sounding. And if a storm could develop, you would be able to tap into that energy and become a nice big beefy storm and start producing hail and lightning. Well, that's what happened today. That's what happened this afternoon. The National Science Foundation Ice Chip campaign is in West Central Texas today, and they deployed on a storm that formed southwest of Lubbock, and they came across hail that was 2.5 to 3.5 inches in diameter. The Ice Chip campaign is working to better understand how hail forms in thunderstorms and how it gets as big as it does and how it melts as it falls through the atmosphere so that we can have better warnings about severe hail. We can come up with better building materials so that roofs don't get damaged as much or that siding doesn't get damaged as much. This campaign is really supporting keeping people safe, keeping property safe from severe weather. So this is just one example of how these soundings, these balloon launches, support meteorologists. Now here's a lot of dots on the map. This is the entire database of the Integrated Global Radiosonde Archive. So this looks at radiosonde data from 1905 to 2025. There are 2,879 sounding locations with over 51 million soundings available. So we've done a lot of upper air measurements in the last 120 years. The white dots, these are the stations that have been active in 2025. There are a lot fewer, only 838 that have been active in 2025. And there are significant gaps across the planet. So Western South America, most of Africa, parts of Asia, parts of Canada even, that have significant gaps in the balloon launch coverage. And each of these missing locations, each of these dots that not there, is a missing data point that would help us understand the atmosphere better. That would help us provide more data for the weather models. That would give the meteorologists more data to look at to understand what's going on in the atmosphere. Closer to home here in the United States, there's 84 dots on the map here. That's 10% of the global radio sound network. But we've started to see a significant reduction in the number of balloon launches. On March 20th, the National Weather Service said it was going to start reducing launches because of staff shortages. And this chart that was put together by Scott Danson and some colleagues at the Washington Post shows the number of missing balloon launches by day since the beginning of the year. And you can see that upward trend. Now, not every station launches a balloon every day. Sometimes the weather is too bad. You don't want to send somebody out in a thunderstorm to launch a balloon. Sometimes you just don't have helium or hydrogen to go through and launch a balloon. Sometimes the ground equipment just isn't working, or you launch a balloon and it gets tangled up in a tree or hits a building and you're unable to get a sounding. But you can see once the staff shortages started, the number of missing launches doubled or tripled. Now it says that 3 stations are closed indefinitely. Those have been closed for a couple of years in some cases. A station in Chatham, Massachusetts had to close in 2021 because of coastal erosion, and it was too dangerous to send somebody out there. There was a fear that the balloon launch location was going to actually tumble into the ocean. And in Denver and in Tallahassee, helium shortages have prevented balloon launches from occurring. Now, the locations of those 2 balloon sites don't allow for hydrogen to be used because they're too close to population and too close to people. Hydrogen, a little explosive, and it's a safety hazard. Now, where have the balloons failed to launch? So this is another map that was put together by Scott Danson and colleagues at the Washington Post. And you could see where in some cases up to 100% of balloon launches have been missed in the last few months. A lot of them are taking place over the northern Rockies and the northern plains. And that's where a lot of the storm systems that cause severe weather, or the storm systems that will steer tropical storms and hurricanes, that's where they get their act together. So it's a concern to see this many balloon launches being missed. Tennessee, the Nashville site, I will point out that this station had ground equipment issues for a couple of weeks. So that was a case where it wasn't because of a staff shortage. It was just because of an equipment failure and they needed to get some repairs. But a lot of these stations are missing data because of staff shortages or because of equipment failures or anything. But each time we miss a balloon launch, that data is gone forever. So what happens when the balloons don't fly? Well, we lose one of the only direct measurements of the atmosphere above the surface. Sure, there's satellites, there's radiometers, there's remote sensing, but those aren't at that 15-foot by 15-foot resolution. And the data for those are actually calibrated by using radiosonde data. So radiosondes are actually measuring the atmosphere. Remote sensing is looking at a radio signal and interpreting or estimating what the atmosphere would be like. You may have heard of chaos theory, the butterfly effect. Butterfly flaps its wings in Brazil and you get that hailstorm southwest of Lubbock. Well, small errors in initial conditions, they become big errors over time. So if you're filling the computer models with interpolated data or remotely sensed data, as time goes on in the computer model, those errors start to multiply and they get bigger and bigger. And as I had mentioned, once you miss a flight, that data is gone forever. So it's interrupting climatological data collection. Some of these balloon sites have been collecting data for at least 50 years. The Denver site goes back to 1919. And in 2022, it stopped collecting data. That was 100 years of a data base that stopped because of a helium shortage. So we're missing the ability to watch trends over time. This is the map I showed a little bit ago, but we had a 900-mile stretch with no balloon launches. We had a 1,200-mile stretch with no balloon launches. That's a lot of the United States that did not have balloon launches this morning. And the balloon launches can have a significant impact. They reduce the global forecast error by 10 to 20%. So, the daily forecast error gets looked at every 24 hours to see how accurate was the forecast compared to what we actually measured. Radiosondes give a 10 to 20% reduction in that forecast error. So it's important for these things to be flying so that we can have as accurate forecasts as we can. And that's really important as we're getting into hurricane season, which officially starts on June 1st. This is a map from September 2022 as Hurricane Ian got started. They were launching 4 times daily across almost the entire eastern United States to help provide more data for the forecasters to better understand potential steering patterns, to understand how the atmosphere would allow Hurricane Ian to strengthen into a Category 5 hurricane before it made landfall in southwestern Florida. Now, what goes up must also come down. I'm going to very briefly talk about a dropsonde. It's a weather balloon in reverse. So you open the hatch on an aircraft and you send a dropsonde into a winter storm or a hurricane or an atmospheric river to collect data, the same data, temperature, humidity, wind speed, wind direction, air pressure. And a paper was just published last week in Weather and Forecasting by Melissa Piper and Ryan Torn. They found that forecasts that included dropsonde data were 24% more accurate than the forecasts that didn't have the dropsonde data in it. A 24% more accurate hurricane forecast is the difference between evacuating the entire Florida coast or a small section of the Florida coast. That saves lives, that saves time, that saves money. So the weather balloons are important. They're our only direct measurement of the atmospheric profile on a global scale. We've been doing them for around 100 years because they work. They reduce the forecast error by about 10 to 20%. And as we work to build weather-ready nations, as we work to expand early warnings for all, as we work to develop a global basic observing network, weather balloon observations are a key component here in the United States and globally. So thank you all for joining. I know this is a very long stream, and I know I saw in the chat people talking about wanting to go and then getting caught up in just how exciting this is. So, thank you for the attention. Thanks for the invitation to talk to you about just how important these measurements are. And, enjoy the other 66 hours of this stream, and happy to answer any questions.
Wonderful. Thanks for the great talk, Chris. We have a lot of questions from the chat, so I was thinking maybe we could try and do rapid fire answers because a lot of these I think have pretty quick answers. So let's just go from the top. So are weather measurements like you're talking about, why I get told if it's a good running day in my widgets?
Yes. So all of those weather measurements feed into computer models or feed into the weather apps that tell you is the weather good, is the weather bad. and they feed into the models that give you the forecast. It will tell you today, tomorrow, the next day, is the weather going to be good or bad. So weather measurements support everything that everybody does every day, whether you're thinking about it or not.
Great. Belton asks, are there restrictions on where these, I think these is the surface weather stations, can be placed?
So with weather stations, you want to have them in a relatively clear location so that the trees aren't shading the temperature sensor, so that you're getting clear airflow across the temperature sensor and the wind sensor. But they can go fairly close to buildings and things like that. When we install weather stations, we keep them at least 100 feet away from buildings, tall trees, and things like that to give a lot of clearance to the weather station. But if you put one in your backyard, it's giving you the absolute measurement of what's going on in your backyard with those conditions. So you could do that as well.
Great. Kelly is fascinated by weather balloons and has 3 questions. Did they have to follow them? This was for the early ones. Don't know if I missed it, but what's their lifespan? And what if there's erratic winds?
Yeah, so if there are erratic winds, that balloon is just following the wind. The weather balloons have landed right next to where they launched. They've landed 1,000 miles away from where they were launched. The radio antenna is tracking that balloon in real time. So we always know where it is. There is a group, if you go to sondhub.org, they track weather balloons in real time. And there are actually people that go and chase weather balloons so that they can take the radio sound as a souvenir. And the balloon flight lasts about 2 hours in general. So it takes about 2 hours to rise all the way up to 120,000 feet, and then it comes back down to the earth fairly quickly after that.
Great. Okay, let's see. There are a few questions about how citizens can get involved. So one was, Jill asked, can citizens volunteer to launch balloons? And then Kelsey asked, would it be possible to invite the public to view balloon launches on certain days and in small groups in an effort to raise awareness of their importance?
Yes, the Weather Service I've seen actually have groups come out to witness balloon launches. The Weather Service really likes to do a lot of outreach. So you can always reach out to a Weather Service office that does a balloon launch and ask, if you can come out to witness a launch. Safety restrictions would prevent them from allowing a citizen to volunteer to launch the balloon. But universities do balloon launches. So there are opportunities for people who are really interested in balloon launches and collecting weather balloon data to get involved.
Yeah, I got to do it one of my first weeks in an atmospheric science program. It was pretty cool. We got to see all the data come in live.
And everybody loves balloons from 8 months to 80 years old. So when you get to play with a giant one like that, it's always exciting.
Yeah. Okay, we have a couple of questions about flight safety. So Raymond asks, does lack of balloons affect commercial flight safety? And the flip side of that is there's a question, drop sound seems so cool. How do we keep the pilots safe when they're above a storm?
Yeah, so missing measurements, it can affect flight safety. And that's a potential concern there in Alaska, especially where you're flying bush planes across from small city to small city, and not having enough data could cause impacts. Drop sounds are very cool. I think they're one of the coolest weather instruments that are manufactured. The Air Force hurricane hunters, they actually taped a picture of me to a drop sound and threw me into a hurricane a couple of years ago. I don't know whether to be offended or flattered. Tomorrow, I think, Jeff Masters is going to talk about a hurricane hunter flight that he was on in 1989 that almost took down the airplane. So come to that talk to learn a lot about flying through hurricanes and hurricane hunting.
Wow.
There are meteorologists on every flight to steer the hurricane hunters to one, where they need to go to drop the drop zones, and two, where not to fly. So safety is always something that is a key in hurricane hunting, which has been done since the 1940s. So we're coming up on 85 years of hurricane hunting.
Yeah. So we have a couple more questions. Chris asks, there's been a lot of talk about ML AI this evening, and one theme has been garbage in, garbage out. So how do these soundings influence the skill of ML AI models?
Yep, garbage in, garbage out. That's something that people always talk about with regular weather models and with machine learning and AI models. Those models are data hungry. So the more good data you can put into them, the better that they'll be. The more observations we have, the easier it is for those models to understand what's going on and look at it and do pattern recognition and do all the different things that those models do to put out good data from their output.
Great. So Jill asks a question, what are your thoughts on SondHub? I assume that's some kind of repository for putting sond data. I'm not sure. And is it helpful for folks to recover radio sonds?
Yep, SondHub is what I was talking about, where the people actually chase radio sonds. It is a good way to follow the balloon launches and see where the balloons are going. And people do recover radio sonds from using SondHub. Historically, it's been about 1 in 10 to 1 in 20 balloons that actually get recovered with SondHub. That number is actually going up. So it's a great way to learn more about the balloon launches that are going on, see where they're going, and then even to find a souvenir.
Great. Okay, so we're about to relaunch the stream, but I want to do one last question, a little lighthearted one. Will we ever be able to track a swarm of multiple probes inside the same storm at once, like in Twister?
We are doing that, not with little tiny things in the hundreds or thousands, but we can track 4, 8, 10, 20 radio sonds with a single system at one time. And on field campaigns, there are a lot of balloons going in and out all the time. So we are doing a lot of those types of swarms.
Great. Well, thank you so much, Chris, for that really insightful talk and for answering so many questions. I think that was a record for most questions answered in a Q&A.
Well, thanks again, everybody. I really appreciate it.
Yeah, great. Thanks. Have a good night, Chris. All right, everyone. We're coming up on, I don't even know if our hour tracker is correct anymore, but I guess hour 35 or so. We've been at almost 8 hours on this specific live stream, and so we're going to have to relaunch our stream because we can't keep the videos for more than 8 or 10 hours. So you're going to have to refresh at wclivestream.com/watch pretty soon. That will link you to the new live stream once it reboots. So make sure that you stick around, and we'll see you soon. And if you are just joining us, thank you for checking in on the live stream. We have another 60-something hours to go. I am having a great time, but also this is 34 hours is a long time. I've been only on it live for maybe 6 hours now, but I've been on behind the scenes, and it's really hard to step away because there's so many good talks, so many great conversations in the chat. So thanks so much for sticking in and learning about the science, asking questions about it. And then also, I'm seeing in the chat that many people are acting also, right? We're all here to support weather and climate science. Like Chris just said, the data that, federally funded teams are making in the atmosphere are essential. Margaret, do you have something to say?
I'm here to assist you all with staying on as we relaunch our stream. So this is going to be a new link. This video is going to end. And if you go to wclivestream.com/watch or go to our YouTube page and click live, you'll be able to stay on. I've counted the number of you that are here, and I expect to see all of you in the new room. We have a really exciting talk coming up for hour 35. So it's going to be worth making that switch. Okay, let's do it.
Awesome. See you all soon.
See ya.